Welcome to the Beginner's Guide to IoT and Hardware Hacking on YouTube. If you are interested in learning about IoT and hardware hacking, then you are absolutely in the right place. We're going to get over to the course very shortly, but before we do, just a quick few items of note. First one is, my name is Andrew Bellini. I also go as Digital Andrew, and I am the creator of this course. I also have my own YouTube channel, Digital Andrew, that I will drop a link to down below, where I'm going to be posting a lot of IoT and hardware hacking content and lessons on in 2026. So check it out, and if you are interested, make sure you are subscribed. The second thing is this is the YouTube version of the course, which is in its entirety on TCM Security Academy. This YouTube version is going to cover the first approximately 2/3 of the course. So if you want to get access to the entire course and those last few sections, then go ahead and check out the TCM Security Academy. I will drop a link to it down below. You'll also get things like a certificate of completion when you complete the course as well. And then finally, we also have a certificate that goes along with this course called the Practical IoT Pen Test Associate, or PIPA for short. And if you are interested in challenging that or challenging yourself to take that, I will drop a link to all of the details about that down below. So with that being said, let's actually hop over to the course now. I hope you enjoy it. Welcome everyone to the Beginner's Guide to IoT and Hardware Hacking. First off, thank you so much for choosing to take this course. I've got some really exciting material and I cannot wait to get started on it. Before we do, in this video, we're going to cover some of the standard course intro topics, such as a brief introduction about myself, a little bit on the course curriculum, and then some of the course prerequisites. So without further ado, let's get started with the intro. So to start, just a little bit about me. My name's Andrew Bellini, and my background is in electrical engineering. I have a bachelor's of engineering science, focusing on electrical engineering and then more specifically specializing in wireless technology. I'm also a licensed professional engineer in Ontario, Canada. Throughout my career, I've worked as an electrical engineer, working across many different industries, including SCADA, control systems, and also embedded systems and electronics for the rail industry. I'm also a TCM student, and I actually took the PEH course many years ago when it was only available through Udemy, and I actually now work as a cybersecurity technical trainer for a cybersecurity company where I train the employees. I generally go by Digital Andrew on my social media, and that's how you'll see me in Discord. And the best way to get in touch with me if you want to reach out is through my LinkedIn, which I've linked here. You can also reach me on Twitter, and then I also have a website. Just a few quick non-technical details about me in case you're interested. I am a dad. I love to play guitar. I play in a band, so if you're any good at OSINT, you can probably track me down there. And I also love the outdoors and fishing. Okay, so moving on, let's take a look at the curriculum for the course. So we're going to begin with Electrical Engineering for Hackers 101, and this is going to be a mostly theoretical section of the course where we will learn about some of the most important fundamentals of electricity, electrical engineering, and electronics. In the second section of the course, we're going to take a hands-on look at PCBs, some of their characteristics and components, and then learn how to use multimeters. We'll then move on to the third section of the course, which is a continuation of Electrical Engineering for Hackers, where we will continue to learn about some of those fundamental theories of electricity, electrical engineering, and electronics. After that, we'll move on to a hands-on section where we learn about logic analyzers and how we can use those to measure and sniff out UART communication, and in doing so, learn about UART. We'll then move on to some hardware Recon and OSINT, where we'll take a look at the various Recon we can perform on our hardware and then the additional information that we can find open source on the internet. After that, we will hook up to the router with the UART shell that we found, and we will actually do some live enumeration of our router. In the next section of the course, we're going to learn about SPI, or Serial Peripheral Interface Protocol, and then we will actually use that protocol to extract the firmware off of the router, and then we'll perform some analysis on that firmware. In section 8, we will then actually do some reverse engineering of that firmware and take a look at how we can start to look for vulnerabilities in it. We'll then do a quick course challenge and course wrap up. Before we move on to the prerequisites of the course, I do just really want to quickly chat about why I've included some theory sections about electrical engineering and electronics in this course. So one of the questions that I very frequently see asked about ethical hacking is, do I need to understand programming or learn how to program? And, the answer to that, or the one that I kind of think is the best answer, is that, you definitely don't need to fully understand programming or be a programmer to get into ethical hacking. However, the more you understand about programming, some of the fundamentals of it, and actually, being able to look at code and understand how that code functions, this is, of course, going to make you a much better ethical hacker and help a lot. So, of course, if you're doing web penetration testing, then you don't need to know how to go and build out a website, from the ground up and understand fully how to do that. However, you should be able to look at the code and have a good understanding of what it's doing. And this is the same for hardware hacking, or at least that's my belief. You don't need to be, a full-fledged electrical engineer, fully understand electronics, or be able to design a circuit from the ground up. However, it's going to benefit you a lot if when you take a look at circuits, you get an idea of, what is going on with that circuit, and you're able to identify the different components. And that's why I have included the 2 theoretical sections on electrical engineering for hackers. So if you are finding that these are too much, like school, you just want to get to the hacking, then of course, this course is yours to make what you want with it. And, I would encourage you to then just move on to some of the hacking sections. But I do think that they will be really beneficial to you if you do want to, in the future, continue on with hardware hacking. With that being said, let's move on to the course prerequisites. So there aren't actually a lot of prerequisites for this actual course. I have listed it as a beginner's course. And I do just want to quickly chat about that. What I mean by beginners is that this is a beginner's course to hardware and IoT hacking. Hardware and IoT hacking in itself is somewhat of a complex topic in that it covers a broad range of different underlying topics. So, I would consider this to probably be like an intermediate level course if you're just looking at it, from an outward lens. And then it's more of a beginner's hardware and IoT hacking course. So with that being said, I think it's going to be really beneficial for you if you have a general understanding of Linux, because a lot of the IoT devices that we're going to be looking at, and specifically the router that we're going to be working on this course, are going to be running embedded Linux. And then, of course, we're going to be using Kali Linux as well as our attack machine. And then also, you should have a basic understanding of penetration testing and some of those principles. So if you're not feeling brushed up on these topics enough, then I would suggest there's a very good Linux course in the TCM Academy that would go over everything that you would need to know. And then, of course, the Practical Ethical Hacking course by TCM Academy is also an excellent precursor to this if you're not feeling brushed up on penetration testing. So then just the things that you do not need to know, though, is if you don't have any background in electrical engineering or knowledge of electricity or electronics, that's okay. We'll cover all of that. You do not need to know how to use any of the tools that we're going to be using, so either software or physical, so things like the multimeter or the logic analyzer. We'll go over all that. And then you do not need any specific knowledge on IoT devices. We will cover all of that. So that wraps up this video. I do have a couple of quick videos after this that go over some really important notices or topics. So I would really encourage you, please watch those before moving on to the course. But that wraps up this video. I'll see you over in the next one. Welcome everyone. So this video, I've just got a really quick notice to make about the TP-Link router that we're going to be using in this course. So if you're anything like me, you may have gone ahead and bought these and you just want to open it up and check everything out. And that's all good to do, but I just want to quickly show you one thing that I think most people will throw away and we're going to try and keep in this course. So this is not just your standard unboxing video. I just want to really quickly show you something. So I'm just going to open up the box here actually. And then, so inside of the box, there is, let me just grab it, should come with a power supply I've got here, and it's just in this baggie, so I'll pull it out of the baggie. And then you'll notice that the actual cable of the power supply, it's secured with this twist tie here. If I just hold it up in front of the camera, Yeah, so this twist tie, when you take this off, so I'll just take it off quickly right now, just go ahead and hang on to this here. We're going to be using this later on in the course for kind of like a little bit of a hacky way to attach some of our equipment if you don't want to do soldering. So I suggest you hang on to this. I mean, if you throw it out, you can probably find these. They're easy to find, but just wanted to give you a heads up. Hang on to this. So that's all for this video. I'll see you over in the next one. Welcome, everyone. In this video, we're just going to do a quick reminder about ethical hacking. So if you are familiar with ethical hacking and this isn't your first foray or course, then this is something you're probably familiar with, and this will just be a quick reminder for you. And if you're not familiar with this, then definitely pay attention. So the first thing that I just want to go over or cover is that, of course, you should be following all of your local laws and regulations, and that, nothing in this course is meant to violate any laws or regulations. Of course, they do vary from region to region, so make sure you're aware of your regional laws and regulations, and if you're in doubt about any of it, then those should take precedence over anything in this course. The second point, this is a really important one, is that we should only be testing, practicing, and hacking on your own device. So in this course, we're going to actually be focusing on IoT devices, and we're actually going to be working on real physical IoT devices. We're going to be working on a router, and you should only target your own equipment or equipment that you have permission to test. And this is a really important one because with IoT devices, they're so ubiquitous now. They're all over the place. A lot of times they can have weak security and gaps or things like that in them. And it can be really tempting to even just poke around on other people's IoT devices, either your neighbors or things like that. And you may think that you can easily get away with it, but the consequences for it are very real and they're very big, so it's not worth it. Only test and only work on and only practice on either your own device or one that you have specific permission to be testing on. So the next point I want to talk about is practicing responsible disclosure. So this course actually uses a real-world device for educational purposes, and because of that, I'm not actually going to be showing any specific vulnerabilities on it. We'll just be using it for testing and showing techniques, but we're not going to be showing any vulnerabilities because, of course, I feel like if I were to show any of those on this, then they would need to then be reported and then patched, and the firmware would be out of date already then by the time the course starts. However, if you are to uncover any potential vulnerabilities, either on the device that we're working on in this course, or when you move on, in your IoT and hardware hacking experiences and you work on other devices, then I really encourage you to practice responsible disclosure if you do come across any of those vulnerabilities. And if you're not sure how to do that, then just, do a quick Google search. There's lots of really good videos about how to properly do responsible disclosure. And then just as a final reminder and a catch-all, we should be responsible, ethical, and moral in all of our actions. And I think, those are just three really good things to follow. And, if we follow those, then that's going to cover, most of what we should be doing. So again, just a really quick reminder of how important these topics are and how important they are that you actually follow them throughout this course and in what you do. Thank you for watching this. That wraps up this video. Welcome, everyone, to the first section of this course, Electrical Engineering for Hackers 101. In this section of the course, we'll be taking a look at some of the key fundamental concepts of both electricity and electrical engineering. We're starting out with these theory-based lessons to gain foundational knowledge that will be required to understand the topics and techniques we'll be covering in future lessons on hardware hacking. I've worked my best to condense these lessons into only the most important and relevant topics that I learned during my electrical engineering degree, along with the knowledge I needed on a day-to-day basis as an electrical engineer working with electronics. The lessons in this section and the following 201 section will get more practical as we progress, and we'll have hands-on portions. Before you know it, we'll be directly applying the theory learned in actual hardware hacks. I'm excited to get started, and we'll see you over in the first lesson. Welcome, everyone. Throughout this lesson, we're going to be working to answer the fundamental question, what is electricity, and what are the units that we use to measure and describe it? In order to get started, we need to shrink things down all the way to the atomic level, and we're going to start our example by looking at a carbon atom. At the center of the atom is the nucleus, and the nucleus is made up of two particles, protons and neutrons. Protons are positively charged particles, and neutrons are neutral. The protons and neutrons make up most of the mass of the atom and therefore stay close to the center and the nucleus. The amount of protons an atom has is a fixed number, and this number is actually what determines which element it is. For carbon, which has the elemental number of 6, this means that it has 6 protons. Generally, there will be the same amount of neutrons as protons, however this can differ. The third particle of the atom is the electron. Electrons have a negative charge, and they are much, much lighter than protons and neutrons. As such, they exist around the nucleus, and one way that we can describe how they move around the nucleus is what we call orbits or shells. The negative charge on the electron is attracted to the positive charge of the proton, and this is what keeps it in these shells. This two-dimensional model of the atom with the electrons orbiting in shells is referred to as the Bohr-Rutherford diagram. I've put an asterisk here because I do want to note that this is not actually an entirely accurate model, however it is good enough for the understanding we need. So, these electrons, as we know, exist in these shells that orbit the nucleus, and each shell can hold a specific set amount of electrons. In the first shell, this is 2, and in the second shell, this is 8. Unlike protons that are fixed to the atom, in some circumstances, electrons are able to move from atom to atom, either leaving an atom and joining another, or in the opposite, an atom will pull an electron from another atom. When this happens, the atom becomes what is called an ion. And an ion is a negatively or positively charged atom. It either has a surplus or deficit of electrons. In this example, we have what's called a cation because we have more electrons than protons, and this gives the atom a negative charge. The opposite of this is an anion. In this example, we have more protons than electrons, and this gives the atom a positive charge. This ability of electrons to flow from one atom to another and to also create positively and negatively charged atoms is fundamental for electricity and how we are able to harness it. Let's take a look at how we can harness the flow of these electrons for electricity. We'll start by looking at arguably one of the most common conductors, and that is copper. You'll notice that copper only has one electron in its outer shell. This outer shell is called the valence shell, and the electrons in it are called the valence electrons. Copper's single valence electron is very loosely bonded to its nucleus, and this makes it easy to travel from atom to atom. This makes it what we call an excellent conductor. Atoms with this looser hold on their valence electrons allow them to move freely from one conducting atom to another. If we add a second copper atom closely, we can see that the valence electron can easily move from one copper atom to the other. In fact, in a piece of copper that may have millions to billions of these copper atoms in them, this valence electron just flows freely between all of the atoms. At this point, this does not constitute electricity though, because we just have this random movement. In order to turn this into electricity, we need to be able to control the flow. Let's now take a look at how we can harness this movement of electrons. If we take a look at the cross-section of a copper wire, which could be made up of millions to billions of atoms, we know that each of these atoms has valence electrons that can freely flow from one to the next. If we are able to control this flow and have it move through the wire in a specific direction, then we can have a flow of electricity, or an electrical current. And this electrical current is a stream of charged particles, generally electrons, moving through a conductor, and we measure this in amps. Now you'll notice that I have the arrow for the electric current pointing in the opposite direction of the flow of electrons. This is not a mistake, and we'll chat more on this later. Of course, at rest, we will not have this electrical current or flow of electrons in any meaningful direction. The movement of the electrons will be random. Let's now take a look at how we can control this flow of electrons. In order to move the electrons, we need a force to push them. One great example is a battery. A battery creates a chemical imbalance in electric charges. The fundamental rule of nature that opposites attract will cause the negatively charged surplus electrons to want to flow to the positive side of the battery. We connect a conductor such as a copper wire between these that will facilitate this. This negative charge will push the electrons through the wire. This imbalance of charges is what we call electrical potential difference. And this is the difference in electrical potential between points, and we refer to this as voltage. Commonly, this is a buildup of charge, and we measure this in volts. Now that we understand how we can control this flow of electrons, how can we harness it for power? The movement of an electric charge causes energy to be transferred. If, for example, we just connected this battery with a copper wire, then most, if not all, of this energy will just turn into heat. This is actually a bad example in real life, and you'll most likely just cause a fire. This is what's called a short circuit. However, if we put an electrical component in the way, like a light bulb, then this electrical charge will be transferred into other useful forms of energy, in our example, light. We can describe this flow of charge through the circuit's ability to transfer into other meaningful forms of energy as electric power. The electric power is proportional to both the flow of electrons and the charge imbalance that is pushing them through. As such, the electric power is proportional to the voltage and current. So to calculate power, we just multiply the voltage by the current. Now, power is not to be confused with energy, which is a measurement of the amount of power delivered over time. You remember previously I was chatting about how I had the arrow drawn backwards, and that is because the conventional flow of electricity, or how we refer to it, is actually opposite to the flow of electrons. The convention for the flow of electricity is from positive to negative charges. This may be a little confusing at the start, and the reasoning for this is actually because when electricity was first being discovered, it was thought that electrons flowed from the positive to negative charge. And as such, the convention of drawing circuits with the electrical flow flowing from the positive charge to the negative charge was set as this direction. Later on, it was discovered that electrons flowed in the opposite direction. However, this original convention was kept. In reality, it doesn't actually matter that much, as long as everyone agrees to use the same notation. Of course, way back when we were discovering the atom, we could have just decided that protons would be a negative charge and the electrons would be a positive charge. It is all really relative. The last fundamental concept that we'll discuss now is that of electrical resistance. So we know that the voltage pushes the electrons through a conductor, which causes an electric current. But how much electric current does this voltage create? Of course, we do know that as we increase the voltage, the electrical current increases. The amount of current that flows for a specific voltage is proportional to the resistance of the material that it is flowing through. In copper, we have an excellent conductor and there is very little resistance. Our light bulb, though, for example, has much more resistance than copper, and as such resists the flow of electricity. This resistance of the flow of electricity is what causes most of the voltage to be transferred over the light bulb, and as such, most of the power is transferred into the light bulb as opposed to just being lost as heat in the wire. We call this electrical resistance, and the electrical resistance is the measure of an object's opposition to the flow of electric current. It's the opposite of conductivity, and we measure this in ohms. That wraps up this part of the lesson on our discussion about what electricity is, its fundamental properties, and the units that we use to describe it. We'll pick up in the next lesson talking about what electricity is and using a popular analogy comparing electrical flow to water. I'll see you in the next lesson. Welcome everyone. In this first of 3 videos on electrical engineering fundamentals, we're going to take a look at how we can represent circuits with schematics, what resistors and voltage sources look like in these schematics and in real life, and then we'll wrap up with the very first fundamental law of electrical engineering, Ohm's law. As a very quick recap from our last lesson, some of the key points that we learned about were voltage, which is caused by an imbalance of charge and creates a pushing force for electrons through a circuit. This flow of electrons through a circuit is what we call electrical current, and as this electrical current passes over a resistance, it causes a voltage drop, which is turned into power. The power can be calculated as the current multiplied by the voltage. This pictographic representation of the circuit that we have is not a very efficient one. So let's take a look at how circuits are commonly drawn. Throughout the rest of this lesson, we're going to be drawing our circuits as schematics. Schematics are a visual representation of circuits. A few things to keep in mind about schematics. The wires in schematics are represented by the black lines. These wires are what we call ideal conductors. This means that there is no resistance in them, and therefore the length of these wires does not matter. In fact, schematics are not to scale at all, and they do not actually represent how the circuit is physically laid out. We use many other symbols in schematics to represent different electrical components, and throughout this lesson we're going to be looking at a couple of them. Let's start with how we are representing our voltage. You'll see here how we have V1 representing the voltage, drawn as a symbol with a circle, and then a positive and a negative representing the polarity of each side. A real-life example of this would be a power adapter that plugs into the wall. Here I have pictured the one that comes with our TP-Link router. If you look at it closely, you'll notice that there is an output label, and the output is for 9 volts, and then we have this symbol here, which represents direct current, something that we're going to talk about later, and then we have an amperage rating of 0.6 amps. What this output rating tells us is that this adapter operates at 9 volts, so its output is 9 volts, and then the current we see is not actually the current that's always supplied. This is just a maximum rating, so the maximum current that can be supplied. Now that we know the voltage is 9 volts, let's work at trying to actually figure out the current. The first thing that we need to take a look at in order to do so is actually the resistance. A resistor is represented in a schematic by the squiggly line that's drawn here. In real life, on a circuit, they may look something similar to the picture here, however they come in multiple packages. Resistors are one of the most common electrical components in circuits, as they are essential to how we control the flow of electricity and can divide voltages. For our example here, let's say that our resistor has a resistance of 100 ohms. In order to calculate the current, we'll look at the first fundamental electrical engineering law that we're going to introduce in this lesson, which is Ohm's law. Now, Ohm's law states that the voltage is equal to the current times the resistance. In this case, though, we would like to calculate the current. Using a little bit of simple algebra, we can rework the formula so that it is I equals V divided by R, or current is equal to the voltage divided by the resistance. If we plug in our numbers from the circuit, then we get that the current is equal to 9 volts divided by 100 ohms. Plugging this into our calculator, we'll get that the current is equal to 0.09 amps, or another very common way to write this is as 90 milliamps. Resistors will commonly have a power rating that specifies how much power can safely be dissipated across the resistor. If we surpass this power rating, then the resistor may catch fire. Let's look at how we can calculate the power that is dissipated across this resistor. You'll recall that the power is equal to the current times the voltage, so in our case, this is equal to 90 milliamps times 9 volts, which is equal to 0.81 watts. Welcome everyone. In this second video of Electrical Engineering Fundamentals, we're going to take a look at the second fundamental electrical engineering law, Kirchhoff's voltage law, and then we'll take a look at series circuits. Before we move on to looking at the second fundamental electrical engineering law, a quick reminder on conservation of energy. So because of conservation of energy, this means that we can't actually lose any electrons. So what that means is that the current is equal throughout an entire closed loop. In our circuit here, I've drawn the flow of the current with red, and you'll notice that throughout the whole closed loop, this current is equal throughout the whole thing. The electrons have nowhere to go as they must remain in the conductor, and as such, the flow is equal from one point to another throughout the entire circuit. With this in mind, let's take a look at our second fundamental law of electrical engineering. And that law is Kirchhoff's voltage law. Now, Kirchhoff's voltage law says that the sum of all voltages across a closed loop circuit is equal to 0. And in order to better demonstrate that, I'd like to talk about another schematic element, and that is the idea of circuit nodes. So a circuit node is a point or region on a circuit between two circuit elements. And I'll put one up here on our schematic. So on our schematic, we actually have two nodes. The first one being right here, as we have a joining connection between the positive end of our voltage supply and our resistor. And then the second one being the joining end of the negative side of our voltage supply and the resistor. So what Kirchhoff's voltage law means for this sum of all voltages across a closed loop circuit is zero, is that if we go around this circuit, so you'll notice how I've drawn it here, all of the voltages across this have to equal zero. So if we were to measure the voltage across this 100 ohm resistor, we know, of course, that it's going to equal 9 volts. Now you may be wondering, how does 9 volts plus 9 volts equal 0? Well, in this case, using the convention of a current flowing from positive to negative, when we have a current that flows through a voltage source from this positive to negative, that means that this voltage is an additive voltage, so we are adding 9 volts. Since the resistor is not actually supplying power, rather consuming it, you'll notice that we have the polarity swapped, so this is from positive to negative. As the current flows from a positive to negative, we actually have a voltage drop. So one way to write this would actually be as minus 9 volts. Now, commonly in circuits, you won't actually see these voltages as positive and negative, and instead you will see the voltage source generally labeled as negative to positive, and then elements that consume power, it's just inferred that it's going to be this positive to negative. So one way that we could actually write this or look at it as this is as plus 9 volts, and then this is as minus 9 volts, and it equals to 0, which satisfies Kirchhoff's voltage law. The next concept we'll chat about is that of a series circuit. So in a series circuit, components are connected end to end, one after another, in such a way that they create a single path for current to flow. So you'll notice in our circuit here that we have added an additional resistor, but our resistance still is equal to 100 ohms. And this is because resistances in series can be added together. And as such, our current is still equal. However, our voltage will be divided amongst these two. Using Ohm's law, we can calculate that the first voltage will be equal to 2.7 volts. And then we could either use Kirchhoff's voltage law or Ohm's law to calculate that the next voltage would be 6.3 volts. Of course, our 2.7 volts and 6.3 volts adds up to our 9 volts to satisfy Kirchhoff's voltage law. What happens in our series circuit if we add two voltage sources in series with each other? If we look at Kirchhoff's voltage law, of course we know that this is going to be 18 volts. As our current travels through the circuit in our loop again, when it goes from this minus to positive and this minus to positive, we're going to add 9 volts twice, so we get 18 volts again. Of course, since we've doubled our voltage and our resistance has remained constant, then we know due to Ohm's law that our current will also have doubled. Hello everyone, and welcome to the third and final video on electrical engineering fundamentals. In this video, we're going to take a look at parallel circuits and Kirchhoff's current law. We'll begin the lesson by looking at parallel circuits. Parallel circuits are opposite to a series circuit in that components are connected to each other in such a way that current has more than one path to flow. If we look at our example circuit here, we can see that we have added an additional 100 ohm resistor in parallel. The current that leaves from our voltage source, once it reaches the node here, will be able to be split between the two resistors, with one path flowing through this loop and the other path flowing through the outer loop. Kirchhoff's voltage law still applies to both of these loops, and as such, the voltage drop across the outer resistor will still be 9 volts. If we take a look at the inner resistor, we'll see that the voltage drop is the same as well. For series circuits, you may recall that the current remained the same through both resistors in series, while the voltage was split in proportion to the resistance. For parallel circuits, it is the opposite. The voltage remains constant across both circuits in parallel. However, the current is split in proportion to the resistance. In our example, the resistances are the same, so the current will be split evenly. As our initial current leaving our voltage source splits at this node, this means that we now actually have three currents. I1, which is the one leaving our voltage source, I2, which is the current that travels across the first resistor, and then I3, which is the second current that travels across the outer resistor. The split of these currents brings us to our third and final of the fundamental electrical engineering laws, which is Kirchhoff's current law. And Kirchhoff's current law states that the sum of all currents entering and exiting a node must equal to 0. So in our case, that means that I1 is equal to I2 plus 3. Since I1 is entering this node and I2 and I3 are leaving, we can determine that I1 will have a positive and I2 and I3 will both be negative. Instead of adding resistors in parallel, what happens if we add two voltage sources in parallel? You'll see that we now have I1 and I2 entering the node and I3 exiting it. This means that I1 plus I2 equal I3. Of course, using both Ohm's law and Kirchhoff's voltage law, we can calculate that I3 equals 90 milliamps. As the voltage sources pushing I1 and I2 are both identical, and we have no components for voltage drops between the nodes, we know that I1 and I2 must be identical. This allows us to calculate I1 and I2 as 45 milliamps. If you didn't follow all of the math on this one, that's all right. I just wanted to show here how adding two voltage sources in parallel does not actually increase the voltage. However, it splits the current demand on each voltage source. This is important to remember, especially when using batteries, as we can add multiple batteries in parallel, and this will extend the life of the battery as each one of them has a lower current draw. Now that we have an understanding of Ohm's law, Kirchhoff's voltage law, and Kirchhoff's current law, let's take a look at how we can use all three of them in combination to solve out the currents inside of this example circuit. This is a fairly common practice when designing circuits, as we can choose both voltage sources and resistors from the market or off the shelf that fit our needs. However, depending on the voltage sources and resistance we choose and how we configure them in the circuit, of course, this will change the amount of current. The first step to take when solving our circuit is to label all of our currents in the direction they're flowing in. Of course, we have our main current, I1, that is leaving our voltage source, and this current is split into three separate currents across our parallel resistors. We have I2 traveling over the 100 ohm resistor, I3 traveling over the 30 ohm resistor, and then I4 that is traveling over a 30 ohm and 10 ohm resistor in series. The next step we'll take in solving the circuit is to label out our voltage nodes. What these voltage nodes represent is the voltage difference between the top node and the bottom node. With our currents and voltage nodes labeled, we can start to write out the formulas that will allow us to solve for the currents in the circuit. First, we'll use Kirchhoff's current law to define that I1 is equal to I2 plus I3 plus I4, as we know that the current entering the first node must be split into three separate currents, and that they will all equal the current entering the node. Using Ohm's law, we can calculate that each of the currents, I2, I3, and I4, will be equal to the voltage drop over the resistor divided by the resistance. With that in mind, we can add those into our first equation. We've substituted I2 for V1 divided by 100 ohms, I3 for V2 divided by 30 ohms, and then I4 for V3 divided by 40 ohms. Notice how we have combined the 30 ohm and 10 ohm resistor in series to equal 40 ohms. Next, we can use Kirchhoff's voltage law to solve for our voltage nodes. If we draw our first loop throughout this current, then we can determine that the voltage across this resistor is equal to 9 volts. Another way to look at this is that if we actually just cross out this 9 volts and we look at this minus end as being 0, and then this top end as being 9 volts, This 9 volts actually represents the difference between the two. We then can also write that our node up here is 9 volts, and since we know that this node is connected to the negative end, it's 0 volts. As the current travels in a circle through, so when we travel here from positive to negative, we go from 0 to 9, so plus 9 volts. And then as we travel from this node down to here, we go from 9 to 0, so we go through minus 9 volts. As such, we can say that V1 minus 9 volts equals 0, and of course, if we rearrange that, we can get V1 equals 9 volts. In our scenario here, these top 3 nodes we can think of as identical. We know that the wire in between are actually ideal wires, so there's no voltage drop between V1 or V2, and as such, each of these have to equal 9 volts. Again, if we think of the additional loops, this also satisfies Kirchhoff's voltage law. Because of this, we can set V1 equal to V2 equal to V3. With all the values for our unknown variables accounted for, solving for I1 is as easy as plugging the numbers into our calculator. We can calculate I1 as equal to 9 volts divided by 100 ohms, plus 9 volts divided by 30 ohms, plus 9 volts divided by 40 ohms. If we plug these all in, we'll get that I2 equals 90 milliamps, I3 equals 300 milliamps, and I4 equals 225 milliamps. If we add these all together, we'll get I1 equal to 615 milliamps, which is actually 0.615 amps. For those of you keeping score from our initial look at the voltage source, if this were that same voltage source, then we have actually surpassed the amperage rating or the current rating. So something to keep in mind when we're calculating and designing our circuits. You may have noticed that even for this quite simple and basic circuit, the algebra and math starts to add up. Fortunately for us, there are many great circuit simulation tools that can take care of all these calculations for us, and this is rarely done by hand. However, it is really important to understand the fundamentals of these 3 basic laws and how they work in order for us to set these simulations up. This wraps up our 3-part series on electrical engineering fundamentals. I'll see you in the next lesson. Hey everyone, so we left off at the end of the last lesson chatting about how there's lots of great circuit simulators that can actually do most of these simulations for calculating currents and voltage nodes, and also there's a lot more that they can calculate. And in the past, these simulation softwares were pretty expensive, and realistically you could only get access to them if you work for a company that was going to buy a license. But now there's a few good ones that you can get for free, and this Circuit Lab is one that I just wanted to show everyone quickly. It's pretty cool and it runs right in a browser, so you can get to it from circuitlab.com. And if you want to watch their intro video or get started, feel free to take a look at that. And then if you scroll down, there's some great examples and lessons and things like that. However, I'm just going to jump right in and show you how we can do a quick simulation. And then maybe if you want to take over and play around, that would be awesome. So at the time of recording this, you don't even need a login or anything like that. You can just go right into Launch Circuit Lab, and it's going to open up their simulator right in the browser. And you can just copy everything here. I'm just going to drag and drop, and we'll just delete it all. And I'm going to quickly lay out that last circuit that we were looking at in the previous lesson. So we'll start by grabbing our voltage source that we had. And if we just double click here, we can edit the voltage here and we'll make it 9 volts. And I'm just going to call it V underscore source for the voltage source. All right. And then we'll add in our resistors. So we had our 100 ohm resistor here, and then we had a 30 ohm resistor here. And then we had a 30 ohm and a 10 ohm here. So you just double click on them. You can edit 30 and then 10. So now we just need to add our wires in to close this up. You can just grab a wire here and you just draw the wire by dragging and clicking, which is awesome. You just drag and click. Let's bring these all together. And then the one thing you're always going to have to add for the circuit simulations is we still need a ground because it all works off of reference voltages. So we haven't really talked too much about grounds yet, and we will in upcoming videos, but we need to tie all of our returns to a ground, and this just lets the circuit simulation know that, you know, this negative polarity here, that all this is tied to a zero reference voltage as opposed to it being a floating voltage, and it's going to need that in order to solve it. So if you run a simulation without this ground, it's going to fail. So the last thing we can do is just add some node names so that it makes it a little bit easier for us to know what voltages it's talking about when it's solving. So I'm going to drop in some node names, and we had called this one V1 before, and we'll add one here for V2, and then we'll add a final one here for V3. You'll see if I hover them already, it's telling me what voltage it is, so that is pretty cool. Just like we suspected, so we have, because of KVL, we know that it's going to be 9 volts for all of these reference points. And you may have noticed that actually as soon as I added the ground to the circuit, it satisfied all the conditions for it to run the simulation, and it automatically actually populated all of the currents and powers and voltages. So if we just hover over the nodes, we can actually see all of those details. If we hover here, for example, of course, the voltage is 9 volts, and we can see that then we're 90 milliamps. And if we hover over here, just to give an idea of that voltage drop that I was talking about, we can actually see the 0 volts now as we have that full current drop, but the current remains the same. And then, of course, we can also see the power, which is kind of cool. If we go through to the other nodes, of course, we have 9 volts again, and we can see that second current as 300 milliamps. Over here, if we look at these resistors, of course, we have this 225 milliamps, and then we can also see the voltage drop across each of these resistors. And then if we go down over here, we can see the source at 615 milliamps. This is just a really, really basic example, and honestly, it just scratches the surface of what this software is capable of. And it's pretty cool that we're able to get free access to it. So I'd highly recommend checking it out, hopping in here, creating a few circuits yourself, playing around with it, running some simulations, and experimenting. Hope you enjoyed this quick demo. I will see you over in the next lesson. Welcome everyone to the first lesson on reading schematics. We will pick up again on this topic later on in the course. In this lesson, we're going to be taking a look at the difference between how a circuit may be represented in a schematic versus actually physically laid out. We will also take a look at a couple of practical schematic drawings and how they differ from the theoretical schematics that we've been using so far. I've modified the schematic that we were previously using to add a few new components. So you'll see here that we have replaced our 9-volt power supply with this symbol, which represents a battery, and the longer line is the positive end and the shorter one is the negative. We've also added in 2 LEDs, or light emitting diodes, a red one and a green one. And we've also added in a switch. The symbol here is a switch, and when it's in this position, it represents open, and when it's like this, it represents closed. You may recall in one of the previous lectures that I mentioned how a schematic does not actually represent the physical layout of a circuit. And to demonstrate that, we're going to take a look at what is called a wiring diagram. And a wiring diagram is a pictographic representation of how a circuit is actually physically laid out or wired up. So you'll see in our wiring diagram here, of course, we have our 9-volt battery, and we have this connector to it, which has a positive and negative leads. And our red wire actually represents the positive wire. And, usually wiring diagrams will give like wire lengths and wire colors so that someone can actually build the circuit. The first thing that I'd like to draw your attention to is how we do have this split of parallel circuits that splits here. However, instead of here first going to the red as our inner circle, we actually split up to our switch and go to the green, and that's on the inside. And what I want to show by this is that the ordering of the components, or where they actually are in relation to each other on the schematic, doesn't necessarily represent where they're physically laid out. Of course, the electrical connections still matter, and we have them connected by this node. The second thing I'd like to point out is just the length of the wires. So you see here we have some longer wires, and this may be because if this is fitting, this whole wire up is fitting inside some mechanical case or something, we actually need these wires to be longer so they can route to where they need to go. On a schematic, of course, this does not matter. The other way that we can actually physically lay out circuits is on what's called a PCB, or printed circuit board, and we'll be taking a deeper look at that in the hands-on section once we open up the router. I've switched back our schematic to our voltage source that we are more familiar with, because I want to show a couple of other different items that will happen when we are practically reading a schematic. So the way that we have it drawn here, this is a valid way to draw a schematic. And when you're learning about circuits or electronics, and especially electricity, you'll see the schematic drawn how it is here. Like if you were looking in a textbook, this is a very common way to lay out a circuit when we're teaching. And the reason for that is because when we're talking about those loop currents that we were with Kirchhoff's voltage law and Kirchhoff's currents law, it's very easy to visualize the flow of the circuit. However, when we're actually drawing these schematics out on paper, it starts to take up too much room to show all these return loops and connect, all these wires. So a very common way that you will see schematics laid out is something like this, where we're representing our 9 volts with this line here. And this isn't actually like a wire or anything. It just represents that this is starting at 9 volts. And of course, this is the exact same circuit here. The other thing that I'd like to call out is this notion of ground, which is something that we have not talked about too much yet. And what ground means in these electronic style circuits like this is that this is all 0 volts. So this is just a reference at 0 volts. And we could add a ground here in this schematic, and this would be totally valid, stating that this is all 0 volts. And the reason that you frequently won't see it in this style of representation is, as we were saying before, generally this negative end of the voltage source represents 0 volts, and ground also represents 0 volts. So by us having, all of these tied together, even without the ground, it represents that they're at 0 volts. The last thing on ground here is we can think of all of these grounds. So in a bigger circuit, you will start to see more and more grounds added on. They're all the same point. So it's the same as if we took a wire and connected these together and then had one ground. In order to reduce space and make the schematic a little bit less cluttered, we just connect them all to their own ground as needed. You may also see a schematic like the one on the right laid out like this, where we represent 9 volts with this pin style here, or you might see it like this. So all of those are valid representations. The last thing that we'll take a look at in this first part of reading schematics is what happens when our schematics start to expand bigger and take up more space. You'll see that we start to have wires that need to run over each other. And there's a few ways that this is handled in schematics. The first one is where if we just consider any time the wires touch like this, that actually represents an electrical conductivity. And as such, we cannot cross wires like we did here. So we would use these kind of loop styles to demonstrate that this is not electrical connection, and in fact, this wire is going over. The other style that's much more common in CAD style drawings is you will see anywhere there's actually an electrical connection or interconnection, we'll have this circuit node style connection that you're used to drawing, and then the wire will actually just go straight through the other one. And this does not mean an electrical connection. Lastly, unfortunately, there is not a set specific standard for all schematics, so you will see things differ between schematics. The one important thing when drawing them and also reading them to keep in mind is that they should be uniform or standardized throughout the schematic. So this one is a bad example here where we're using 2 different methods to show interconnection and jumping over wires. Again, we'll pick up more on reading schematics in the next section, but this should give you enough information to get started on the course challenge. I'll see you over there next. Hey everyone, we are nearing the end of the first section of the course, and I just wanted to say great job on making it this far. We've covered topics that include math, science, and engineering, and I know that these are topics that you generally wouldn't find at the start of a hacking course, so great job on persevering and making it through this section. If everything didn't click the first time on these videos, you had to rewatch them a couple times, or even there's still some things that you're not fully understanding, that's okay. These are topics and concepts that took me a while to figure out, and we did cover a lot of the topics and core fundamentals that would be covered in first year electrical engineering courses, and we did those pretty quickly. If you're interested in these topics and you want to learn more, I'd highly encourage you to seek out some other resources on the internet. I really just scratched the surface of these topics because, well, of course, this is a hacking course, and I didn't want to take up all of our time with electrical engineering. I've designed a fun course challenge that takes some of the theory that we've learned and applies it in a practical setting. So let's dive right into the challenge briefing right now and take a look at that challenge. Okay, welcome to the first challenge of the course. Red Team needs your help. Let's take a quick look at the design briefing together. It reads, Operator, we require your immediate assistance. We're performing a covert Red Team operation tomorrow on a sensitive target. One of our field operatives discovered during initial recon that a backdoor at the site is locked using a smart lock and took some pictures of the model. Luckily, we were able to procure some of the locks for testing in our lab. Our hardware team uncovered a transmission output on the board. They were able to capture multiple transmissions and sent them over to our software team for analysis and decoding. They discovered that at startup, the device's bootloader outputs to the transmit pin followed by the results of some initialization scripts. One of those outputs contains a hashed version of the lock's pin combination. Luckily, the lock is using an outdated hashing algorithm that is easily brute forced. This is where we need your help. The software team wrote a script that handles reading output from the pin and brute forcing the hash. They loaded it onto a Raspberry Pi so our field operative only has to open the smart lock and connect one wire from the Pi. He was running through a dry run today on our test locks and uncovered a problem. The Raspberry Pi input-output pins can only handle 3.3 volts, and the smart lock transmits at 5 volts. The hardware team has already left for the day. We need a simple solution to shift the voltage level down from 5 volts to 3.3 volts. Our lab is stocked with pretty much any commercially available standard resistor. Oh, and one other thing. The lock has an anti-tamper setting built in that will stop it from being able to open if it detects any output current from its microcontroller pins above 1 milliamp. Make sure your design won't trip this. The Raspberry Pi I/O has an input resistance of 50 kiloohms. On the next slide, I'm going to give a starter circuit for the solution and a few tips. So if you want to go in and solve this completely on your own, then close the video now and you can check your solution in the next video. However, if you'd like a little bit of a starter circuit and some tips to get started, I'll see you in the next slide. Okay, so here is a starter circuit for us to put our solution in. We have the lock's transmit pin, so TX usually stands for transmit, and then we have the Raspberry Pi receiving pin, and we know that the lock transmits from 0 to 5 volts, and then we need to drop that down to 0 to 3.3 volts. One thing I want to show here is this notation that you will very frequently see where instead of writing 3.3 volts, we'll actually use the symbol for the units instead of the decimal here. And that's just because it makes it less error prone to reading if you miss the decimal, for example, especially in things like resistors. So we will put the unit in the decimal and you will commonly see it written like this. And then also for resistors, you'll just see it as, this K. So 50K means 50 kiloohms. When you're solving for this circuit, I wouldn't really worry too much about this section right here. Just focus on what's here and then focus on getting, your output that we would be able to pull off this at 3.3 volts. And one last tip for you. Don't worry about treating this challenge like it would be a high school or university exam where you're just going to have to sit down with a pen and paper and solve it. I'd encourage you to use whatever resources you would like. So use Google. If you want to use ChatGPT, give that a shot. If you want to use Circuit Lab, then that would be definitely be a valid way to solve this. And also, since we're going for a real life solution using real life components, you won't need to get your solution to be exactly 3.3 volts output. Shoot to get it within 5 to 10% of that. The closer you can, the better, but as long as you're within that 5 to 10%, that's great. Good luck with the challenge. I'll see you over in the next video where I'll show you my solution. Hey everyone, hope you had fun with this little challenge. We're going to go through a solution now. The first thing that I usually do when I get a problem like this where we had a lot of wording is I'm just going to take out the key design components that are required, and I've written them down. So our key design criteria, of course, is that our voltage in, where we're at the lock transmission, is 5 volts. Our voltage out has to be 3.3 volts, and then our current out of our transmission pin has to be less than 1 milliamp. And then finally, we have this limitation that we can only use standard resistors. And we'll chat a little bit more about that later in the solution. So I'm going to be showing how I would approach and solve this, but as long as your solution fits this design criteria, then that is okay. You may have recalled from our previous lecture on series circuits and Kirchhoff's voltage law that when we have two resistors in series, then we actually are able to split that voltage across the two of them, or as some may call it, divide that voltage. And this is a very common circuit called a voltage divider. So if we're not familiar with those though, what I would suggest and what I would do is I would just go hop over to Google and look that up. So let's hop over to the browser. Just going to hop over to trusty Google here. The first thing I'm going to look up is just a voltage divider. And we'll take a look at trusty Wikipedia here. Perfect. So we're already seeing we got a voltage divider, and if we want to read a little bit about it, we can do so. And then we can also see the mathematical proof here for it if you're interested in seeing that. But we moved on to the engineering solution. So I'm just going to take a straight look at the engineering solution. And when I see this little circuit here, this looks exactly like what we need. We have a voltage in, we are just using resistors, and then we have a V out. And if we look over here at the formula, we even get this handy dandy formula here that just says V out over V in equals R2 over R1 plus R2. And we already know V out and V in, so we can just grab this and steal it and solve for R2 and R1, and we'll be able to finish our circuit. So we saw from that Wikipedia page, the layout of that voltage divider will fit exactly as we need. So I'm just going to grab it and steal it. What we've done here is very common, taking a specific circuit element or a few portions of a circuit in kind of like a block format and then using that in our own designs. And this is very common in circuit design. It's something to keep in mind when you're either building a circuit or reading a circuit, is that we don't necessarily have to reinvent the wheel. There is lots of various circuits that perform a specific small function that we can then add together, as building blocks to a bigger circuit to accomplish a bigger overall goal. If you're familiar with programming at all, this is kind of similar in that we would use, libraries and pre-built functions, and we would combine all of these together. And our job as the programmer is not to reinvent the wheel and rewrite all these libraries and functions. We just kind of have to do the in-between code that links all of them together. And that's the same in circuits. With that being said, we've taken our voltage divider here and dropped it in, and we know the voltages. We just have to solve for R1 and R2. So what I would do first is add our current to this circuit, and I'm calling it IM for Imax, and that's the max current that we are able to have coming out of our microcontroller pin from the door lock. And you may recall that that was set at 1 milliamp. Now what I'm going to do is I'll say that yes, it needs to be less than 1 milliamp, but because this is a real life engineering solution, I'm going to set it to 0.75 milliamps, and we'll give ourselves, that 25% headroom there in case we have any extra voltage or anything, a little voltage spike, we don't actually get close to that 1 milliamp. And this is very common when designing circuits, is that you don't want to go right close to the maximum because spikes or things can happen. If we put in our equation that we grabbed from Wikipedia, of course, we have V out over V in equals R2 over R1 plus R2. Since we know the current to simplify that equation, we can use Ohm's law to actually calculate what R1 and R2 are together. So of course, using Ohm's law, reminder that it is V equals IR. In our case, that's going to be 5 volts equals 0.7 milliamps times R1 plus R2. If we rearrange that a little bit, we'll get R1 plus R2 equals 5 volts over, and you'll see here I have written it as 0.00075 amps. So I'm just converting from milliamps to amps because if you're actually doing this in your calculator, these are the actual numbers you would need to punch in if you want to get your resistance in ohms. So we get that R1 plus R2 equals 6.7 kiloohms. And now we can drop that back into our initial voltage divider equation. So I'll just clear the screen quickly here and we can drop that in. Reminder that the initial formula was V out over V in equals R2 divided by R1 plus R2. We can start plugging some numbers in here. So we have 3.3 volts divided by 5 volts equals R2 divided by 6.7 kiloohms. We're substituting there the R1 plus R2 with the 6.7 kiloohms that we calculated. That gives us 0.66 equals R2 divided by 6.7 kiloohms. And if we rearrange that formula, we can solve R2 equals 6.7 kiloohms times 0.66, which is actually equal to 4.4 kiloohms. All right, and we know that R1 plus R2 is 6.7 kiloohms, just a reminder from our calculation before. We can rearrange that, so R1 equals 6.7 kiloohms minus 4.4 kiloohms, which gives us an R1 of 2.3 kiloohms. Perfect, so that gets us very close. These calculations will give us a nice output voltage of 3.3 volts. However, unfortunately, we can't just buy or get whatever resistor values we want very easily. We are limited generally to what's called a list of standard resistors, which are the ones that are actually commonly commercially produced. In order to get a little bit more information on that, let's hop back over to Google. So just a quick tip on these components that come in different values like resistors. You can get tables from the manufacturers. So I'm just going to look up standard resistor table. And if we scroll down here, this one here, they've already looked at, it is from Vishay, which are a manufacturer of a lot of electronic components. So we're going to take a look at their table. And the way that these tables work is they are a logarithmic scale. And the values listed here are in these plus or minus what we call tolerances. So if you look at the values under plus 1%, that means that they're guaranteed that the resistor will be plus or minus 1% of that value. And then the values in here, they can be either in plus or minus 0.5, 0.25, or even 0.1. So you can specify, how exact or precise you need it to be. Of course, the more preciseness you are purchasing, then the more expensive those resistors are going to be. And we see all these values, like you'll see, we only have like 10 ohm, 10.1 ohm. Like, how do we get resistors of different values? If we scroll down to the bottom here, it actually gives us a little bit of a reading about how that does. And it says standard resistance values are obtained from the decade table by multiplying by powers of 10. As an example, 13.3 can represent 13.3 ohms, 133 ohms, 1.33 kiloohms, 13.3 kiloohms, 133 kiloohms, all the way up to 1.33 mega ohms. So the way that works is we can multiply it by 1, and that just gives us the ohms value, and then we can multiply it by 10, we can multiply it by 100, 1,000, and so on. So what we're going to look for then is our first resistance value. We calculated it as needing 2.3 kiloohms. So if we scroll down this table here, perfect. The closest one we can get to is 23.2 here, this 23.2. And if we multiply that by 100, so if I just open up a calculator quickly, and just to show you how this works, if we go 23.2 times 100 Get 2,320, which is equivalent to 2.32 kilo ohms, so pretty close. We can do the same for the other one we were looking for, was that 4.4 kilo ohms. So we scroll down this one here. Perfect. We've got one that's 44.2, and that's the closest we can get. And if we multiply that by 100, we're going to get 4.42 kilo ohms. So you may be wondering that these are a little bit off of our calculations in resistance values, and that is okay. Just like we designed some tolerance into our max current calculation, it's generally safe to assume that other circuit designers are going to add a little bit of tolerance into their circuits as well. So for the Raspberry Pi, this means that our voltage is going to just be off by a little bit, but that will be okay. Now that we've found our standard resistor values, let's hop back over and just make sure that these still work. Okay, so I filled in our resistance values, and just a very quick reminder on our notation here, where we have filled in this 2K32 and 4K42. This K here is representing the point, and we can think of moving it over here. So this is actually 2.32 kilo ohms, and this is 4.42 kilo ohms. So if we just want to really quickly do the math, of course, our current is going to change just a little bit because we have changed those resistances. And using Ohm's law, of course, we can take 5 volts and divide it by the total resistance. And that's going to give us 0.74 milliamps, which we are pretty close to our original one. So we know our voltages are going to be pretty good. Of course, our V out is going to be the voltage in minus the voltage drop over that first resistor. And of course, we can use Ohm's law again. And that gives us, if we wanted to punch into our calculator, this 5 volts minus, of course, again, we have switched back from the milliamps to the amps. If you want a quick way to do this, and the way that I actually think of it in my head, is if the decimal was here and we're going from milliamps to amps, so milli means 1,000, then I literally just, I draw the things, I move the decimal over 3 points, and that's how I do it and think about it in my head. So if we punch in this calculation, we're going to get V out is equal to 3.28 volts, which is close enough to 3.3. That will be perfectly fine for our operation. So the last bit that I want to touch on, just in case anyone's wondering, is, I didn't even really touch this portion of the circuit in our solution. And when I was doing the calculations, and this is a tip I gave you, I said just kind of ignore this part of the circuit for now, and we'll just work on dividing our voltage here. Now, the reasoning for that is if you actually crunch the numbers here, you know that we're supposed to be 3.3 volts all across here. And if you punch that in for the circuitry, you're going to get a magnitude of, I believe, 0.06 milliamps. So we're talking much, much smaller than the current that we're working with here. And this is by design on these receiving pins for devices because, of course, we want to use as little current as possible. We're not powering anything. We're just reading the voltage. So as little current as we can get away with, we will use. And that's how these are designed, with this really high, what's called input impedance or resistance. Now, if you did actually go back and solve this whole circuit out, taking into account when we hook up across this input pin, of course, that will change this current just a little bit. We'll have an extra little bit of current draw by adding these two resistors in parallel. Even though we're adding a 50 kilo ohm resistor in parallel, it's actually going to make the combined resistance of these two circuits smaller. So if you take the total between these two, it's actually going to be a little bit smaller than this. And of course, that's going to increase our max current just a bit. But luckily, we left a lot of headroom in our calculation, giving ourselves that extra 25%, and that's going to be okay. So just to really quickly show how that would affect the circuit if we do take into account that input resistance, I've added it here. And just to show another very valid way of solving this problem, I've quickly sketched up our circuit in Circuit Lab, and I did drop in those resistance values that we were using. So we check this node, we have 5 volts as expected, and our total current has gone up to 783.6 microamps, which in milliamps would be 0.78. So we're definitely still below our 1 milliamp. Of course, because we've increased that current, we're going to have a little bit more voltage drop over this resistor. If we look at the voltage down here, we can see that it is 3.18 volts, and that is a little bit below our desired 3.3 volts. So if you did take this into account and you were able to find standard resistors that functioned a little bit better in this scenario, then good for you. However, that 3.18 volts is well within the threshold that we would need for a logic shifter. And we're going to talk a lot more about digital communications in further lessons, and it'll make sense why we can be off by that, 0.12 volts. We're only off by about 4%, which is okay. Finally, one other point here, if you use resistance values that are much greater than this, that's okay. And honestly, it may even be a better solution because we're going to reduce our overall current draw, which of course is going to lower the amount of power that we're pulling from the smart lock. So that actually may be a better design. I just went with the lowest number that was underneath our max current. That gave us a little bit of threshold, but you could even increase these even more as long as you use standard resistance values if you wanted. As long as you're getting that 3.3 volts here, then that would be a valid design solution. If you got the solution, great job. That's it for this first section of the course, and I'll see you over in the next section where we're going to start with some hands-on. I hope you're enjoying the course so far. A really quick reminder to make sure you are subscribed to my YouTube channel, which is linked down below, and also make sure you are subscribed to the TCM YouTube channel where you're watching this right now. We're almost at 1 million subscribers as I'm recording this. It would be great to hit that mark. So if you are enjoying this video and you've watched to this point, it would really help us if you could subscribe. Hello everyone, and welcome to the second section of the course where we're going to be doing some hands-on testing and a little bit of hands-on lab work with some of our equipment and the router that we're going to be targeting. Before we dive into these hands-on portions though, I want to do a very quick and very important lesson on electrical lab safety and some of the dangers of working with electricity. As I'm sure everyone watching this is aware that electricity can be very dangerous and can also be deadly. However, the things that we're going to be working on in this lab and the testing that we're going to be doing can all be done extremely safely. And in order to do that, we just have to follow a few very simple rules. So the first rule, and if you're only going to listen to one or follow one, is this is the most very important one, and that is that we're only going to work on low voltage. So what does that mean by low voltage? Well, a good rule of thumb is generally to stick below 30 volts DC. That's a pretty common standard for what's considered to be the threshold of low voltage and safe voltage to work at without further proper training on how to handle high voltage. So that means that we're not going to be working on anything with the wiring or the outlets or anything like that from our household. In North America, our household voltage is 120 volts, and depending on where you are in the world, that may differ. You might even be up to 240 volts or 220 volts. So all of that is outside of that safe range. So we're not going to be touching any of this stuff. We're going to leave that to the electricians, all the wiring behind it. And that also includes anything that we plug into it. So in our lab, we're going to be using the power supply that comes with our router. And of course, when we plug it in at this end, it's 120 volts, and then it gets stepped down to 9 volts for us that we're going to work with. But since this whole thing plugs into the wall, that's all we're going to do with it. We're just going to plug it into the wall and into the router. We're not going to open this up. We're not going to do any testing on it. We're not going to modify it. We're not going to alter it. Also, if we do come across a power supply that we're using, it has been modified or altered, or we see that it's damaged, we shouldn't use that. And in addition to that, we should only be using the power supplies that are rated for the equipment that we're using. And the best bet to make sure you're doing this is to use the power supply that was included with the equipment. So just a really quick demonstration of why it's so important for us to leave these higher voltages to the pros. I just want to go over a chart here that shows some of the effects of electrical current on the body. And when we see this current, so this is not like the supply current that the circuit can actually supply. This is, if we were to shock ourselves, this is the actual current that would run through our body. So you'll see even at 1 milliamp, which is a fairly small current level, we'll start to be able to notice a slight tingle. Even at 10 to 20 milliamps, this is where we'll lose the our ability to let go. So if you were to grab a wire or something like that and you were getting electric shock, the current is actually strong enough that it will cause the muscles to contract and we can't let go, which can actually be quite dangerous. If we aren't able to let go, we'll be continue to receiving that shock. At 30 milliamps, breathing can become difficulty and we start getting the increased possibility of death. And then once we get to even 100 milliamps, so this 100 to 300 milliamps is when ventricular fibrillation happens. So this is when the electrical signal through our body actually is able to shut off our heart. So like very dangerous and likely fatal. And then above these levels, you're going to get into like really severe burns and lots of nasty stuff. So as I mentioned before, this current though is the actual current through the body. Now we know from our previous lectures, of course, that the current is dependent on two things, the voltage and then the resistance. So in our case, we can control the voltage. That's why we're only going to be working on these low voltage levels. And then the other thing that we do have working in our advantage is, especially at lower voltage levels, the body has a very high resistance level. So just to demonstrate that, I want to show like a really bad stick drawing I have here of our little demo person. We'll call him Bob. And Bob was working and he was working overhead. So maybe he made contact with his hand to a live wire that he was working on overhead. And then he had his other hand touching maybe a ladder or a railing or something metal. So he's created a path for the electricity to travel through his body and to ground. Now we'll say in this scenario, Bob has, dry, clean hands without any sores or anything like that on his hands. And under that scenario, the resistance of the human body and the skin in particular is very high. So 100 kilo ohms is a pretty good estimate for dry, undamaged skin. And if we do the really quick math for this using Ohm's law, of course, the current is equal to the voltage divided by the resistance. We get 9 volts over 100,000 ohms, which we get 0.09 milliamps. So Bob wouldn't even feel this one. And that's because we're working with a low voltage level. And also we have this dry, clean hands. However, if we just change this up a little bit, so a more likely scenario, if he's working at his home or something like that, we have now 120 volts. So also we'll say that his hands are sweaty because it's been hot and he's been working. And under these conditions, the resistance of the skin is actually much, much lower. And we'll estimate for this case that it's down to 1 kilo ohm, but it can even get lower than this. So if we re-crunch these numbers now under these circumstances, we can see that we're actually already up to 120 milliamps. So we're well within this fatal zone. And that's why it's so incredibly important for us to leave these higher voltages to the pros and only work on the lower voltages. In this course, we're just going to be working generally around 9 volts, which is what comes out of our power supply. We're not going to be working with that power supply at all. We will plug the power supply into the wall, and then we'll plug the power supply into the router, and we will be working only on the router. The second rule that is just a really, really good habit to get into is that we're only going to power on circuits when required. So if we need to test them, then we'll power them on and then we'll power them off. And if we don't need to actually, be doing any testing that requires a circuit to be on or any work that requires a circuit to be on, then we'll just power the circuit off. So at some points in this course, we're going to have to connect things. We're going to be visually inspecting the board. And at those points, there's no reason for us to have the board on or the router powered on. So we will power it off. And the best way to make sure that you actually have it powered off is we will just physically unplug the power source. So in our case, it is this brick power supply. We're going to unplug that right from the router. Our router doesn't have an on-off switch, but some devices do. Even when they do have an on-off switch, in my opinion, best practice is just to remove the power supply, and then there's no chance of accidentally having any electricity coming through to what you're working on. And this is just a really, really good habit to get into when working with any type of electricity. It can prevent you from getting a shock and also can prevent you from damaging the board. So I always get in the habit, I'm done working with it, turn it off. If I don't need it turned on, I don't even turn it on. Okay, the third rule, a really quick one, is that we're going to remove any jewelry. We're talking about how the resistance of the human body is quite high, so that helps us to prevent from getting these damaging electric shocks because we keep the current low due to that high resistance. Of course, metallic jewelry is a very good conductor generally, so it can actually carry quite a bit of current. And what can happen if you make contact with any jewelry, even at lower voltages, it doesn't increase our chance of a shock because that resistance is still high on our skin, but the jewelry can heat up quite hot and you could burn yourself, or you can make a spark or something that is a distraction to you and causes you to do something else that would be dangerous, like swing your hand away and hit it on something. So good rule of thumb, really when you're working on anything, but especially electronics, we should remove any jewelry. Okay, and then the last rule that I want to chat about, which is not as applicable for this course, but just in case you're going to go and take what you learned in this course and work on other electronics. And that rule is to be mindful of capacitors. So we haven't chatted too much about capacitors yet, and we will talk about them much more in detail in the 201 section of electrical engineering for hackers. But just a quick rundown on capacitors. They are able to store an electric charge on a circuit, kind of in a similar short-term way that a battery would do. And they're actually able to build up a much more powerful charge over time and then dissipate that very quickly. And with larger capacitors, like some of the ones that are shown here, they can actually be at a much higher voltage than the rest of the circuit operates at, and they can pack a pretty good punch. So if you're not careful with these guys, you can get a good shock and actually at levels that could possibly be dangerous. The other last really important thing to keep in mind with capacitors is that they are able to store charges, and some of these capacitors can actually hold onto a charge for a pretty decent amount of time. So this means that even if you're following rule number 2 and we've powered the circuit off completely, you've removed the power supply, the capacitors can still hold a charge for a pretty good amount of time. Good circuit designs will have ways to dissipate this over time. However, you don't want to trust that someone has put this in. So we always want to be mindful of discharging these capacitors. How to do that is a little bit outside of the scope of this course, since we're not actually going to be working with any capacitors that are at that dangerous level. So if you do encounter these large capacitors when you're working on something, even in TVs or power supplies for computers or things like that, be very careful of them and maybe do a little bit more further research or learning before you actually dig into using them. Again, in this course on the router that we're using, there's not going to be any that are at that high dangerous level, but I just wanted to make sure everyone was aware of that. So that wraps up this quick lesson on safety. I will see you over in the next lesson where we're actually going to start getting our hands dirty and do some hands-on. Hey everyone, welcome to this first hands-on lesson of the course. If you've just unboxed your router, one really quick reminder to hang on to the plastic twist tie here that I have. It's what holds the power supply together, and we're going to be using this guy later on in the course for a little bit of a hack to get a connector connected without soldering. So make sure to hang on to this, just set it off to the side and hang on to it. So in this lesson, we're going to be taking a look at our TP-Link router. That's going to be the target that we are hacking on and doing testing on throughout the course. Now, the one that I'm working with and the model that we're going to be using throughout this, if you just want to double check, it is a TLWR841N. And I've chosen this model to be our target for a couple reasons. One of the main ones is it's very cheap at about $20. And it also has a lot of what some people will call features, other people would call security misconfigurations that can help us to learn about hardware hacking and some of the things that we can take advantage of. Now, in order for us to get access to most of these hardware hacks or any of the testing, we're actually going to have to open this device up. So we're going to be in this video taking a look at how we can do that. In order to do so, we are going to need a couple of tools. So one of them is going to be a Phillips screwdriver. I've just got a set here of small screwdrivers, which includes a Phillips screwdriver. And then we're also going to need something to pry this open. So I've got two here, what are called spudging tools, and they are used to pry open electronic devices like this. Now, you'll see this in many electronic devices where it uses what's called a pressure fit to snap together. So this one's got a couple screws in the back, and I'll just flip it over to show you that right now. So we've got 2 screws here in the back, and once we take out these screws though, it's still not going to come apart. It's actually going to be held together pretty tightly. And the reason for that is most of new electronic devices these days use this pressure fit. So even things like your phone, if you've ever had to take that apart to get your battery out, or laptops, they use this pressure fit. And these spudging tools are specifically designed to open that. The nice thing about them is they are also not conductive, so we don't have to worry about any type of shock discharging into our components or shorting anything. Pick these ones up off Amazon for pretty cheap, but if you don't have any or don't have access to them, you can use a small flathead screwdriver. So I've got one right here. The only thing with these is to keep in mind they are metal, so we don't want to make sure we're not shorting any of the circuits. So try and be careful when we are using them, not to insert them too far into the router themselves. Okay, with that out of the way, let's take a look at how we can open up this router. So the first thing to do is just to pop these screws out. So I'm going to do that right now. If you haven't done so already, also, these antennas just fold down. It's much easier to work with them if you fold them crisscross like I have here. And we'll just take these screws out. So even with these screws taken out, you'll see the router is still actually together pretty strong. Even though I'm pulling on it with my hands, I can't quite get it open. So this is where that spudger tool comes in handy. On this router specifically, I find it's easiest to, if I just move these antennas out of the way for a second, it's easiest to get started. We can kind of slide in here with your tool and pry open. So that's where I am going to start on mine. And if you just get the tool in and just give it a little pry, you can see mine has popped right open, and I still have it. It's a little bit stuck on the ends. Here, I'll flip it up so you guys can see. Still stuck here on the end, so this is where this tool comes in handy. You can just try and pry along. If I just use my hands a little bit, we can just work it along the edges. I'm going to come back to this side here. There we go. Okay, so the one thing you will notice when you're doing this, and you may have heard it there on camera, is we do get some kind of snapping, and it does sound like it is breaking a little bit. That is to be expected when you are working on these pressure fits. That snapping is okay. You'll notice like nothing on here actually broke. I've got no broken plastic, and if I wanted to, I could just snap this back together by just pushing it back together. Just going to set this out of the way here. All right, so we now have our router open, and we can start taking a look at working on the internals. I'm going to pause this video here, and we'll pick up in the next one where we start taking a look at the internals, and we'll also chat about how to safely handle electronics and make sure that we don't have any electrostatic discharge. That wraps up this video. I will see you over in the next one. Welcome everyone. So before we start actually touching and handling and testing our router and the internals of it, I do just want to chat a little bit about electrostatic discharge and how we can safely handle the electronics and the PCB. So I'm sure that everyone watching this video has at some point in their life walked across a carpet or some other surface and then touched a doorknob or another metal object and received an electric shock. And while these shocks are not harmful at all to humans, while they may be a little jolting or surprising, they're not actually harmful to us. They can actually be very harmful to electronics, and in particular, the kind of very small electronics that we see on these circuit boards. Now, the reason for that is with an electric shock, you can actually get up to easily 5,000 volts or more. The reason they're not dangerous to humans is, of course, it's for a very, very, very short amount of time. So the amount of energy dissipated is extremely low. The reason this isn't harmful to humans is that it's for such a short period of time, and our large bodies are easily able to just dissipate any of the charge that would come from that. However, for small components, if I just grab my pointer, like some of the ones on this board here, like the chips or the other, it's even really hard to see small componentry on here. They're so tiny that this large charge across them can actually do quite a bit of damage. And the one really concerning thing with electrostatic discharge or shocking these components is that a lot of times the damage won't be noticeable right at the start and everything will function as is. However, we've weakened that component to the point where it's going to fail later on. And this can be a nightmare from a quality assurance standpoint, especially if we're working in a production environment or we're doing testing on a board for a potential customer or something like that. We want to make sure that we're not accidentally introducing this damage to the board, because then we're not entirely sure if it's something that we did legitimately with our testing or if it's from this electrostatic discharge. So if you're working in a professional setting, depending on where you're working, there's going to be a set of measures that you're probably going to have to follow for electrostatic discharge and to make sure that that doesn't happen. And I just want to go over some of those so that everyone is aware. And then when you're working at home, you can kind of make your own risk assessment about which ones you're going to follow. You know, one of the nice things in this course is the router that we're working on is relatively cheap. It's only $20. So if we do damage it, then it is easy to replace. And, you know, in this scenario, we're not actually working on a customer's component. So ultimately, it is up to you to decide how many ESD precautions you want to take. These are not like a safety precaution for ourselves or injuring ourselves. They are to stop us from damaging the board and our equipment. All right, so the first thing that I'm doing here is I'm actually working on this ESD mat. So the way that this works is it's very insulating. It's made of rubber and it has an extremely high surface resistance. So that's going to help dissipate any electric shock, because of course it's going to be hard for there to be a path to ground. Another thing that we can do before we start working is we can make sure to dissipate any charge on our body. So what I have done is, near me, I have a doorknob that's just off camera that I touched before I start working. So if you have anything similar near you, a doorknob or like maybe a metal bed frame or anything like that, you can make sure that you've dissipated any of your charge. The other thing that we can do that is free is make sure that when we're handling the board, we're not actually touching any of the components unless we absolutely need to. So if I were going to pick up this board, then I would do so from the edges and just touching the edges like so. I wouldn't like actually go and directly touch any of the components, because that can relate to a shock going straight into the component. That's why, like, when I need to point out to them, I am using this tool that is non-conductive so that there is no chance of dissipating shock. Okay, so the other things that I'm going to show here are stuff that's going to cost money, and I'm not going to be using them all because I personally feel like it's a little bit overkill for this, but I just wanted to demonstrate in case you are ever in a professional environment, you'll probably need to use those. So the first one is something that you've probably seen, and that is these ESD bags. So these bags are non-conductive, they're highly resistant, and when we're transferring or moving electronics, then we should put them in these bags because it stops any electric shocks from dissipating throughout them. So these are great for that. You've probably seen them if you've ever bought like any electronic components, they come in these bags. The other thing that you will commonly see in a professional setting is a way to actually keep yourself grounded. And I'm just going to show you one way that you can do that. So I have a power bar that's mounted that I'm using for power. It's just right here. And on this power bar, of course, this little pin here, this is just a straight connection to ground. So that's generally done for safety reasons. If we have a short circuit or anything like that, all the power will go straight to ground. And this plug that I have here, it's only got one prong and it only just fits into the ground. So I'm going to plug that guy in here, and then it's going to give us access here. I got it plugged in. I'll just set that here. It's going to give us access to two ground connections. So what I have here is a wristband, and this is a metallic, like it's got metallic conductive material in here, and it's got this alligator clip here that I can pull off. So this plugs into one of these guys, and then I can just put this wrist strap on. All right, so you just wear it on your wrist like that. And then what this does is this makes sure that I'm not actually going to be able to build up any charge because I am constantly grounded. So there's almost like a zero resistance path for any charge to go. And it's going to take the path of least resistance. So instead of, shocking anything, it's going to go through to ground. All right, so I'm just going to take this off because it's a little hard to film with, and I'm not going to be using this because I think it's a little overkill for this lesson. But if you're in a professional setting, like when I used to work on electronics in a professional setting, I would wear one of these. All right, and then the last thing that you can do is that we actually can ground the work area that we're working on as well. So I've got another one of these clips right here, and we've got this that plugs in on the one end, and then it's got this alligator clip here. So I'm just going to clip it onto the side of this mat. And then even though this is set to be like a really bad conductor, and it's very, very highly resistive, just in case, we can also ground this to make sure that there's no chance of any electrical charge dissipating. It will go straight to ground. Okay, so I just plugged that in again. I'll show you into my power bar that's here. So now, if I'm wearing this, I'll just put this back on again quickly. All right, so if I'm wearing this, now we can see that I'm grounded and the area that we're working on is grounded. So it's almost impossible for us to have any sort of electrostatic discharge. The last thing that you'll see in a professional environment is something that I have had in working areas as well, is there will also be special flooring that is very, very conductive so that it makes a good path to ground. And you'll wear special shoes that are ESD protective shoes, and they will also make sure to ground you. So I then have 3 points of grounding, and it's very unlikely that we're going to have any sort of ESD. Now, these last three things where we're using, the grounding of the mat and the grounding of the wrist strap, and obviously no one's going to have this at their home, but the grounding through the shoes are great for production environments, and we want to be absolutely sure we're not going to do any damage. However, for the home stuff, I would just suggest to sticking with the, touching only the PCB by the edges and trying to avoid actually physically touching any of the components themselves. And I also do just ground myself on something metal because it's very easy to do before I work with it. That being said, if I was working on something like my personal laptop or maybe my phone or something that was worth a lot more money, then maybe it's good practice to follow these. So I will leave that up to you as the viewer to choose which options you're going to use for ESD protection. With that being said, we can now move on to our first testing and taking a look at the PCB. So we'll wrap that up for this lesson, and I'll see you over the next one.
Welcome everyone to this lesson on PCBs. So if you're not already aware, PCB stands for printed circuit board, and in the internals of our router, that is this green board here. Now you hear PCB used interchangeably to reference both just the bare board, so that is just this green portion of the board, and then also what is called the PCB assembly, which is actually the bare board, then with all of the components that are soldered and attached to the board. So generally, when people are talking about PCB, they'll use it interchangeably, and they'll just call it the board or PCB, and most frequently that will refer to the actual whole board itself, including all of the components on it. I'm going to move our target router to the side here and show you an example of just a bare board so that we can look at some of the features of it. So this is called a helping hand. It's just good for holding electronics in place. I'm going to use it just to hold this board a little bit closer to the camera. All right, so the PCB has two main functions. The first one is that it holds all of the components in place, and it does that by, we have these items here, so here and here and here, and there's many of them on the board, and these are called pads. And the components like the resistors and the chips all get soldered to these pads, and that helps hold them in place. So on this PCB, we actually have two different types of pads. The first one, example is right here, and these are called through hole. And the reason for that is these are actually a hole on the board that have a metal ring of conductive material, and the components actually go through this hole and then are soldered in place. So you can see, I don't know if you can see, I can actually poke through it here. The second type of pad that we have are these, an example right here. So we have many of these ones as well. And there's no hole here. We just have a metal rectangle of conductive material. And the components don't have any leads. They just get soldered directly onto these pads. And that's called a surface mount pad because the components are directly surface mounted on there. So I'll just flash up on the screen here quickly to show you an example. On the left here, I have an example of a through-hole resistor. These metal wires on the sides of it here are called the leads. And you can see here an example of it on the board. So the leads will actually fold. These would be holes that they would slot through. So you can see some examples of those holes right here. You push the leads through the holes and then they get soldered in place. That's why it's called through-hole. And then on the right-hand side, this is an example of a surface mount resistor. Instead of leads, we just have these metal edges that are on the sides of it. You can see here on the board, they actually just fit onto those pads that we were showing and they get soldered into place that way, and there's no holes or anything. In commercial boards these days, you're going to be much more likely to see mostly surface mount components, and there's many reasons for that. One, they can be made much, much, much smaller. You will see that on the actual router board. And then second, it's much easier to automate the process of creating these boards. We can have machines much more easily drop these into place instead of having to bend the leads and push them through the holes. And we'll take a closer look on our target PCB of the router as well at how those look. The second function of the PCB is that it actually electrically connects all of the components together to form the actual circuit. And the way that it does that is with these green lines that you can see drawn on here. So these are what are called traces, and they are electrically conductive, and they perform the function of wires on the PCB. For us as hardware hackers, this is quite important because we can actually start to visually inspect the PCB and try and figure out what the circuit is doing and where the signals are routing on the actual PCB. One thing that does make this tricky though is that modern PCBs now have many layers to them. So of course with these traces, for example, like these ones, we're not actually able to route through them. So if we wanted to cross through here, for example, we cannot route through these traces. So what we have done in modern PCBs is we actually make them multi-layer. And that way we can have traces buried in the middle of the PCB, and we can also have traces and components on the back. So I'm just going to quickly flip this one over to show you how that looks. Okay, so looking at the back of this PCB, you can see that we actually have some traces that are just visible on the back that are connecting some of our pads. And we also, for example, here, this F1, this is a fuse, so we can see that it actually is only on the back as well. And then the last thing that I want to show here that is really important and unfortunately makes our lives kind of tricky as reverse engineers is we can see that we have this D1 here, so diode 1. And you can just make out the traces here, but they don't seem to go anywhere. They just go to these very tiny metal holes that are not actually through hole pads. And if I just flip the PCB back over, so if you just keep in mind where this is on the PCB, so when I flip it over, you can see now this is where that was, and there's no traces or signs of anything, and we only just have these two metal holes here. So what these are called is they're called vias. And vias we can think of as traces that go between the layers. So they actually take the trace and then they transport that electrical signal. So these have conductivity and then they go to layers. So on this PCB, that diode's traces, they actually go up and only into the middle layer of this, which we're not able to see. So that does make it a little bit more challenging for us to reverse engineer. However, there are ways that we can get away from this. So just to demonstrate what the vias look like, I'm going to pop up on the screen here a quick image and chat about them briefly so you can see in 3D what they look like. On the left here, I have a sample PCB where we can see in the top we've got the assembly, and then on the bottom, just to show what it would look like without the components soldered on, we can see just the bare board with the pads. Now on this board, we have some vias as well, so we've got a few vias here, and you can see what those look like on the bare board. So what this would look like if we just do a break apart of this into kind of a 3D look. I've done a drawing. These aren't actually like all of the traces that you'd see on this PCB, but just to give you an idea, the vias run down between the traces. So there's an actual like metal connection, like metal pipe, you can also almost think of it. And it brings those connections from one layer down to the other, and then we can route these circuits. So this one I've drawn with 3, but we can get many, many more layers in actual production PCBs. Okay, so we're back here with the target router PCB, and I'm just going to lift it out of this bottom part of the enclosure. So it can just lift right out. There's nothing that's actually holding it in. It's just resting on a couple of pegs here. All right, so I'm just going to lift it out. And then the only thing that's actually attaching it is these wires, which go to the antennas. So if we're just gentle, we can lift it out though to work on it. And what I'm going to do is I'm just going to quickly put it on the helping hand so that we can get a closer look at the PCB itself. So unfortunately, our target PCB is a little bit more complex than the one we were just looking at. But in case you're getting intimidated by taking a look at this, do not worry. We don't actually need to know everything about this or how it works. There's just a few key points that we're going to start taking a look at and learning to identify that are going to help us along our journey with hardware hacking. Now, the couple things I just wanted to show here are on this board, we are mostly surface mount components. And they are so tiny on this board that it is actually very hard to even see some of them. Even on this 1080p camera, it's hard to get them in focus. Of course, so we've got our chips here, and they are surface mount. They just rest on top. And then they're very hard to see, but all of these little items here are actually components. So we've got capacitors, resistors, all tucked in there in their little surface mount packages. Here's a couple that are bigger. And it's really, really hard to show these because they're so small. I'll just put my finger in for reference so you can see. Like, I could fit almost all of them on the tip of my finger here. Now, we do have a couple through-hole components. So we've got these LEDs here that are through-hole, and then our capacitor that's through-hole. And generally things like, your push buttons and these Ethernet ports are also through-hole. And the reason for that is one of the advantages of through-hole components is they actually hold things in place much better. So for bigger items that might be able to get bumped, or we're going to be plugging them in and out, you'll usually see through-hole used. And I'll just quickly flip the board over so you can see what that looks like on the back. So you can see on the back of this is actually where these components, their leads stick through, and they are actually soldered through those through-holes. That wraps up this first look at PCBs. I'll see you over in the next lesson where we're going to break out our multimeter and start doing some testing on our PCB. Welcome everyone to this video where we're going to be chatting about digital multimeters. I've got the one here that we're going to be using in the course, and in this video we're going to be taking a look at it. So digital multimeters are arguably one of the most important tools in both an electrical engineer and hardware hacker's toolkit. And the reason for that is they are kind of like a Swiss Army knife. They're called a multimeter because they actually perform the function of what used to be multiple meters. So in order to measure voltage in the past, we used to use what was called a voltmeter. And to measure current or amps, we use what was called an ammeter. And then to measure resistance or ohms, we would use what's called an ohm meter. So these digital multimeters are able to combine all of those measurements plus a couple other functions that we're going to chat about in this video. So this meter that we're using in this course, I've selected because it is relatively inexpensive while still being quite accurate and having some great features to it. And it has all the features that we're going to need for this course. The one thing that it doesn't have, which you will start to see on more expensive meters, is what's called either auto ranging or auto scaling. So what that means in that we don't have this auto ranging or auto scaling is that we actually have to pick the scale that we want to measure on. So I'm just going to pick this up to show an example of it. All right, so if we take a look, for example, here, we can see how we can make the ammeter measurements. So this A symbol stands for the ammeter, and then we already know that this symbol here is for direct current. And if we want to make a measurement, for example, that is in the 0 to 2000 microamp range, then we can use this one. And then if we're going above that 2000 microamps and we're at this 20 milliamps or below, so between this 2000 microamps and 20 milliamps, then we would use this measurement, and then so on all the way up to the 10 amps. So same thing down here, we have the ohm symbol. So this is where we can use it in the ohm meter mode to measure resistance. And we can measure the resistance all the way from 1 ohm up to 200 ohms here, from 200 ohms to 2 kilo ohms, and then all the way up to the 200 mega ohms. Okay, so for voltage, we are up here, and this is the symbol for volts DC. Again, same idea with those ranges. And then finally, I'll just show you here this symbol and these two measurements. So these are for measuring the volts in alternating current, and we're not going to be touching those in this lesson, so no need to use it. So to make measurements with our multimeter, we are of course going to need probes, and these are what are called the probes, or sometimes people call them leads. And the way that these work is we're able to press these metal leads onto the components or wherever doing our testing, and we can make a measurement. And then of course the other end of them, so these ends actually plug into our meter. The first one that plugs in, and you guys can do this if you're following along, is the black one goes into this one, which is labeled COM, and that COM stands for common ground. So this is where the ground goes, and of course our black is going to be that. So I'll just plug it in right now. All right. And now you will see that we do have two areas where we can plug in the red one. And if we look at the first one, it says here, volts, ohms, milliamps, and then this squiggly line, which is for our function generator, which is another feature that this multimeter has. And that's where we're going to be using it for this course. However, just so you're aware of why we then have one here that says it's for measuring 10 amp max. The reason for that is we see here it says fused. So internally on this multimeter, there is what is called a fuse. And what the fuse does is it protects the internal circuitry from if we measure a current or something that's going to put a current too high through the internal circuitry, and it would damage that. Instead, we have the fuse in line. And when that current that's too high goes through the fuse, it will burn out the fuse and stop the current from flowing. And the fuses are really cheap. It's easy to replace them, so we don't actually break our internal circuit or burn it out. Now, the fuse for this one is fused to allow the milliamps. So we can see here, if you take a look closely, this one is fused at 500 volts max or 500 milliamps. So for everything in this course, that's going to be perfectly fine for us. However, if you were, doing this 10 amp current reading here on the ammeter section, you would need to unplug from here and plug into this one. And then we get access to that bigger fuse that's going to allow that measurement. Again, we're not going to be working with anything that high in this course, so we don't need to do that. We can just plug it into this one. I'm going to do that right now. Plug the red one. All right, and then you can just leave it in these two for the rest of the course. That's all we'll need. There's two other features that I want to show on the front of this. So we do have a light here. Now, if I just turn it on here, and then if we push this, then we get a light that lights up. The other thing that we have is this button, which is a hold. So if you're taking a measurement and you just want to not have to write that down or remember it for a second, if you push this hold button, then instead of measuring anymore, it's just going to lock what's on the screen, so you have that saved. Last thing I'll show is on the back, it actually does open up. So internally of this, there's a 9-volt battery, and that's what used to power this. If it does die or it stops working, that's where you replace this. And also the fuses are internal in here. So if you ever blow out a fuse, you can replace it from in here. All right, finally, one last thing. So you might hear the digital multimeter referred to as DMM, that abbreviation for it. And I might say that a few times as well, because it's pretty common to hear that. So I just want to make sure you're aware of that. That wraps up this video, and I'll see you over the next one. Welcome everyone. In this video, we're going to be taking our first measurements with our multimeter on the TP-Link router's board. However, before we get started, with those measurements, I just really want to quickly show you something important and another very important tool, and that is our notebook. So in this course, I'm going to be taking notes in a paper notebook, and this is what I usually do when I'm working on electronics because I may not always have my computer handy, and sometimes I find it very useful to just have a paper notebook because you can also draw circuits or other just quick memos in it. Now, I apologize for my very bad handwriting, but I want to just quickly show you what I have started with writing for notes for so far what we're testing with this TP-Link router. All right, so I've put the target here and I've got the router model number and the name of the manufacturer here. So we have this TP-Link TLWR841N. And then also very importantly, I have the serial number here. And this is important because if we're testing multiple routers or multiple targets of the same one, then we need to identify what the actual one that we are testing on in case we do any damage to it or something happens, we can actually trace back with our testing and see which model and which actual serial number to trace back to that physical piece of equipment. I've also included dates, so I'll be adding these dates in as well so we know when we're doing certain things. And I have the first action wrote down here. So the first thing that we've done is open up the router case with the spudger and visually inspected the PCB. And now as we do more testing, I'm going to be adding these actions and taking notes in here. So feel free to take notes however you would like. If you prefer to take it, in OneNote or Cherry Tree or some other type of digital note-taking app, then go ahead. That's totally acceptable. My preference is just to take these paper notes when I'm doing the measurements. All right, so we'll be coming back to this throughout the course, and then we'll also be visiting these notes when we write up our final report. I'm just going to put this out of the way and then grab the things that we're going to need for taking our first voltage measurements. Okay, so to take our measurements, we are going to need, of course, the router with it opened up because we're going to actually need to be probing internally on the board. We're going to need the router plugged in for this, so we will need the power supply. And then we're also going to, of course, need our multimeter. A quick reminder on safety that we're just going to be plugging in the power supply when we need to, and then we'll unplug it when we don't need it. Just to quickly show you where we're going to be measuring, a lot of times on these boards, if we're measuring the through-hole components, which is what we're going to be starting with, it's actually easier to probe them on the bottom. So I'm just going to flip this over. It just lifts out like this, and then we can flip it over. And if we look at the back, we can see, again, like we identified before, these through-hole components, and that's where we're going to be doing the testing. Now, I'm going to be using what's called a third hand to hold this up, and it's just a little bit easier to film. You don't need to use one if you don't have one. You can just rest it on the router case like this and do the probing as well. So I'm just going to quickly set up that third hand and then we'll jump over to testing. I've got everything set up now, and just to show you before we plug it in, the first measurement we're going to be taking is to verify the input voltage, and this is something that is always good to test before we do any further testing. Now on the router here, we know we have this input jack right here, so right here, and this is where the power supply plugs in, and then it is a through-hole component, and these are the two pins that come through and are soldered, so we can test the voltage by measuring the drop across these two pins. And on this router, I already know this is the positive one and this is the negative one, so we'll put the red lead here and then the black lead here, and that's how we can test, and I'll show you how we can figure that out. All right, so I'm going to get the meter set up first. All right, so since we know that we are at looking around 9 volts, I'm going to set it to this 20 volts DC setting that I have here, and we can use that for measurement. And I think now that we know where we're probing and we have our meter set up, we can plug it in. Okay, so just a little bit out of the shot here, but I can see the lights are starting to light up. Perfect. So I know that we have the power on and we're ready to take our measurement. Move this here so it's just a little bit more visible. And red lead goes to the top one and black lead goes to the bottom one. And we just press it there. All right, and we see it stabilized there at around 9.25, 9.26 volts. All right, so if we had them backwards and we just want to identify what it would look like if it's backwards. If I do put the positive or the red one on the wrong lead, then we'll see that we actually get a negative measurement. So that's how we can tell which one is the positive and which one is the negative. And that's important because on this circuit, all of our return current is going through this negative end, and we can think of that as being the ground. So we'll come back to that later. So to take these voltage measurements, what we did there is we actually connected the digital multimeter in parallel to make these measurements. And just to make that a little bit more easier to read, I'm going to move this third hand out of the way, and I'll show a quick drawing of the circuit. All right, so I've got a drawing here just to quickly illustrate how we're taking that measurement. Now I've got right here a bad drawing of that input jack. We've got the positive and negative leads of it, and then it flows through and into the rest of the circuit. Now what this is called, or how I'm representing this, is a black box equivalent. So we don't care necessarily about what's in that circuit at all. I'm just showing that, you know, the power or the current flows through out of this jack, and then it goes through to that whole rest of the circuit, which we don't care about. Now, in order for us to take the voltage measurement in parallel, what we did is we attached the probes to, if we can think of it, this way, these ends, and took that measurement. And now if I just set these down to kind of illustrate, what we've done when we do that test is the power is able to split. That's why it's in parallel. So our current comes out of the positive end, and it can split at this node, of course, and go through our meter, and then also most, or if not almost all, of the current goes through the router circuit. And that's how we take that measurement in parallel for measuring voltage. When we are measuring voltage with the multimeter, it has what is called a very, very high input resistance. So the resistance internally that's making this measurement is very, very high. And what that does is that it allows us to not affect the rest of the circuit while we're taking that measurement, because we barely take any current to measure that voltage. For voltages, which is what we're going to be probably measuring the most on circuits, it's very easy to do. All we need to do is just find the two leads of the component we want to measure the voltage drop over, and we just touch the red to the positive and the black to the negative, and we'll get our voltage reading. I'm going to take this drawing away and put the router board back on the third hand, and I'll give you a quick challenge to take a measurement on your own. Okay, so at the very top of this board, beside this orange flashing LED, there is a green one that is on constantly. And if you just power it on your board, it does take a few seconds for it to come on constant like that. But what my challenge is, or what you can pause this video now and do, is try to take a voltage measurement of this and make sure you get it to be a positive reading. Just a hint that, of course, the leads that come through, this is a through hole component. So the leads are on the back. You can measure it on the back, or if you want, you can actually measure it on the front. So pause the video here and find out what the voltage drop over that LED is. All right, did you get it? Let's take a quick measurement and see what I get for the reading of that voltage. Again, I've got mine set still on this 20 volts, which is going to be okay for reading this measurement. And I'm just going to touch the two leads here. All right, and I am getting mine at 1.94 volts, which seems about right for this green LED. Again, if you flip these and put it the other way, then you're going to see the same reading or similar reading, but negative. There are a few other areas on this board where you can measure voltages. One of them, a good one to check, is the capacitor. So I'm going to stop this video here, but if you want to practice a little bit more, then I think it's a good idea to go through and check some of the voltages across other components. You can start with the capacitor, which the leads are right here. That wraps up this video, and I will see you in the next one. Welcome everyone to this video on using our digital multimeter to measure resistances, or use it as what is called an ohm meter. So on our multimeter, we are able to measure resistances in the range of all the way from 0 ohms at the 0 to 200 ohms, all the way up until this 200 mega ohms. So we can actually measure a pretty wide range of resistors. Now, on our board, unfortunately, the resistors, they're just too small to be able to accurately get in and take a resistance measurement with these probes. They're too big, these hand probes, to actually measure those very small surface components. And I will show later in the course one way that we can take measurements on these small surface mount components, but we're going to need some different equipment. For this lesson, just to demonstrate, I do have 2 bags of resistors here that I will show on how we can measure. All right, so the first one I've got here is we have a 680 ohm bag of resistors, and you see they have 1/4 watt rating, and they're guaranteed to be within this 5%. So we can double check and make sure they are actually at 680 ohms or within that 5%. Alrighty, so I'm going to set the multimeter to the 200. We'll go up to the 2000 ohm setting, and that should give us a good reading. All right, and on these leads, you can see there's actually a little ledge, and the resistor leads just fit nicely into that little ledge. So I'm just going to fit mine in here. All right, and if I move my hand out of the way, so we can see that this resistor is measuring at 672 ohms. So we are about 8 ohms off of what the baggie is saying, but that's okay because we're within that 5%. All right, and I've got another bag here that I'm just going to pop open. Okay, and this one, actually, I'll just show first. So this one's at 6.2 kilo ohms, again, 1/4 watt and 5% tolerance. So same thing, I'm just going to put it into the ledge here that is on these leads. And we can just hold it in place. All right, and you'll notice when I do this one, so on our multimeter, we are just reading 1. And the reason for that is this is a 6.2 kilo ohm resistor, and we're just in this up to 2000 range, so we're over that range. So what I'm going to do is I'm just going to switch it to this 20K range, and then we should be able to take our measurement. All right, and if we hold it here, just going to make sure I'm holding it tight to get a good reading. Okay, so we can see that this one's actually off by quite a bit. So we're at hovering around 6.03 kilo ohms when it's supposed to be a 6.2 kilo ohm resistor. So we're still within that 5%, but just wanted to show how these can vary off by a little bit. Okay, so if you don't have any of these resistors at home, that's okay, don't expect you to. But if you do want to make a measurement with your digital multimeter to check some resistances, then one thing we can do is we can actually measure the resistance between our hands through our body. We were chatting about in the safety lesson how our bodies actually have quite a high resistance, and I just want to show you how you can make that measurement. So I'm not entirely sure what mine are, but I'm expecting, I have dry hands and I do have some calluses on my fingers. So I'm going to start at the highest reading at 200 mega ohms. And then if we have to, we can move down from there. So I'm just going to switch mine to this 200 mega ohms. What I'm going to do is I'm just going to grab the probes pretty tightly here and we'll see what it goes to. All right, so mine is going to this 1.3, and we know that's in mega ohms, so that's 1.3 mega ohms. So that's the resistance through my body right now, which is pretty cool that we can measure it as that 1.3 mega ohms. I'm just going to lick my fingers here and see how that changes the resistance. Okay, so I just licked my fingers to get them a little bit wet, and we can see that even already that's bringing down the resistance value a bit. And if I got them even wetter, then we would be able to bring that resistance down even more. So kind of cool to see that. On our board, unfortunately, as I mentioned before, it is too hard to measure the resistance values with these probes. There is some value to taking resistance measurements on the board sometimes if we're trying to do reverse engineering and figure out what value resistors are, or if we're trying to match a schematic to a board that doesn't have good markings on it, we can kind of identify the areas of the board by looking at the resistance. If you are making resistance measurements on a board and the resistors are big enough you can probe it, it's best practice to take resistance measurements with the board powered off, because that way the current that's running through the circuit will not throw off your resistance measurements. Of course, the way that this guy takes resistance measurements is it actually uses a low voltage itself, and then based on the amount of current that's able to flow, it's able to tell the resistance. So we don't want to throw that off by having the board have its own current going through it. And also just good safety practice to have it off. That wraps up this lesson on using the multimeter as an ohm meter or to measure resistance. I'll see you over in the next video. Welcome everyone. In this video, we're going to be taking a look at another one of the very important features of our multimeter, and that is to take a continuity test. So if I just bring this up closer to the camera, to use the continuity feature, we actually move this rotary dial to this little symbol right here, and you can see that it's got this marking that looks like it's making a sound. And that's because a lot of people also refer to a continuity test as beep testing, and we'll see why in just a second. So I'm going to switch my meter over to the continuity test setting, and we have it here. And what the continuity test means or tests for is that we have electrical continuity between the 2 points in this probe. So of course, if we are able to just touch these together, we'll see that it starts to give us this nice beeping. And that indicates to us that there is a path for electricity from this probe to this probe, which is something that's very important to be able to test on circuits. Just to give you another idea of what I mean by that, of course, I've got this alligator clip here, which is essentially just a straight wire. And if I connect it to this red probe, and then as soon as I touch it to this probe, we get the beeping, again, because electrical signal or an electrical current is able to flow between these two. Now, this is maybe honestly the most important tool and what I use my multimeter for the most when I'm hardware hacking. And this is because this allows us to be able to tell where signals or currents are flowing on the boards, especially if we don't have a schematic. We can do what's called beeping it out. So we can, touch from different pins on things like chips to output pins and determine where those are going on the circuit. And we can also trace through vias. So you remember when we were looking at the board, we have those vias that go down to different layers. So if we're trying to figure out, our signal disappears down a via, then we can go and probe the other vias and trace where that signal is coming through. So now that we have a little bit of an idea about how this beep testing works, I'm just going to move this to the side, bring the board back, and show a few areas that we can beep out or start testing on the board. I've got my board upside down here because I do want to make a connection from this ground that we already identified when we were measuring the voltage, because one of the first things that I'm going to beep out or check is see if I can identify any other grounds on the board. And you don't necessarily need one of these alligator clips or this third hand to do this. I could do it without it, but it's kind of hard to show on the camera or film. So what I'm going to do is I'm actually going to connect this alligator clip to here, and then I don't have to try and reach under the board. And I'll just leave that connected, and I'm just going to flip this board over now. All right, so I've got the board flipped over, and again, I have connected this green jack to the underside of the negative pin on this input voltage jack here. And you can do it by just putting the probe underneath here. It's just kind of a pain to film, so that's why I have this alligator clip. The other thing that I just want to quickly call out in case you didn't notice is we don't have any power supply to the board. I have it completely unplugged. And when we're doing these beep tests, we don't want any power. We just want to be checking for the continuity or the electrical signal that comes from our multimeter. So we'll leave the board powered off. I'm going to connect the black end to this here so that it's connected to ground. And when I was visually inspecting the board, and this is something that you'll get used to, I did identify this interesting top piece of bare metal pad here. And you generally won't see these bare metal pads left on a board like this unless they're connected to ground. One of the reasons for that is they just can become an antenna and add noise or interference. So when I saw this, it stood out to me that I thought that this was ground, and I just want to verify that now with the continuity tester. So when we touch to this, see that I immediately get a beep, and that does confirm for us that that is ground. So what I'm going to leave as a challenge now for everyone, so if you want to pause the video after this, is to just go through the board and probe out and see if you can find any other grounds on the board. There's one that's actually labeled, so that there's an easy one, but there's a couple other grounds on here. So I'll just pause it now and see if you can beep out and find some of the grounds. All right, did you find any? I'm just going to show a few of them. So I know, for example, that there is one over here, I believe. Yeah, so we know that we have a ground point over here. And then, of course, we've got one labeled over here that is a ground as well. And we're going to be coming
back to these guys later because they are going to be quite important later on. So that just goes to show how we can start to test beeping out and checking for continuity. We're going to be using this a bit more throughout the course and helping us to identify where different pins and different connections travel on the board itself. That wraps up this lesson, and I will see you over in the next video. Welcome everyone. In this video, we're going to be chatting about taking a current measurement with our multimeter or using it in the ammeter setting. Now, as hardware hackers, it's not as important to be able to take a current measurement, and unfortunately, it is actually pretty difficult to do on a circuit board. And the reason for that is that opposed to how we measured the voltage in parallel by measuring just across the leads or the pins of the component, in order to measure current, we actually have to insert our meter in series in such a way that all of the current is going to actually travel through the meter. So we take a look back at our original drawing that we did before where I was showing how to measure the voltage in parallel. I've put a break in that circuit here. And if we wanted to measure current, so we'll set it to this 200 milliamp reading here, then we would actually have to put our positive lead here and our negative lead here. And then all of the current, it has nowhere to go. So if I just kind of rest these down, you think of them connecting to those points, then all of the current is going to flow into the positive lead. It's going to go all the way through our meter, back out the black one, and then travel through the circuit and then back to ground. So opposite to our input resistance being really, really high when we're measuring voltage because we don't want any current to come through and alter the circuit, it is the opposite when we're taking a current measurement and our input impedance is very, very low. It's generally in the single digits of ohms, and the better your meter is, actually, the lower that resistance is, because we don't want to be having any voltage drop over it and affecting the rest of the circuit by putting something in series. So this is the reason that I'm chatting about this, even though it's not something we're going to be taking any measurements with, because this is how it's the easiest to actually damage the meter or blow a fuse. Now, the reason for that, again, is the input impedance or input resistance of this is extremely low. So if we were to close this circuit, so we just draw this closed circuit, and we were going to, try and measure the current that's coming straight out of that jack, and we're just curious about it. And we set, this to our 200 milliamps because we know that we think it's going to be around that. And we were to just then touch our leads here, so positive and negative. Then I'll just draw out what's going to happen on this circuit. I already took a measurement, and I think in the manual, if you read this, it's going to tell you what the input impedance or the input resistance is. And when I measured it, it was just around 4 ohms. All right, so I'll just draw out the circuit, and we'll say that this is the probe, and it's coming down, and this resistor will signify our actual multimeter in that current reading setting, and it was 4 ohms. I can tell you right now, the impedance of the circuit is going to be much, much greater. So what's going to happen is when we get our current flow here, it's almost all of it is going to go through this top route, and it's going to come down through our meter. Now, if you just do the quick math on this, 9 volts, 4 ohms, that is going to give us a current of 2.25 amps, which we already know is much greater than our meter is fused for. So we're just going to blow that fuse immediately. And it's really easy to blow these fuses taking the current measurements if we're not doing them properly and we are doing them in parallel. So I just really wanted to quickly call that out. Now, again, so the reason that this is really challenging to take these measurements on the board is we actually need to break the electrical path or the signal path that current is taking. And there's no really good way for us to do that on a circuit board without actually damaging it. So if we wanted to, for example, interrupt the trace, then we would have to actually, we could take a knife and cut that trace, or we could, cut off the end of a component and lift it up and then try and connect between that. So there isn't really a good way to take a non-damaging measurement. And that's why we're not going to be taking any.
As hardware hackers, this isn't super important. And just a quick reminder, of course, of Ohm's law and that we can usually calculate the currents as needed quickly mathematically. So I did want to just really quickly demonstrate, how you can use the multimeter to take a current measurement and just how to do it properly without just using this picture. So what I'm going to do is I'm going to bring over a quick little very basic circuit and show how we can actually take a measurement. Okay, so what I've got here, this is called a breadboard and it's used for prototyping circuits. So the way that it works is that on these lines that run perpendicular to the length of it, these are all electrically interconnected. So I have the power coming and it travels through this whole top line. And then I have the ground on this battery and it travels through this whole line right here. So what I've done is I have the LED, the positive end of it comes out to this line here, and then the resistor is in another hole, so that means there's a connection here. And then when I tuck this into the ground, you can see that the LED lights up. So very, very basic circuit. Now, if we want to measure the current from this, what we can do is I can, again, break this connection. And we're just going to grab a couple alligator clips, and I'll show you how we can put this meter in series. Okay, so what I've done is I've just broken that connectivity in that circuit and I've connected the alligator clips to each end. So if I touch these together, we should see this light up. Yep, perfectly, it lights up. All right, so if I put the positive end of our ammeter in through here, and then if I connect through here, this means we have it in series. And we're looking at about 11 milliamps flowing through this. So that's how we take that. Again, if this were on a circuit board, it would be really hard for us to do this because we would actually have to, either desolder these leads and pull them out, or maybe cut them and then use some sort of jumper. So there isn't really a good non-destructive way to do it. Before I wrap up this video, just a really quick reminder to be careful when you're taking current measurements. Make sure you have it in series because it is the easiest way for us to blow a fuse or damage our equipment. So that actually wraps up this section and wraps up electrical engineering for Hackers 101. So great job on making it this far. I will see you over in the next video where we will start over in the electrical engineering for Hackers 201 section. And we're going to expand on some of these fundamentals and look more in depth at some of the principles that we'll need to know for our hardware hacking. Thanks a lot. See you in the next video. Welcome everyone to the first video of Electrical Engineering for Hackers 201. In this video, we're going to be talking about alternating current and direct current. Now, in the first 101 section of this course, we actually already have been talking about direct current, and all of the circuits and everything that we've been looking at, all of the formulas have been in reference to direct current. In this lesson, we're going to be adding in alternating current and talking about the difference that this has between direct current and some of its important properties. Now, I think using current to describe these is a little bit confusing. And the reason for that is when we're getting power from a power supply, the voltage being supplied is set by that supply, and then the current is actually proportional to that voltage. And we know that the current is going to be proportional to the voltage and the resistance in the circuit. So I think it's a little bit easier to think of this as direct current, actually meaning a fixed voltage, and then alternating current, what that means is that we actually have a fluctuating voltage. And just to give a little bit of a representation of what I mean by that, we're going to go back to this very first image or pictographic representation of a circuit where we have this voltage, and the voltage creates a current that goes through our circuit and through our light bulb. And if we look at this as a direct current, so in our example, that would be a fixed voltage. One way to actually represent this voltage that will make more sense with these alternating current is in a graph. And on this graph, we would have voltage being the y-axis, so how much voltage we have. And then on our x-axis is over time. Now, with a fixed voltage or a direct current, we can see that this just makes a horizontal line. So in this example, the voltage stays the same. It's just a fixed voltage. And as we go through time, that voltage level is the same. Now we know due to Ohm's law that the current is actually going to be proportional to that voltage, and it's also going to be a fixed level. Of course, the value that this current is going to be is proportional to this resistance. However, we know that it's going to be set unless the resistance change is going to be the same current level.
If we change this though for an alternating current, so we'll say that this is an alternating current, and I'm just going to bring up a marker here to draw on the graph what that might look like. So one example of alternating current that everyone is probably familiar with is the voltage that comes to our house. And the way that this voltage changes over time can be represented with a sine wave. So the voltage comes up to its peak voltage and then it comes down to here. And of course, if we represented the current at this point, it would come up to here and come down. And of course, this current again is going to be proportional to this resistance, but we know that as far as the graphs go, they're going to follow the same shape. Now, what happens when we get to this point on this? So once we actually start, going the voltage into the negative, then the current is actually going to go into the negative. And we see at that point that our voltage actually flips, and then the direction of our current changes. So this is kind of where that alternating current terminology comes in, because our current is now flowing the opposite direction. So of course, if we finish this drawing, it's going to look something like this. And our current is going to follow. And in the sections where our voltage flips into this negative, of course, our polarity is going to swap here, and our current is going to start actually flowing in the opposite direction. So one example of alternating current that everyone is probably familiar with is the power that comes into our house. Now, in North America, this operates at 120 volts AC at 60 hertz. And we'll talk about what that means a little bit later in this lesson. Now, you may be wondering why I'm talking about alternating current if we actually are not supposed to be touching anything with our household power or the power from our sockets in our house. And that is absolutely correct. Again, shouldn't be working on that. However, we do use as alternating current or fluctuating voltage for a lot of other very important things in electronics. So just to represent that, I'll show this graph here that represents a fluctuating voltage over time. So this waveform here that we have, where it goes from this 0 to 5 volts, is a good representation of something we could see in an IoT device. Many sensors are very good at changing the voltage that they supply based on how they read something. An example of this could be a temperature sensor, where as the temperature changes, the voltage that is output by that sensor would change. So we could see a change in a fluctuating value like this. So I just want to bring up a second wave here that's going to help bring this point home for why these alternating currents are important in our IoT devices and electronics. All right, so I brought up a square wave here, and these are very important for how we do digital communications, where we will have a high voltage represent a 1 and a lower voltage represent a 0. And even though these are more what we call a square wave, they are still a type of alternating current. And as such, they behave differently than if we just have a fixed voltage. So that is why it's really important for us to learn a little bit of the fundamentals about how alternating current functions and changes things in our circuit. I'm going to go back to just a plain standard sine wave here so we can talk about some of the important ways that we actually describe and measure alternating current. The very first one is what is called amplitude. So the amplitude is the distance between the 0 or the mid-level, if it is going from positive to negative, to the top of the wave. So this would be the amplitude for this sine wave. The second one we'll talk about is the peak voltage. So this is the highest voltage that's represented, and it's actually the same as the amplitude, but sometimes you will hear it called the peak voltage. So generally when we have a sine wave that is not fixed amplitude like the one we saw in the last, the peak voltage will be the highest one, so the highest that it can get. All right. The next one that we'll talk about is the peak to peak voltage, which is VPP, and that is the measurement of the top peak to the bottom peak. So it will be double the amplitude. The next measurement or calculation here that I'm going to show is not actually important for this course, but I just really wanted to show it out of curiosity. In case you're wondering, for example, at our household voltage, that's 120 volts AC. Which voltage is that? Is that this peak voltage or this peak to peak voltage? Well, the answer is that it's actually neither of those. that 120 volts AC is actually what we call the root mean square voltage, or RMS. And I'm going to quickly show here how to do the RMS voltage calculation for a sine wave. Now there is a bit of math behind this that I'm not going to show because it's outside of the scope of this course. So just keep in mind this is for a sine wave like we use in the North American household voltages. So to calculate RMS, it is equal to the peak voltage divided by the square root of 2. And we can actually approximate the square root of 2 as 1.41. So the peak voltage for North America is actually 170 volts if you were to measure this actual top peak voltage. And of course, if we do 170 divided by 1.41, then this gives us just around 120 volts AC. Now, the reason we use this RMS voltage is because if you were to compare its equivalency in DC, so if we think back to our circuit where we have our light bulb, and if we want to kind of think about the brightness of the light bulb or the actual power delivered to that circuit, the equivalent AC to DC would be the RMS voltage. So if you have 120 volts DC, then you wanted to compare this to AC, then it would be equivalent to that RMS voltage. So that's why we use this RMS when we're talking about it. And if you ever see, voltage for our household at 120 volts AC, you can know that that's actually in this RMS calculation. Again, we don't need to know this for the course. I just thought some people might be curious about that. Okay, so I've brought up a square wave because there are a couple specific things we should talk about with regards to square wave. Now, the frequency and period and amplitude that we talked about in sine waves, those are all going to be the same for square waves. However, since we do have this wave changed a little bit in how it's formed, there are some different characteristics that we use to describe it. Now, the first one is the pulse width, and this describes just how long this, like if we think of this as the on portion of the square wave where we're actually applying a voltage, the pulse width is how long that pulse goes on for. So we see in this example of this first portion of the square wave, the pulse width is 0.1 seconds. And in this first section of the square wave, we have uniform between how long it's off. So it's off for 0.1 seconds and on for 0.1 seconds. And this whole section right here would be one period. And then we would know that the frequency for this would actually be 1 over 0.2 because our period is 0.2 seconds, so we would have a 5 hertz frequency. Now, what happens if we don't have this uniform square wave? So I'll just bring it up here. What happens if we actually have like a longer resting period than we actually have our on period? Now, the way that we describe this is with what's called the duty cycle. And the duty cycle explains the ratio of the pulse width or the on duration to the actual resting period in that period. So it is a proportion. In our first example, where we have this pulse width that is equal to this resting period, then we have a duty cycle of 50%. So the duty cycle, which is represented generally with a uppercase D, is calculated by the pulse width over the period duration. So for example, in this one, we have 0.1, so the pulse width is 0.1 seconds divided by this whole period, which is 0.2 seconds, which gives us 50%. In most of the waves that we're going to be looking at for digital communications, we're just going to be working with a duty cycle of 50%, and we're going to have that fixed pulse width. However, I just wanted to show these terminologies because you may hear them come up, and they're important to how we describe these square waves. That wraps up this lesson. I'll see you over the next one. Welcome everyone. In this video, we're going to be taking a look at capacitors and talking a little bit more about them. Now, we have already chatted a bit about capacitors in the safety lesson, and then also when we opened up a router for the first time and we're looking at the PCB, there were many capacitors that we would have seen on that board. And we haven't chatted about them fully in depth yet because we needed to have an understanding of alternating currents before all of their functions make sense. So now that we understand about alternating currents, let's take a look at how capacitors function. Okay, so I've got up on the screen here the actual schematic representation of a capacitor, and you'll notice that it is two, what we see as like conductors or almost wires that are parallel to each other, and we just have some air in between it, so it kind of almost looks like an open circuit, and then we've got our leads connected to it. And the reason for that is this actually mimics the construction of an actual capacitor. So we take a look here at a cross section of a certain type of capacitor, which we call a ceramic disc capacitor, or just a ceramic capacitor. You'll notice that on the inside, we have what's called the electrode, and it's just a large metal plate with a big surface area. So we tried to make it as thin as possible and make the surface area as big as we can. And this is connected to the actual leads here. And if we looked on the other side, coming to this lead, there would be an identical plate to this one. And then it's actually sandwiched in between, we have this ceramic disc. And the ceramic material is what we call a dielectric. And what this means is that it does not actually conduct any electricity, so it doesn't allow any electrons to flow through it, but it's very good at holding these electric charges on the outside of its material. And this is super important for how the capacitor functions. To better understand and see this in action, let's take a look at it in a circuit. I've got a very basic DC circuit here with just a 9-volt DC power supply and a switch that's closed and a capacitor in series with that. So what's going to happen in this circuit when we throw this switch closed is that we will initially get some current that travels through. And in this DC circuit, what's going to happen with those electrons is they're actually going to pile up on those electrodes or plates. And because we have this dielectric in between here, they're not actually going to be able to flow through to this wire. So we will get an imbalance of those charges piled up on these plates here. And when we get that steady state, and the capacitor is what we call the charge state, then we'll get the matching voltage across this. So if we were to measure the voltage over this capacitor, we know, of course, because of Kirchhoff's voltage law, it's actually going to be that 9 volts. And at that steady state, we'll actually get no current through here. Now, of course, in a real life scenario, we wouldn't just hook a capacitor up like this because it really has no function. It's basically just creating an open circuit for us. So to give a better representation of what they're actually used for, let's take a look at a more real life applicable scenario. So I've added into our circuit here this 350 ohm resistor and an LED that we're going to be lighting up. And let's say in this circuit, the switch is open and it has been open for a very long time. So there's actually no charge left in this capacitor. So if we were to measure the voltage here, it would be 0 volts. We have 0 volts over this capacitor and our light would be off. When we throw this switch closed, let's see what happens when we throw this switch closed. We're actually going to start to get some current coming through, and it won't actually go through this capacitor. But what's going to happen is over time, the capacitor is going to charge up, and it's actually going to happen fairly quickly. This is going to be, almost instantaneous. But as it charges, we will get some current, and the current is not actually traveling through the capacitor. What's going to happen though is we're just going to induce a current because we're going to have, if we look at it at this time, for example, right here, then we don't have a fully 9 volts charge here. We're going to have an imbalance of that voltage, and that's going to induce some current. However, once we actually reach this steady state here and we get to that 9 volts, we're not going to have any current here, and our circuit's just going to function as it would normally with that series circuit of our resistance and our LED. Our LED will be lighting up and we will be all happy because that's what our circuit is designed to do. Okay, so what happens though if we throw open this switch? And we do that to simulate maybe we have a little dip in our voltage supply, or the power cuts for a second. What would happen in that scenario? All right, so immediately what's going to happen then is we have this 9 volts here, and it actually will function kind of similar to a battery. So we'll see here, we actually start having our current being induced because we can think of the polarity of this. We have a minus and a plus here, and we can treat it kind of like a battery, and it's actually going to power our LED and our circuit for a brief period of time. So if we take a look again at the graph for that, it's going to look something similar to this. Now this dotted line here represents when we throw open the switch. So in our steady state, the voltage here is just happy at 9 volts, and we're going along in that straight DC. And then when we flip open the switch, what's going to happen is our capacitor is then going to kick in, and it's going to discharge very quickly all of its charge, and it will actually be able to power the circuit for a brief period of time. See here that it actually dips pretty quickly, and it follows this then slowly discharging. So while this isn't a perfect power source for us or voltage source, because of course our voltage actually drops in time pretty quickly, and with it, so does the current that actually comes through the circuit. It will actually help us with some quick dips in our voltage source. So maybe if we only came to here and then we came back on, we'll come right back up to that 9 volts quickly. And that's a lot better than us just dropping off this peak. So this is why you'll generally see these bigger size capacitors in the power supply, because they really help to even out if we have any dips or drops in the voltage. Then they can keep our circuit running as it should for a brief period of time until that voltage kicks back in, which is a really nice feature. Now, the amount of charge that we actually hold is what's going to determine how quickly this capacitor discharges and how long we can actually supply some voltage and current. And the property of a capacitor to actually hold onto this charge is what's called capacitance. So you'll see here it's capacitance, and we usually denote that with the letter C, and it's measured in the unit farads. Now, one thing to note with farads is this is actually a very large unit. And an electronic circuit, so things like our IoT devices, we're generally going to be seeing things in the range of microfarads or sometimes even nanofarads or picofarads. So those are just very small fractions of the SI unit, which is farads. So this demonstrates how capacitors behave in a DC circuit. And the one really important takeaway for this is that in its steady state, there's not going to actually be any current that is able to flow through the capacitor if it's hooked up to a voltage source. So keep that in mind. You can think of it at DC in its steady state that it's basically an infinite amount of resistance. This is not the case, however, though, for alternating circuits. So we're going to take a look at that now. Okay, so I've just brought up a very basic circuit here where I am showing what we have an alternating current voltage source. So this little squiggly line inside of the circle, this is what we actually use in our schematics to represent an alternating current voltage source. And just for ease of calculation and what we're used to, I'm using our North American voltage here, so 120 volts at 60 hertz. Now, as I just mentioned, if this were a direct current voltage source, then what's going to happen in our steady state is the current's going to come. We're going to build up those charges here. And then once we reach that steady voltage that matches our voltage source, then nothing's really going to happen in this circuit. We can kind of just think of this as being an open circuit, and we will have no current coming across our resistive load here. For an alternating current, this is actually not the case. The alternating current is actually able to interact with this capacitor and transfer its charges over through to it, which is actually going to then create a current on this side here. Now, one thing that is important to note is that we're not actually still passing electrons through this. This dielectric doesn't allow them, but the alternating voltage here that comes with our alternating current is actually going to cause this charge to build up and then discharge, and that imbalance of charges is going to allow us to transfer the current over to this side, and we'll actually have some current through. Now, capacitors still do resist the flow of an alternating current, and the amount that they resist that flow of alternating current is what we call reactance. And the calculation for reactance here, we are going to start to get into a little bit more math, but the calculation for that is it's 1 over 2 pi, and this F is frequency, this little f, not farads, and then C for capacitance. So the most important takeaway here, just to remember, is that it is inversely proportional to the frequency and the size of the capacitor. So as we increase this frequency, the higher it is, then the less that this capacitor is going to resist that alternating current. And also the greater the size of the capacitor, then the less it's going to actually resist this flow of current. So if we were to calculate it for this capacitor, of course, we're 1 over 2 pi FC. So if we plug in our numbers, we have 60 hertz, and then this is 100 microfarads if we just convert it to farads, and we're going to get 26.5 ohms. Now, one important thing here is we can't actually just add this reactance with a purely resistive resistance. And unfortunately, the math does start to get a little bit complex here about how this works, and it requires some trigonometry. And I'm just not going to go into that in this course. If you are curious about it, then I would encourage you to take a look more and study more in depth about it. But I'm just going to show some of the formulas here for it and how it works, and I'll tell you about the key takeaway. So we want to combine our purely resistive resistance with this reactance. What that's called is, and you've probably heard me mention this a few times, is called impedance. And we denote impedance with this Z here. So for a series RC circuit, and this math only works for a series RC circuit, which is what we're mainly going to be working on. And this RC circuit means we just have a resistor and capacitor in series. We can calculate the impedance as the square root of R squared plus X squared. So this is our resistance here, and then this is our reactance. So for our circuit, that's going to be 350 squared, which is this measurement of the resistor. And then we already calculated the reactance as 26. So we'll do this 26 squared. And I'm just dropping off that 0.5 here just to make this calculation super simple. And we get this 351 ohm. So the big takeaway here, and what I wanted to show, is that this 100 microfarad capacitor is really only adding about 1 ohm of impedance to the current. So it's really having very, very little effect on how much current is actually flowing through the circuit. And if we increase this frequency or we increase this capacitance value, then it's going to have even less effect on it. However, if we decrease this frequency, so as we get closer and closer and closer down to our DC, which would be, 0 hertz, we're going to get more and more and more impedance till we basically reach what is considered an open circuit, or impedance so high that we're not going to allow any current to travel through the circuit. And this is the most important takeaway for this. So if you don't remember any of the math or what impedance or anything like that, is just to remember that capacitors at a higher frequency are going to offer very little resistance. And the higher the capacitor value we go, it's also going to offer very little resistance. Now, this is super important for when we're working on our IoT devices, or really any circuit that's going to be working with alternating currents, because what it allows us to do is we can create what are called filters. And what we can do with these filters is that we can actually then block certain frequencies from going through to our circuit. And this is going to be really important for when we're working with all these communication signals and we have our square waves with different frequencies and we have interference. We're going to need these capacitors to create these filters. And that's why, if you recall, when you're looking at the board for the router, it was filled with capacitors, because this is trying to create a wireless signal. So we're going to have lots of different frequencies going all over on that board, and the capacitors are what actually allow us to filter out and keep only the ones we want. In the next video, we'll actually take a look at how we can create some of these filters and simulate them in Circuit Lab. But before we hop over to that, I just want to loop back to our original look at the 3 capacitors we started this lesson with and just chat a little bit about some of their properties. So on the left here, we have what's called an electrolytic capacitor. And the reason it's called that is because if you were to bust this apart and take a look at the inside of it, instead of just having 2 simple plates, we actually have a sheet, a very thin sheet of metal conductor here, and it's rolled around in a circuit, like almost if you think of like one of those like Swiss logs or something like that, those baked goods, it kind of is similar to that. And then on the inside, where between what is rolled, instead of ceramic for a dielectric, we actually have an electrolytic compound, so like a gel, and it's a very, very good dielectric. It's better than ceramic. And what that allows us to do is we actually can make these capacitors much, much bigger in capacitance. So if we need a bigger capacitor or bigger capacitance, then we have to use these electrolytic capacitors. Now, the one really important thing with these is they actually care about polarity, so which one gets hooked up to the negative and positive ends. And the way that we can see that is this will usually almost have a piece of like marking tape or indicator, that's the negative one. And then also the lead on the negative one will be shorter and the positive lead will be longer. And this is true for a lot of components that have polarity. The longer lead will be the positive one. And one way that I was taught to think about this, just to help you if you're ever going to forget that. So if you think of like a positive symbol and you take like 2 lines, for example, and you cross them like this, well, if you uncross those, put them together like as a lead, then it's going to be longer than if you just took a negative and put it as the lead. So that's how I always remember that the longer one is the positive one. All right, so the next one that we're going to take a look at is what we've already taken a peek at actually, and that is the ceramic capacitor. So we saw what was on the inside of this one, and these are great if we just need a fairly low capacitance because they are very cheap to make, and also the other nice thing is we don't care about the polarity on them. The last one here is a surface mount capacitor, so we can make them in that surface mount package, and you'll see lots of those on our router board, for example. And this is actually a ceramic surface mount capacitor, so it's just got a piece of ceramic in between two little tiny metal plates here. All right, so the last very important thing about these capacitors is you'll see on them they have two different markings. So the first one just tells us about the capacitance. On this one, it's 100 picofarads. And then we'll see this 1000 volts, for example, on this one. And this one's rated at 6.3 volts. So this voltage is kind of similar to when we had the current for our power supply, in that this is not actually the voltage that they operate at or anything like that. This is the maximum voltage they can withstand. So the voltage that the capacitor will be charged at is whatever voltage we apply to it. But if we go over a certain voltage that is more than it's rated for, then like these guys will actually blow up. You'll see them, they'll go pop and they'll blow up. And these ones will just burn out. So we got to keep in mind to take a look at that voltage rating. That wraps up this lesson on capacitors. I'll see you over in the next one where we're taking a look at Circuit Lab. Welcome everyone. In this video, we're going to be picking up from the last lesson where we were chatting about capacitors, and we're going to be doing a quick demo in Circuit Lab to show how we can use just capacitors and resistors to create both a high pass and low pass filter. So if you're following along or you want to follow along in your browser, you can get to Circuit Lab from www.circuitlab.com. And at the time of recording this, you don't need to create an account or log in. You can use it for free. However, you are limited to a set amount of time per day, so just keep that in mind. I have created an account and purchased their membership. I think the one that I have is about $20 a year. Just wanted to be able to support them and also have that unlimited access. So if you are enjoying their website, consider buying that membership. However, you should have enough time and be able to follow along with everything that I'm doing with the free version without logging in. So what I'm going to do is I'm actually just going to dig in here and create a common scenario that we have and what we could use a filter for. So I'm going to add in an alternating current voltage source here. So that's the symbol here, if you remember correctly. And I'm going to make it 1 volt amplitude, but I'm going to make it 60 hertz. So it's kind of like the voltage that's coming from our house. And then I'm actually going to add in a DC voltage source here. And I'm going to make this 9 volts, similar to the voltage source that we are using. And then what I'm going to do is I'm just going to add in a single resistor. Let's do a 1K resistor. Add in some grounds here. Going to connect these up with the wire. And then I'm going to add these nodes here. We'll call this one the voltage in, and we'll say this is what we're measuring our voltage out over. All right. And for those of you following along at home, you will notice that in this scenario, I mean, these are the same nodes, so of course the voltages and everything's going to be the same, but you'll see later why I have added those. Now, if we use what we previously did to check the currents and voltages here, we can actually see our 9 volts DC here, and we actually have this 9 milliamps. However, this is just purely the DC portion of the circuit, so the part that comes from here. However, this little bit of sine noise that we have here is actually going to affect the circuit. In order to see how that affects a circuit, we need to take a look at running a simulation for this, because of course this voltage source, it's going to alter over time, and we want to take a look at how that plays out over time. So what we can do is run a simulation. So I'm going to click down here, simulate, and we're going to do a time domain simulation, because what this is going to allow us to do is it's going to let us plot the voltages and the currents in graphs over time. That's kind of similar to how I've been showing them in the whiteboard lessons that we've been doing. I'm going to set the start time at 0 seconds. That's just when the plotting is going to start. And I think 100 milliseconds is an okay duration to run this. We'll be able to see enough periods of our wave in that. And then this last one is the time step. So that's how frequently we are plotting the graph. So I'm just going to do 10 microseconds. And that's going to give us lots of plots on the graph so that we can see nice smooth waveforms. And then it's going to ask here for us to add expressions. And this is why I've added these V in and V out. And we can just run a time domain simulation now, and we'll actually see that we have this V out, which is the orange one, and then the V in, if we just actually hide the V out one, see the V in is the same as the V out, which we were expecting. However, we'll see here, we wanted a purely 9-volt DC signal. I mean, if that was our goal. And we have this 1-volt amplitude of noise at 60 hertz. And in actual circuit designs, if I just hide this is something that can happen with poor quality power supplies, or if the power supply itself doesn't take care of this. With this 120 volts, 60 hertz that comes from our wall, if we're plugging, our power supply into the wall, and then it's supposed to transform this to DC and step it down to 9 volts. Sometimes what can happen is this signal is so strong that electromagnetically we can still get interference, and we can get some of that signal into our power supply, or especially if we have like an antenna where we're trying to pick up a wireless signal or something like that, we can get a little bit of this 60 hertz signal induced onto our line. And that's what I'm simulating here by doing that. So that's why we have that, 1 volt is actually quite a bit of noise on top of our 9-volt power supply. So what I want to show here is how we can quickly start to get rid of that. So if we actually, what I'm going to do is I'm going to go back to build here, and I'm going to grab this resistor, and instead of measuring the voltage out over the resistor, what I'm going to do is I'm just going to drop it in here. And I'm going to grab a capacitor and drop this capacitor down into ground. I'm going to set this capacitor, we'll start with 10 microfarads. I'm just going to rerun the simulation with these same parameters. All right, so we can now see that our V out is actually changing, and we're getting closer to, squashing it down to that pure 9-volt DC signal that we want. But we still do have a little bit of jitter. We've cut it down to, I don't know, about here, 9.37. So we've cut it down about 60%, but we still can do better than this as far as just getting a straight line. So I'm going to hide this, and then we can go back to the build. So the way that I like to think about this, or how this filter works, is that we have this resistive load here of 1 kilo ohm, and then we've got our 10 microfarad capacitor. And we know to our 60 hertz sine wave, these higher frequencies, that the impedance, or like what we can think of as the resistance of this capacitor, is very low. And so essentially what we're doing is we're just allowing the sine portion, or the alternating current portion, to pass over this with very little impedance. So what that means is that it's actually going to drop most of its voltage over this resistor because the impedance is much greater. And then for this 9-volt DC signal, of course, it can't even actually travel over this because it sees this as an open circuit. Now, if we want to improve our filter and get it closer to being that flat line, we have two options. We can either increase the resistance or we can increase the capacitance. So I'm going to increase the capacitance here. Let's just do it another 10 times and bump this up to our 100 microfarads. I'm just going to run the simulation again. And we can see now we're getting pretty close to that nice smoothed out straight line. We do still have a very bit of noise in here. We're looking at like 0.05 volts of noise, and our circuit's probably going to be able to handle that if it's looking for a DC at 9 volts. But we can do better. So let's just hide this and let's pump up our resistance again just to see how that affects it. So let's just double this guy to 2 kilo ohm resistor, and we'll run the simulation again. You can see we're getting even closer and closer to what would be a straight line. Now, of course, we can do the opposite here. So what I'm going to do is just click build here, and we can reverse these. So grab this. So I'll just delete that, grab this, rotate it, and just fix up my circuit here. Drop this in. 2K. So this circuit, the other circuit is what is called low pass filter, in that we only were letting those low frequency, or in our case, just the DC frequency to go by. And now if we reverse this, then this is what's called a high pass filter, because we're only going to be allowing those high frequencies that we want to go by. This one is actually maybe even a little bit easier to visualize because, of course, basically just creating an open circuit here. So none of this DC voltage is going to be able to pass here to where we're reading this out. So if we just simulate this and we run our time domain simulation, we can see that our Vout is basically just this 1 volt. And we don't have any of this 9 volts that would have brought it up here and that 9 volt DC interfering with it. So we've got an almost perfect filter here where we are bringing it down just to the original alternating current sine wave. So hopefully this little demonstration just gives a little bit more details about capacitors and how we can use them as filters. We can start to get a lot more complex with what we do with the capacitors and our filtering to make what are called band pass filters, where we're only going to allow a specific frequency band. So instead of it just being anything over or under a set frequency, we can actually also create them. So if we just want a set frequency range, so maybe from like 60 hertz to 120 hertz. So what I will end on with capacitors is I've really just barely scratched the surface of the theory that's behind capacitors and how they affect signals. There's a lot more if we want to start talking about phase and leading and lagging currents and voltages, but I don't really think all of that stuff is super important for us as hardware hackers. The main thing I wanted to impasse is just what they're usually used for in the circuits that we're going to be looking at and how they can play a role as filters. So that wraps up this video here, and I'll see you over the next one. Welcome everyone. In this video, we're going to be chatting about inductors. Now, when I was putting together the curriculum for this course, I wasn't entirely sure if I was going to include a video on inductors or not. And the reason for that is they won't be as frequently seen in small electronics that we're likely to see in IoT devices. However, for both completeness and because some of the science behind why inductors work is important, I've left this video lesson in. So with that being said, let's dive into taking a look at inductors. I've got one on the screen here, and then I've also got the schematic symbol here. Now, before we chat about conductors, we need to look at another important electrical engineering law, and that law is Ampere's law. And what Ampere's law says in like the most basic form is that when we pass current through a conductor, so we look again at our very basic, simple wire, and we'll imagine that this one is actually connected to a voltage source, so that's how we're able to pass a current through it. And when we pass this current through the wire, it's actually going to create a magnetic field around that wire. And I've got these blue rings here on the screen that represent the magnetic field, but just keep in mind this is a field, so it exists all around the wire. And as we get further away from the wire, the magnetic field exists, but it weakens in strength. Now, the direction, or what we call polarity, of that magnetic field is actually proportional to the direction of the current. So if we swap the direction of the current, you'll notice here that the polarity or direction of that magnetic field reverses. So Ampere's law is super important actually for how we interact with and use electricity in our day-to-day lives. And one of the reasons for that is that the opposite actually also holds true. And that is that magnetic fields actually are also able to induce currents. So you see here, I have that same wire from before, and I'm just showing these rings kind of expanding out to demonstrate how that field would propagate outwards. So keep in mind that as we get further and further away from the wire, that the magnetic field is actually going to weaken in its strength. Now, if we put another wire inside of this magnetic field, what's going to happen is that it's actually able to induce a current onto that wire, which is really, really important actually for a lot of our daily uses of electricity. So this is kind of one of the fundamentals of how we generate electricity. It's also how electric motors work, and it's also how we transmit a lot of our wireless signals throughout the air. Now, the one really important thing to keep in note with how this magnetic field induces currents is that it's not just a magnetic field that induces the current, it's actually a change in magnetic field. So when we first put this wire inside of that magnetic field, we're going to induce current for a short period of time. But then once we reach that steady state, and if neither of these wires are moving and this current is not changing, then we're going to lose this current that we're inducing because it's only the changing magnetic field. So in order to induce a current, if that's what we want, we have a couple of options. First, of course, we can move this wire, so we can move it in and out of the magnetic field. And remembering that the magnetic field changes in its strength as we get further from the wire, so this change is going to induce a current. Second is, of course, we can move this wire so that it makes this further. And then the last thing that is really important is we can also use an alternating current. So if we flow an alternating current through this wire that's creating the magnetic field, of course, as we change that current, this magnetic field is going to change in its intensity and also possibly its polarity if we have this current going back and forth. And what that's going to do is it's going to induce a current onto this other wire. So something super important to keep in mind. With that in mind and a little bit of an understanding of Ampere's law, let's take a look at how we can use this to create inductors. So I've got an example of an inductor here on the screen, and really in its most basic configuration or construction, an inductor is just a wire that is coiled up. So you see here in this illustration, we have a wire and it's coiled around itself many times. And in this example, it's not many coils, just kind of pictographically, but in reality, we're going to have, up to thousands and thousands of times that this wire coils around itself. And when we do this, these magnetic fields are going to form in such a way that they create a magnetic field in this kind of pattern where it's the strongest in the center. And what we can do with this kind of magnetic field like this is we can actually store energy in it. So when we send a current through the inductor and it travels all the way through it, even if it's just a DC current, when it travels through and it's, at that instant of it changing, it's going to create that magnetic field. And then if we actually remove that current, and as long as, we still have a path for current to flow, then the magnetic field is actually going to recede and it's going to release all of its energy back into the wire. So in the same way that capacitors were able to store their energy in that electric field, inductors are able to store their energy in this magnetic field that can then be released to create current back into the wire. Another thing to keep in mind is that this magnetic field, as it's being created or changing, actually creates a resistance or impedance on the current. So when we apply just a direct current to this wire, at the very beginning, when it's first being applied as this magnetic field is being created, it's going to create some impedance for that current. But then once it reaches that steady state, the magnetic field and the current are stable, then it's not really going to apply much impedance at all. We can just think of it to that direct current or a very low frequency as almost just being a straight wire. However, for an alternating current, and especially one that is fluctuating at a very high frequency, then the change in current is going to constantly be trying to change or fight against this magnetic field. And what that's going to do is it's actually going to create quite a bit of impedance for that alternating current. So we'll take a look at the next slide about how that impedance and reactance is calculated. Okay, so I've got a very, very basic circuit here, again, similar to the capacitor and resistance circuit that we were looking at. Now you'll notice that I have swapped out our voltage source here with a 10 kilohertz frequency, and that's because inductors, they generally interact much more with these higher frequencies and impede the higher frequencies. So I have upped it to make it a little bit more realistic in the actual value of the inductor. So similar to capacitors, inductors do have a measurement for how much energy they can store, and we call this inductance. It's usually measured or denoted with an L, and the unit for it is henries. Similar to capacitors, Henry is a pretty large unit, so you're generally not going to see inductors having a measurement of a full Henry. A lot of times you'll see it in millihenries or maybe even microhenries. And again, like capacitors, the amount of resistance that they have to alternating currents is called the reactance. We generally denote this with an XL. And the calculation for it is 2 pi times the frequency times the value of the inductor, so the amount of henries. And you'll notice that kind of opposite to capacitors, our reactance is directly proportional to the frequency and the size of the inductor. So as we increase the frequency, or as we increase the inductor, then we're going to get more reactance. In our example here, we can see if we just run the quick math, we're going to get around 6,283 ohms of reactance. And if we convert that into impedance following the similar method that we did for capacitors, I won't go over all of the math again, but if we just really quickly run through this math, you'll see that we're going to be getting an impedance of around 6,292 ohms. So adding this inductor in series for this somewhat high frequency is going to add a lot of impedance. And this, honestly, this really isn't even that high of a frequency. You know, we can get up into the megahertz or gigahertz in signals. So you can see how at these higher frequencies, these inductors are actually going to start to be almost like an open circuit or infinite impedance for these really high frequencies. Just to really quickly circle back to my initial comment from the start of the lesson on how we won't see inductors as much in smaller electronics like we're going to see in IoT devices. Now, the reason for that is twofold. The first is that inductors themselves are costly to make in comparison to capacitors. So if we look at this example here, we've got an inductor, or even this one on the circuit board here. You can see how we actually have to take a wire and then either wrap it around itself or wrap it around some other material. And this manufacturing process for this is more expensive. It just costs more to actually do this than a capacitor, where we can just take two metal plates and slap them together over top of a ceramic disc or some other material. It's a lot easier to make those capacitors. The other reason is if you look at this circuit board, this is kind of an old school circuit board, but just to really demonstrate it, I've got an inductor here, and then we've got some capacitors here. Now, these are much smaller, like in their ability to store energy. And you do see we've got some big capacitors here, but overall inductors are going to be a lot bigger than capacitors and take up more space on the circuit board. And then also we still have that magnetic field that we have to worry about that inductors create, and they can actually be a source of noise on our circuit boards for us. So if we're not careful about where we put them, or if we're shielding them properly, then that magnetic field that they create, it can actually bleed out into the rest of the lines on the circuit, and it can be a source of noise for us. Now, we did see just in our previous example how inductors could be an excellent filter, especially for these high frequency signals and blocking them. But keep in mind that we can actually use a capacitor to block high frequency signals as well. And we demonstrated that in the capacitors lesson, where we were able to create what we called a low pass filter that just let the low frequencies through and block those high frequencies. And then using that same capacitor and resistor and just switching the order of them in the circuit, we were able to do the opposite. So for a lot of applications where we would use an inductor, we can actually use a capacitor instead. And since they're cheaper, smaller, and easier to produce, we just select to use a capacitor. Now, there are some specific cases where inductors are better, and I'm not going to go into those, but you will sometimes see them on the board, so it's something to keep in mind. That being said, inductors also play a really important role in lots of other areas of electrical engineering. So if this is a topic that you are interested or you want to learn more about them, I've really just scratched the surface about both inductors and how Ampere's law functions. So definitely would encourage you to dive deeper into that. With that being said, that does wrap up our video on inductors, and I'll see you over the next one. Welcome everyone. In this lesson, we're going to be chatting about diodes. So I've got the schematic symbol for a diode up here, and then a picture of a very standard through-hole style diode here. Now they do come in many other packages, but this is what the common through-hole ones are going to look like. This is another circuit component where it really makes the most sense to take a look at it in an actual circuit. So let's take a look at a basic schematic that has a diode in it. And we're just going to revisit that really basic DC circuit that we were looking at before, where we have our 9-volt DC power supply, and we've just got a resistor here, and we've dropped a diode in series with it. So just for the explanation of how this diode functions, I'm going to drop in 2 circuit nodes here, and just to help label the polarity of the diode. So this end of the diode is the positive one, and this one is the negative one here. And you regularly won't see diodes represented like this in schematics. I'm just adding this here because it makes it a little bit easier to understand what's going on. If we just bring that picture of the diode back, just so you can see, this end is the positive end, so it correlates to this end here. And this end is the negative end, the one with the stripe on it, or the way that I like to think about it is that this is just a negative symbol. And the positive end of a diode is called an anode, and the negative end is called a cathode. It's not super important to remember those, but just so you know, that's how they work. The way that I remember it is, since anode comes in, alphabetically before cathode, it's the positive one. And the way that diodes function and why we needed to talk about this polarity is they actually work similar to like a valve in water, in that they control the flow. In our case, it'll be the flow of electricity, so current, in such a way that they're going to allow it to only flow in one direction. So if we hook this diode up in such a way like we have here, where we have the positive end or the positive lead hooked up to the positive end of our voltage supply, and then we also have the negative end hooked up to the negative or to ground, then this is going to allow current to flow as it would here, and it's going to offer very, very little resistance to this current. If we flip this voltage supply around, so you see here now I have flipped this, so we've got this negative to positive, and we're going to actually have our current be trying to flow this direction around our circuit. And of course, we've got the negative end of the diode, or the cathode, hooked up to the positive end of the voltage supply. And this is actually going to block any current from flowing. It's going to basically be like an open circuit. We do have a very, very small amount of current, that's called the leakage current, come through, but realistically, you can just think of this as being an open circuit, and it's going to block that current from coming through. The really nice thing about the schematic symbol or representation of diodes is that, it actually is just an arrow that helps remind us what direction they go. So if the current's flowing in the same direction of the arrow, it's going to pass. And if it's coming into, where we have this line that I kind of think of as like the negative symbol or like a wall, it's going to block the current. So this is really, really useful for helping us control the flow of electricity. And there's actually a lot of things that we use diodes for in electronics. And I'm not going to go over all of them in this lesson, but just to get you kind of thinking about it, one really basic thing that we use diodes for is to protect our circuits from applying a backwards polarity or backwards voltage to those circuits. So we talked about, different circuit elements, like there's types of capacitors or even LEDs, which are actually a type of diode. They really don't like having the polarity swapped on them and putting voltage or current the wrong way through them. And this is especially true also of lots of like digital components, which we haven't talked about yet, but things like processors or, all the chips inside of our actual electronics, they really don't like having their polarity swapped on them. This can fry all of those components. And you've actually maybe done this before with like a remote or something else that has a battery, where you put the battery in backwards and you realize it was backwards. It didn't work, but nothing bad happened. Switch the battery around and everything was okay. And one thing that may be happening in this circuit is that the designers added in some sort of reverse polarity protection, and they used a diode to do so. So that if you put the battery in backwards, you hook your voltage up the wrong way, what it's going to do is it's actually just going to block the current from flowing, and it's just going to be like, an open circuit, and no damage will be done. So that is one way that we can use diodes. There's lots of science behind how diodes work, and we're not really going to get into that. However, there are some specific characteristics about how they actually function in the real world that we should take a look at. The way that we've been looking at them or talking about them in the last couple of circuits here is mostly as an ideal diode. And in the next couple slides, we're going to take a look at how they actually function in real life. All right, so I've just rearranged the lettering on this schematic here just a bit. It's still the same circuit, just to help identify this voltage here. So the first characteristic that we're going to talk about is the forward bias voltage. And what this means is, previously we were talking about how if we hook the positive end of our diode up to the positive end of our voltage source, and of course the negative is connected to the negative or ground, then we're going to be able to get some current. Now, in reality, this won't happen for all voltages. It's only going to happen if the voltage that we hook up is greater than what is called the forward bias voltage. And on most standard diodes, this is going to be at about 0.6 volts. So once this voltage here, we've got it at 9 volts, so that's not going to be a problem. But, if this were like 0.4 volts or 0.3 volts, then that's not going to be enough to, the way I think about it is turn the diode on and go over that forward bias voltage and actually allow current to flow. Now, in reality, it's not going to be exactly at 0.6. It's going to be, kind of around there, and there's going to be a kind of region in that where there's, a bit of current that can come through. And as we get closer to 0.6 and go over it, it's going to allow all that current to go through. But, 0.6 is a pretty good threshold to think about. And there are diodes where this number is greater or smaller if we need them in our design. So just keep that in mind. We're not going to look at those today, but you can get different diodes that have different forward bias voltages. The other thing to keep in mind with that forward bias voltage is that we're actually going to get a voltage drop over this diode when it's in that, turned on state. And that forward bias voltage is actually going to be that voltage drop. So for example, if we wanted to calculate the current that's going through this circuit, this I1, then we would need to take that into account. Just some really quick math then. If we wanted to calculate that circuit, we're going to have to go this 9 volts minus 0.6 volts divided by the resistance. We're just using a little bit of Kirchhoff's voltage law and Ohm's law here, and we're going to get 8.4 milliamps. If you just do some really quick top of the mind math for this, which is why I use the 1K resistor, if we didn't have this diode here, then we're going to have 9 volts over this resistor. And of course, we're going to have 9 milliamps. So because of this diode, we're actually going to have a small voltage drop and a small little bit of less current than we would otherwise. And depending on your circuit, maybe this really isn't going to matter at all. If we're operating at 9 volts, maybe that's not going to. But for some electronics, especially where we're getting into logic levels at 3.3 volts, then you can start to see how this may be a consideration that you want to think about. Okay, so the next important characteristic that we're going to talk about is if we flip this voltage supply and then we up the voltage. So we were talking previously about how if we put this voltage supply in backwards, we have the polarity swapped, and we have the positive end of the voltage supply hooked up to the negative end of the diode. We have current trying to flow backwards to the diode. It's going to block this current coming through. So in a perfect world, it would just block this for all voltages. In actual real life applications, the diodes, they can only withstand so much voltage before they're going to do what's called breakdown. And the voltage at which they do this is called the reverse breakdown voltage. So on a standard diode, looking at around minus 50 volts. However, this one's, not as standard as that forward voltage drop or the forward bias voltage. So you really should be, if you're concerned that you're going to be getting to this level or you're designing your circuit around this, then it's really important to actually look at the data sheet for the diode and see what this is. And what happens when we go over that breakdown voltage? So if our voltage in is, in the backwards polarity, and then it gets greater than that breakdown voltage, we're going to have what's called the diode breakdown. And what's going to happen immediately is this diode's going to switch basically on and offer almost no impedance or resistance. So we're going to get the current rush right through it. And then generally what's going to happen is it's going to fail. And it's kind of unpredictable about how it's going to fail, but it's probably going to burn up, and it may burn up into an open circuit, or it may burn up into some kind of closed short circuit. It's really unpredictable what's going to happen, but the important thing to remember is it's probably not going to come back from this. It's going to be, broken. It's going to be a burned out component. So we don't want to, for most diodes, be, approaching or going over that breakdown voltage. Now, there are some special types of diodes where we actually can go into or over the breakdown region, and that's actually their design of them. But we're not going to talk about those today, but just something to keep in mind that there actually is diodes that can do this. However, most standard ones, once we go into that breakdown region, they're broken, they're going to burn out and be unusable. So that kind of covers the basics of diodes in a DC circuit. We are going to take a look, though, at how they affect alternating current voltage sources. And to do that, I think it's easiest to jump over into Circuit Lab. So I'm going to hop over to Circuit Lab, and I'll meet you over there. Now that we've popped over into Circuit Lab, let's take a look at how diodes interact with alternating currents. So we'll just start here with our alternating current voltage source. I'm going to drop that in. And we'll leave it at 1 kilohertz sine wave. We'll just leave this all default at 1 volt for now. I'm going to have add a resistor, so we've got a load that we can measure over. And then we will grab our PN junction diode. So that's this one. And we don't need to worry about what that means, but we're just going to put it in this direction with the polarity. And we'll connect these up with some wires here. Add in our grounds. Then I'm just going to name these nodes so they make it a little bit easier for us. So we'll call this one voltage in. And we'll call this one voltage out, or V out. Okay. Now, same as before when we were working with the alternating currents, in order for us to see what's going on with these voltages, we're going to need to run a simulation. So let's do that now. Put this back in the middle. All right, we're going to do a time again, and we'll set this actually, since the waveform is much faster here, we're just going to do 10 milliseconds, and I'm still going to do a 10 microsecond step time here. And we'll click on these here to add our input and output voltages as expressions, and then let's run that time domain simulation. All right, perfect. So let's explain what's going on here. So this blue one again, this is our input voltage. So we just have this perfect sine wave with a 1 volt amplitude, and we'll see, interestingly enough, this is kind of the region where we're actually turning on the diode, and can see that it's actually clipping quite a bit of that signal, because we have that for this diode, it's between 0.6 and 0.7 volts that we're actually clipping off the top. And then once we go into this negative region, we don't get any, because this is where the diode's actually turned on. And then as we go back on again, we are still clipping. So I'm just going to hide this. This is kind of what we expected, and shows how that diode needs that forward bias voltage and able to turn on, and how it doesn't let anything in reverse. Let's just hide this, and then let's jump this up just to get a better idea. So we're going to jump this up to 10 volts here. And then let's run the same simulation. All right, and now we can see how our output voltage for the portions of the sine wave where it's in the positive region, or the current's going in the positive direction, it's more or less unaffected. So we get that positive blip, and then we actually just get it turned off, and we cancel out the negative voltage portion of the wave, or where the current would be trying to flow in the opposite direction. So for these periods here where it's negative, I'll just hide this. We would have the current trying to come back across this diode, and it's not able to turn on. So what this is actually called, really basic circuit, this is called a half wave rectifier, because we have turned off or rectified out half of that wave. Just want to show really quickly just one thing for interest. If I go back to build here, and if we grab a capacitor here actually, and we put it in parallel, we'll just add a ground here. And I'm going to put this up to 100 microfarad capacitor, so it's got a nice amount of ability to hold charge. And if we run this same simulation just really quickly using the same parameters, you can see now actually that we're able to turn this, what was a sine wave actually, into getting close to being a DC signal here. And we're actually able, if we play around with the resistance values and the capacitance values, to get this pretty close to being a DC input. And so this is a half wave rectifier with a capacitor filter in order to make this. And this is actually somewhat of an inefficient way, but really cheap and easy way to turn alternating currents into a DC signal. The reason it's inefficient is because we're just basically wasting all of the power in the second half or the second portion of the period of the wave. But this is a really cheap and basic way that we can create a DC signal. And if you are interested in this or you want a little challenge for yourself, you can look up what's called a full wave rectifier, which just takes a few more diodes and a capacitor. And it's a much more efficient way. So if you're curious about that, I would challenge you to, Google the schematic for that and build it out in Circuit Lab and see how that works. However, for this lesson, hopefully that gives you an idea of how diodes function and why they're so critical in circuits. I'm going to wrap up the video here and I'll see you over in the next one. Welcome everyone. In this video, we're going to be chatting about transistors. So this is actually the last electrical component that we're going to be talking about in the Electrical Engineering for Hackers series, and we've arguably left the most important one for last. I've heard a lot of people say or make the argument that transistors are the most important invention of the last century, and to be honest, I would probably agree with them. More on that in a second. Up on the screen here, I've got the schematic representation or schematic symbol for one specific type of transistor that we're going to look at in this lesson. And I've got two through-hole components of it right here. This one is for larger power and current, and it's got a heatsink. And then this is just a very, very common through-hole transistor style that you would see. And then, of course, these also come in a surface mount design. So in addition to those packages where we would actually be putting transistors into a circuit or onto a printed circuit board, we also use transistors to make up the inside of, processors. So inside, your computers or your phones and the integrated circuits or processors in there, they are made up of millions to billions of transistors, which is actually kind of mind-boggling. And to just kind of demonstrate how many they are, I've got a chart up here of Moore's Law. And Moore's Law, it started out as kind of like a theory, but has turned into a law over time. And it basically just says that every year, the maximum amount of transistors that we can fit on one of these ICs or a single wafer of silicone, the material that they're made out of, is going to double. And it became a law because over time that actually did hold true. And you can see we've kind of got this linear progression over the years of the amount of transistors we can fit, all the way up to, this goes into 2018 and we're at about 50 billion here. And now 5 years later, I think we're actually close to 600 billion that we can fit, which is pretty insane. And the reason that these transistors are so important and allow us to make these computations in the CPUs or processors or these ICs that they're in is because one function of transistors is as a switch. And of course, switches are a very good way for us to electrically represent a 1 or a 0. They're either on or they're off. Now, this is an extremely complex subject, chatting about the construction of processors down to this level. And we're not actually going to dig into that in this course. I just wanted to kind of show for interest and also my explanation of why transistors are so important, just give you an idea of how they are used. So we're actually just going to be looking at one specific type of transistor in this lesson, and it is called an NPN bipolar junction transistor. You'll hear that referred to as BJT for short, and we'll chat more on what NPN means in just a second. Now, one of the things you may have noticed with the transistor that's different from all of the different circuit components or electrical components that we have looked at so far is it's actually got 3 leads or 3 inputs to it. With the other items, like, for example, the resistors or the capacitors or even the diodes, all of them just had the 2 leads, and we inserted them in our circuits so that, they would have an input from one end and an output from the other. And we'd have either a current or voltage come through them, and they would, change that in some way, and it would come out the other side. So at the most, all we really needed to do was possibly label the polarity of our leads, one positive, one negative. So now that we've got 3, this actually completely changes how this circuit componentry works. And in order to keep track of the different leads, we actually name them. So in this layout, this NPN BJT, we have the top one is called the collector. The middle is called the base, and then the bottom is called the emitter. So before we dig into what these specific pins do, I just want to give a quick overview of what the two basic functions of a transistor are. So the first main one that we already talked about is we can use it as a switch, and we can use it as an electric switch. So by varying the voltage that goes to the base, if we think of this as our switch or a valve, we can open it up all the way and allow a current to flow through. And there's a lot of advantages to this that we'll talk about later. The other thing we can do is use it as an amplifier. So to use it as an amplifier, what we can do is we can open up, if we think of this as a valve, open it up partially in such a way that if we apply a input signal to the base, we can have that mirrored to a greater voltage and current that is coming through the collector and the emitter. And we'll chat about that more in depth in the coming slides. We're not going to get fully into the nitty-gritty of how transistors work, but we are going to take a look at some circuits and talk more in depth about these two functions. So if past this, all of that isn't making sense, really the most important and two critical things that I want you to take away from this lesson is just that to remember these two basic functions of the transistor, and when you see them on circuits, you'll know that they're going to be performing one of those two functions. Before we get into looking at some circuits and how these transistors actually work, just a quick note on some other schematic symbols that you might see. So I chatted previously about that last BJT transistor was in the NPN configuration. Well, we also have what's called the PNP, and you'll see that we've flipped the emitter and collector. And these function fairly similar to the NPN transistors. A really oversimplified way of saying it is that they just kind of work backwards to them. And then the symbol that we have over here, this is for what's called a field effect transistor. And we're not going to actually talk about those in this lesson, but I just wanted, in case you run across a symbol, to understand what they are. And they have their own different designations for the pins. So the top one is the drain, middle one is called the gate, and then this bottom one here, S, is called the source. And you might hear these referred to as MOSFETs as well. And that MOS, it just stands for the what they're manufactured of. Again, we're not going to talk about these anymore in depth in this lesson. I just wanted to make sure you were aware of, if you saw the symbols for them, that these are what they are. So as long as you understand the core functions of a transistor and what they do, then that core functionality or concepts, they're going to apply to these as well. And then it's just really the implementation of them that's going to differ. One of the best ways that I find to describe transistors and to visualize how they work is to go back to this water analogy. And I've got our transistor up here on the screen just so I can set up this analogy and we can see what the different parts of the transistor and circuit are with regards to our water analogy. So the first part is our voltage supply here. We've got this giant tank with the water held up high. That's going to represent our voltage that will allow this water to come down through this pipe. Second thing is we've got this other big container here. We'll think of this as our ground that can, receive an infinite supply of this water. At the top here, the pipe that's connected to the voltage supply is our collector. And at the bottom, this section of the pipe here is the emitter. And then we've got this valve in the middle that I'm going to call the base. So if you think of this as if we turned it kind of like you would open your hose, then that would allow this valve to slide open and let some water through. Now we've got the analogy set up, I just cleared the arrows away to make it a little bit easier to see. So if we were using this transistor in its switching format or as a switch, then what we would do is apply a voltage to the base, and we would apply that voltage in such a way that it's going to cause the base to fully open up its valve. So when we do that, of course, all of the water is going to rush through this pipe and it's going to go down to the ground. So if we compare that to our transistor here, we apply that voltage, and we'll chat about what that needs to be later. But when we apply the correct voltage, that's going to put it in what we call the active region and fully open. We can think of that as, if this was our valve, it's going to fully open. And instead of water, we're going to get the theoretical maximum amount of current that's going to be pulled from our voltage source down to the ground. And of course, the amount of current is going to be dependent on how we design our circuit and any resistors that we place in the way. So that's how we use it in the switching setup. So the other setup is that we can actually use it instead as an amplifier. And you'll see here, I've changed the image so that, we've cranked this open, but we've only cranked it open halfway. And this is how we use it as an amplifier, because there is a region of operation of the transistor that we're going to chat about a little bit more, where depending on the voltage that we apply here, it's only going to open this flow partially, and that is going to be proportional to the voltage that we input. And that's how we use it as an amplifier, by kind of sliding open and close this valve to let a certain amount of that water or current to come through that is proportional to the input, but of course much bigger in scale. So with that water analogy out of the way, let's take a look at kind of like a pseudo circuit of how we could, use a transistor to do this. And I'm going to call this a pseudo circuit because we have no resistors yet in our circuit here, which you would generally want to add some in, because if you actually were to, hook up your transistor like this, then it would actually just catch fire because there would be no current limiting. We get infinite current and it would just burn up our transistor. So what I've done is I've hooked the top of our transistor to VCC. And we haven't really chatted about what VCC means, but you'll see this on a lot of electronics schematics. And what that means is it's like the nominal operating voltage of the circuit. For example, the power supply to our router is 9 volts. So the VCC for that, or the standard operating voltage, would be 9 volts. And then this VN, we're just, this is just a signal that we're going to be taking into the base. Okay, so I've added in a couple voltage nodes here just to make it a little bit easier to understand how this transistor functions. So the first one here, this is the voltage at the base, and then we've got the voltage at the emitter here. And if we were to measure the voltage in between these, it's called VBE. Now, when you look at this transistor, you may have noticed that this symbol, it kind of looks like a diode right here. And that's because for the operation of this transistor, we actually can think of this as being a diode. And the way that transistors actually are created is kind of similar to putting two diodes together back to back. And then the voltage that we apply to the base of it, it will actually change the function of this diode and allow current to come through. So you may recall from our previous discussion on diodes that there is this forward bias voltage that we need to surpass in order for that diode to open up. And that's how we use the transistor as a switch. What we need to do is set up our circuit such that this V in is going to cause the voltage at the base to make this VBE be greater than whatever that threshold is. For most transistors and diodes, it's around that 0.7 volts or 700 millivolts. And once we go past that region, it's going to fully open up this section of the circuit, and it's going to allow our current, that's being driven by this VCC voltage, to flow through our circuit. So for a switching circuit, what we were just talking about, the thing that we have to remember is that we design the circuit such that this VN, it pushes the VBE into what we call the active region. And that active region of the transistor is when it is fully open. So for amplification, the one thing that you may recall from our diodes lesson is there's actually a region of operation of the diode where it's not actually fully open or fully closed. It is, partially open. And in this region is called the saturation region. This is how we can do that amplification that we talked about, where varying this input voltage is going to vary the amount of current that we allow through this diode. And in order to do that, what we have to do is we have to design our circuit, so for an amplification circuit, such that this VBE fluctuates in the saturation region, or in that region where the transistor is going to allow an amount of current to flow through that's proportional to the signal that we input. And the way that we actually set up our circuit to do that and to hold this VBE in that 0.7-ish range is that we do what's called biasing the transistor. And we do that by tying the base up to the VCC through a set of resistors. So if we need to divide the voltage, or just straight through a resistor, and we have some voltage drop over that resistor, and we can then tie this VBE to that saturation region. And then our voltage signal can just ride on top of that and cause that fluctuation that allows us to have the amplification. Now, the design of circuits around transistors and biasing them, and the different configurations of hooking them up, it actually can get quite complex. And I'm not going to specifically go into that in this course because, as hardware hackers, I think it's really just important for us to understand kind of how these transistors are used, and when we see them in the circuit, we can understand that, okay, yeah, this is being used as a switch or this is being used as an amplifier. We don't actually specifically need to know how to design them. Now, if you do want to learn this, then that's great. And there are a lot of awesome resources on the internet for them. However, for our example, I think, taking it to this point is good enough. With that being said, what I am going to do now is I'm going to hop over into Circuit Lab, and I will create two circuits, actual circuits with resistors and signals to demonstrate how we can actually build out an amplifier or a switch. So I will hop over there now, and I'll see you there. Welcome everyone. So that last video on transistors was getting too long to be one lesson. So I split it into two videos, and in this video, we're going to take a look in Circuit Lab at some transistor circuits. So without further ado, we'll jump right over into Circuit Lab right now. Okay, so this first circuit that we're going to take a look at here is just really a demonstration one to show how we can actually drive this transistor into the active region. It's not really a good representation of how an actual circuit would work, but I think the outputs from it really help to understand how changing this input voltage can actually trigger or change the amount of current that we let through. So just to really quickly show what we've got going on here, we've got our voltage source up here at 24 volts, and we've got a current limiting resistor here. And if we look at just at DC, we can see that we have 237.3 milliamps. So the reason we don't have that full 240 milliamps is that's because we actually do have a small voltage drop, what's called the VCE, or the collector to the emitter. And if we hover over the transistor, we can actually see that that is 265.1 millivolts. So that's where we lose that little bit of current from. Just keep in mind, so theoretically, our max current that we can have come through is that 237.3 milliamps. Now, I've got a node here representing the base voltage, and we can see here I have applied this signal voltage, and it is a sine wave at 1 kilohertz. Now I just click on it quickly so that we can see the properties of it. You'll notice I have a 5 volt amplitude, but I do have a DC offset of 5 volts. So just if you're following along, the reason I've done this is that way it's not actually going to bounce from minus 5 volts to 5 volts. I just want this to actually start at a positive value and only stay in the positive range, because it really helps to demonstrate how this transistor functions. And what I want you to think about is, this is not an actual representation of what you would see in a real life circuit, and don't really think about this as like a signal or anything we're trying to amplify. I really just wanted an alternating current that shows what happens with our transistor and how we can use it in this switching region as the input voltage changes. So let's take a look with a quick simulation. So let's leave these parameters here. These are the standard ones we've been using. And then what we're actually going to be plotting is, I'm curious about the current that we can have come through here, and then also this base voltage. All right, so let's just run this time domain simulation here. Perfect. So this gives us actually a really great representation of how the voltage change is actually going to, open up this transistor. So we start here, because of that offset, we're actually starting at 1.2 volts. But we can see at 1.2 volts here, we're at that theoretical max of the current that we are going to be letting through. So that's at that 237 milliamp region. And of course, as our voltage increases over time, we're still over that region that's going to open up the transistor. And as such, our current is all the way at that 237 milliamps. And then you'll notice here, once we get right around this region, right here, right around 700, that 700 millivolts or 0.7 volts, we actually drop off. We drop off very quickly. And once we get below that 0.7 volts, our current is all the way down at essentially zero. And as the rest of this signal changes through here, we are at zero. And it's not until we just kind of breach that 7.7 volts or that 700 millivolts that we actually go back up into that active region. And when we're in that active region, so we don't care now that we're above that active region, what that voltage, as high as it goes, we're all the way open already at 237 milliamps. So if I just hide this quickly then, so what that means is that, we have a lot of sensors and outputs from microcontrollers where the voltage, we can control how that changes. And that's really great because then we can design our circuits so that, as that sensor changes or that voltage output from our microcontroller changes, we can use that to drive this and then open it up as we like. I'll give a couple of real life examples here just so it helps make sense why we would actually want to do the switching in the circuit. So the first one is if we take that example of a photoresistor where the resistance value changes based on the amount of light that's shining. Well, we could make a light that turns on once that photoresistance value gets below a certain level. And this is how a lot of light sensing circuits work. And in that scenario, then once the resistance value is changed enough by the light, we would design our circuit so that it will fully open up the transistor and then it can power a light and turn on that light. Another example is if we actually think about that smart lock that we were talking about in the very first section of this course. If you enter in your PIN to the smart lock and then it's going to unlock, there's likely going to be some sort of microcontroller or microprocessor that's going to have some logic that it outputs on a pin, that digital out as a high or a low. That means that the lock should unlock. And when we do that, the current and voltage that's going to come out of that microcontroller or microprocessor is not going to be powerful enough that it could actually drive any kind of mechanical movement where we actually need to, physically move something to unlock that door. So one way that we could do that is with a transistor and have the transistor and, this VCC or whatever this voltage be set up so that the current and voltage that's supplied when it's in that fully switched on mode would be enough to drive that mechanical motor or whatever we need. And then we tie that pin from the microcontroller down to the base of that transistor, and we design our circuit such that when the logic says that the correct pin is open, it will set the voltage to open up that switch. All the current will come through and drive that mechanical motor. And that's how we do this actual switching. So again, in this example, don't think of this as an input. I just really wanted to show how that voltage changing over time can impact the transistor and cause it to kind of open and close in that switching region. I'm going to just open up another circuit here and we'll take a look at a very basic amplifier. Okay, so I've got another basic circuit opened up here, and this is what we call a common emitter amplifier because we actually just have the emitter of this tied down to the common ground. And we're looking at this circuit, and it can be a little intimidating looking at it at first. So what we'll just quickly do is break it down into the few different regions. So what we've got here is this is actually the sign voltage is representing an input voltage that we would be measuring. So if we just take a quick look at it, you'll notice that I actually have the amplitude set at 5 millivolts. So this is a very, very weak signal, and maybe it would be something that would come from like a microphone if we were measuring sound through a microphone. You'll notice we have this capacitor here, and we already talked about capacitors. And the reason that we have this, what's called a coupling capacitor here, is because we want to set this VB so we're in that saturation range. And in order to do that, we can't have any fluctuations in the voltage other than what is actually coming from this sine wave. Now in Circuit Lab, this doesn't really matter because this is actually like a perfect sine wave, but in reality, we might have some DC leakage coming in, and we want this capacitor is just going to block all that from coming. So the next section of the circuit we'll look at is this one right here. So we're actually using 5 volts as our VCC here. So what we're going to do is we're going to amplify this 5 millivolts with that 5 volt signal. And in order to get this VB so that it's going to be sitting right around that 700 millivolts or 0.7 volt sweet spot, we're going to steal some of this voltage up here and tie it down here. And that's where this RB or the base resistor comes in. We also have this RC, which is the collector resistor, and this is what's going to set the amount of current that comes through here to amplify. And if you want to learn more about how to calculate these to get it in this region, then there's lots of really good videos or resources about that, but this would turn into a really long lesson if we talked about that. So I'm just going to leave it at that. These values, I've pre-calculated them using some formulas and some characteristics of this transistor. And if we really wanted to go into that, it would make this video way too long. The last section of this circuit here is just this one where I'm simulating a load with this resistor, and I'm coupling again with a capacitor to remove the DC bias from the circuit so that we're actually only getting the pure AC signal coming out. So if we run this simulation, let's just run a time simulation. And because we've got some capacitors, I want to look at it in its steady state and ignore the initial power on of this circuit. So I'm just going to start at 100 milliseconds and then go from 100 milliseconds to 110 milliseconds. And we'll still use that 10 microsecond step. And we're going to take a look at the output voltage, of course. We'll take a look at the input voltage, and then we will also take a look at the base voltage. So let's run that time simulation. And this one's just going to take a little bit longer since we're starting at that 100 milliseconds. Okay, so this graph is actually a great representation of how our amplifier works. Now, the one thing that I should mention is that a common emitter amplifier is actually what we call an inverting amplifier. And what that means is that our waveform is going to be flipped. So here, when we're at our peak of our input, you'll notice that we flipped it and we have a negative here. And if this is going to be a problem for our circuit, depending on our signal, some signals it is, some it isn't, what we can do is we can add another transistor that we can flip it back again as needed. But for this one, just to keep it simplified, we'll just look at it in its inverting state. So this orange signal right here, this is our input signal, and we can see how weak of a signal that is. We just have that 5 millivolts peak, and it's honestly so weak we can barely even see it on this graph. So what I've done here with the transistor base voltage is we can see how by pulling it up into that 730-ish millivolt region, or that 0.7 volts, is putting us right in that saturation sweet spot. And we're just riding right around where we're able to partially open and close that transistor. And what that's doing is it's allowing a portion of that VCC voltage to come through. And you can see by doing that, we've actually amplified. If we look at our peak voltage here, right around that 5 volts, that's about as close as I can probably get it. So we're going from almost 5 millivolts to about 710 millivolts. We're looking at about 100, almost 140 times amplification, which is pretty good. And I think right around the maximum of what this transistor is capable to do. So this is how we can use these transistors to actually, bump up weak input voltages from our sensors, and we can actually then, make them more useful to read them. So hopefully this gives you a little bit of an idea about how transistors work. Again, this is a very complex subject, and you could spend a lot of time, hours and hours even learning about just the basics of this. So if there's really just, 2 things you take away from this lesson and that's it, it would just be to remember the 2 basic functions of transistors, in that we can use them as a switch, so we can take a smaller input voltage into the base and then have them to control a much higher voltage and current, or we can use them as an amplifier, again, to put a weak signal or lower voltage signal into the base and then have that partially open up and close the transistor in such a way that we can create an amplified version of that signal passing through the transistor and use that to amplify weak signals. So that wraps up our lesson on transistors. I will see you over the next one. Welcome everyone. In this video, we're going to be talking about electronic communication and signals. So right now, for you to be watching this video, there is dozens and dozens of different electronic communication and signal paths taking place. Of course, the obvious one is that we've got the network traffic going over the internet and streaming this video data. However, also internally, if you're watching this on your computer or a tablet or something like that, on the motherboard of your device, there is all kinds of different communication signals that are taking place just internally between the different componentry on your device, and then also out to your monitor, for example. So we can split up electronic communication and signals into two main categories. And the first one is as analog signals. And we're not really going to focus a lot on them, but I just want to make you aware that this is one way that we can actually do communication. So here's an example of one of the analog signals that we were talking about previously. And we'll just say that it varies in voltage and also frequency to represent a sound signal. And the way that this works is with a microphone, the vibrations that sound make can actually then be translated into a varying voltage, and the amplitude and frequency of that signal changes with respect to the sound. And then we can actually play that back through a speaker, which is just actually a microphone in reverse, and it will play that sound. And we can transmit this signal over a wire and have someone play it back to themselves. So this is like one of the very earliest types of analog communication when we first invented the phone, and it was as basic as that. We may have some components in between to either amplify the signal, like transistors that we were looking at, or other amplification devices, and maybe some capacitors or other things to do filtering. But the signal is continuous, and there's no designation of anything like bits or anything like that. We just have a continuous voltage signal. So for this course, we're not really going to be working much with analog signals. We're going to be more concerned about those signals that are actually internal to our devices and going between the different componentry. And those will generally be digital signals. And we've looked at this already. Instead of, having this continuous sine wave that represents some sort of signal, we use a square wave or an on and off pattern to toggle the voltage between some low value and high value. So generally that would be like 0 volts and then 5 volts. And if we're reading on that line, then we read at 5 volts, we know that that is a 1. And if we read the low, then we know that's a 0. And this is really the basis for all digital communication. Even if, we start thinking of like these higher up, more advanced protocols, if we peel them, all the way back down to at the very, very most basic level, even if you're thinking of, for example, the OSI model, if you're familiar with that at layer 1, then this is really just, voltages on a line or voltages on a wire. And this is one of the important things that I want to drill home for hardware hacking. We're kind of getting into this hardware mentality, is that when we boil these protocols, right down to the very basic, like they're a voltage signal. And, even though it's not analog in the terms of, we have this fluctuating sine wave, this is still a square wave of alternating current, and it still behaves as such. So if we're crafty enough as hardware hackers, then, there's some things that we can do just at the hardware level without even thinking about software, knowing that this communication is actually really just voltages being applied to a wire. So to make sure that we all have a baseline of how these digital communications work and that we can build up on, I want to just introduce, and maybe we can try and come up with our own very, very basic method of doing digital communication with hardware. So I want to introduce just, a super basic circuit here. This is our voltage rail, and I have it labeled as VLH. So that LH, that stands for logical high. So when the voltage is at this voltage level, and we don't really care what it is, it could be 3.3 volts, 5 volts. I mean, we can make it whatever we want because we're making up this, little protocol ourselves here. And then I've got a switch. We've got a resistor here, of course, just because we don't want to have voltage without a resistor, then we're going to be putting way too much current through and burn out the wire. We don't really care about what the resistor is, but that's why it's there. We have a switch here, so we can toggle on and off that voltage. And then we have this receiving pin that we can put out. So it would be transmitting from this end, and then someone could hook up even just a multimeter to this and read out. And then if we go slow enough with our switching, they could actually decode our message. So let's pull up a graph of what this receiving pin would look like. I'm just graphing this, really basic over time, the same way we've been looking at it. So this is the voltage at this pin here, or this output. And then I just have this labeled as this logic high to make it really easy for us to read when we have ones and zeros. So if we close the switch, then we know just, really basic Kirchhoff's voltage law. Then what we're reading out here is going to be the same as this VLH. So of course we get our voltage up here, and the person who's reading on the other end can say, yep, okay, we've got a 1. And then if the next thing we want to transmit is a 0, then we just throw open the switch And you see here, our voltage drops down to 0, and we know we've got a 0. So the great thing about this is that, all we really need to exchange at this point, or all we have, is that we'll just determine what we're considering to be a high and a low. So in our example, we're saying that, this VLH, whatever it is, be 3.3 volts or whatever, that's going to be our high. And then if we get a 0 volts or around 0, then that's going to be 0. So in reality, we'll generally have two thresholds, an upper limit threshold and a lower limit threshold. And when we go above that upper limit threshold, that will be considered a high. And when we go below that lower limit threshold, that will be considered a 0. And this just gives us some breathing room in our circuit if we have, any tolerances or things like that that throw off the voltage levels. I just left them out of this because I think it's cleaner to look at it like this. We'll just assume that we can do those perfect voltage levels. Okay, so in this example, what happens if our transmitter, so whoever's operating the switch, has decided they would like to send another 0? So they leave the switch open, send another 0. Of course, as time passes, we still are just at that 0 volts. Whoever's reading, if they're just doing, the most basic reading ever, they just have a multimeter here, they're still reading 0. How do they know that I'm sending another 0 and not, it's just a continuation of that same 0, right? So when we look at this graph, it's kind of obvious because you're saying, well, we held this 1 for the same amount of time, then we held this 0 for the same amount of time. So it would be assumed that this would be held for the same amount of time. And really, that is the foundation of how we're actually going to get past this issue, in that we're going to set a specific amount of time that we're going to hold each symbol. And that is called the symbol duration. And we represent that generally with this T subscript S. And what that really says is just, each time I transmit a symbol, in our case, it's just going to be bits, so a 1 or a 0, I'm going to hold that for a set amount of time. And that way, if I transmit, multiple of the same symbol, one after another, and you kept transmitting zeros, then the person on the other end is going to be able to decode that. So for example, if we're just, really basic math, every second we're going to send a new symbol. So the person on the other end would go, 1 second, that's a 1. Next second, that's a 0. Next second, that's another 0. When we set up these parameters and, exchange that we're going to be communicating with these different symbol durations, we generally don't actually say the symbol duration. And the reason for that is these get, very quick. We're not going to be doing 1 second. It's going to be down, into the milliseconds or microseconds. So we're not going to say, for example, the symbol duration is going to be 0.1 microseconds. So instead, we'll generally communicate this to be the amount of symbols per second that we can do. And as long as we're measuring our symbol duration in seconds, then to get that, we just go 1 over the symbol duration. So 1 over T subscript S. And the name for this, there's actually a name for this, we call it the baud rate. So the baud rate is the amount of symbols per second. Now, in our example, again, our symbols are just 1s and 0s. So we could call this a bit rate. And sometimes you will see it referred to as a bit rate because realistically now in modern communication, it's pretty much always going to be 1s and 0s and bits. But the industry standard is still usually to call it baud rate. So keep that in mind. I'm going to use baud rate because that's what you'll usually see. You may also see it referred to as speed or the communication speed. So just keep that in mind that you may see either one of those. Okay, so just to bring this full loop, now that we've kind of established what our communication protocol is going to be, and that we're going to send, one bit, one after another, and we're going to have a high voltage level represent a 1, a low voltage level represent a 0, and we're going to send each bit with a specified duration. So we can just say 1 second here, and I put these ticks on the graph to separate that, so we can think of these each as 1 second. So let's say we want to transmit high. This T subscript X, that stands for TX, and then the same for RX. So the way that we can do this is we can send, H and I as ASCII characters. All right, so the ASCII representation for H in hex is 0x48, and then if we convert that to binary, then it's just 01001000. So I can transmit onto that line out like an actual, low voltage level, high voltage level, low, low, high, low, low, right? And you're getting the gist. And then the person reading that is able to, read that, and then they can decode that back from that binary to the hex to the ASCII and see, okay, that's an H. And then we can send an I. So the hex representation for I, 0x49. Again, we're just adding one bit to this. So we're just going to be adding a 1 on the end. We can just transmit this again, right? And then the person receiving, they'll receive that as an I, and we have sent a very basic H and I. When we're sending data like this, 8 bits, and we're sending it grouped together like this for one representation, then generally what this is referred to in this digital communication in this basic format like that is called a frame. So if you're familiar with networking, then you've maybe heard of a packet. So at layer 3 at the network layer, what we call like that grouping of data is a packet. Well, at layer 1, it's actually called a frame. And then even outside of the OSI model, just at these basic communication protocols where we're just looking at the voltage on a line and then building up off of that, this grouping of data we call a frame. So for those of you that are following along at home, you may have noticed that we still have some glaring problems in our communication protocol. The first, and maybe most obvious one is if, let's just say I'm sitting in one room, someone else is sitting in another room. We've run a wire to them, and I have a switch that I'm going to open and close it, and they're sitting on the other end, and they've got their multimeter, and they're going to measure the voltage. And when they see that voltage high on the multimeter, whether it's 5 volts, and then when they see it 0 volts, they're going to know it's a 1 and a 0, and then they can decode that. So as a good example, our very first symbol or bit that we want to transmit is a 0. Well, how do they know that I'm starting to transmit? I mean, if I'm just sitting here with the switch open, am I sending zeros all the time? When does the transmission start? So there's one problem. The other problem is, how do we tell when a frame ends, or like how long a frame is? Is it always going to be 8? How are we going to determine that all of this is the H and then it doesn't flow into this one? And then also, what if that person wants to send us back? We just have this one wire now. So, I mean, we're going to add a second wire. Are we going to, have some sort of way to say, I'm done with the line, it's your turn? There's a lot of different things that we need to kind of sort out. And this is where the various different protocols that communicate in this method are going to come in play. And they all have their own ways that they kind of solve these issues. And we have predetermined things that we agree on or, set ahead of time between the receiver and transmitter in order to fix these issues. And we're going to build on, these very basic core concepts of our baud rate and this voltage and toggling the voltage on the line throughout the rest of the course when we look at those. So the other glaring problem that we have, and this is just kind of a problem with this style of transmission, is that we're limited to just sending this one bit one after another. And when we do that, what this is called, and you've probably heard this before, is this is called serial communication. And that's literally what serial means. It just means we're sending one bit or one symbol one after another. And this brings us to limitation of speed. We're really just limited to how fast we can actually, turn on these symbols on and off. So in our example at 1 second, like that's horrible. It'll take forever. But even, as we increase the speed to what is really, capable of devices to be able to read and transmit, it's going to become a limitation for bandwidth that we just have to send all these symbols one after another. So what we can do to get around that is we can use what's called parallel communication. And in parallel communication, instead of us sending, on one line, one bit after another, we can open up multiple lines and we can send, all of that information in parallel to each other. So that's why it's called in parallel. So if we just take our example again, where we want to say hi. So first we're going to send the H. So before we decode this and actually look at these voltage levels, the other thing with parallel communication that I want to bring in is, before we were using a speed, but what happens, if we say we're all at a speed, but what if we don't start at the same time, right? Then we can start to get our pulses of communication be off from one another. So in parallel communication, we also always will generally bring in a clock, and that clock will allow us to synchronize and make sure that all of our communication pulses are together. And the way that the clock works is going to differ between, different protocols. But in this one that I'm just kind of making up to demonstrate how parallel works, we'll just say that we're going to sample on the rising and falling edges of the clock. And you'll notice that the clock is offset from the actual communication. And that's so that we're going to force it to sample in what would hopefully be the middle of a transmission. And this way we have the best chance of actually being able to capture what, each of these symbols are supposed to be, because if it's shifted, left or right a little bit, that's still going to be okay. So on our rising edge of the clock, we would sample that. And in here, we're going to get, of course, that 0, 1, 0, 0, 1, 0, 0, 0. And that's going to make up an H. So instead of, us sending it one after another, if we were just using one channel, instead we've sent them all in parallel. And essentially, even if we were doing this just at 1 second, we have times 8 our bandwidth, right? Or times 8 our speed, because we can, send this at one time. And if we want to send our I, then on each channel, we would then resend our bits. Again, we have 0, 1, 0, 0, 1, 0, 0, 1, and this would make up an I. So the main difference between parallel and serial that I want to make sure everyone understands, because it can kind of get a little bit confusing for some of the serial protocols, is that you will see them start to have, multiple lines, and they still may use a clock for synchronization. But the really big differentiator of what still makes those serial is that even if we had 4 channels, and we were talking serially, each of those channels would send all of their data or their frames on one channel. So, channel 0's data would not be intermixed with channel 1's data. Whereas in parallel data, each of these frames are split across each of the channels. So this whole frame is taken up by all of these channels, and that's what is considered to be this parallel communication. So in this course, we're mostly going to be working with serial communication. It's actually still, very, very commonly used for a lot of protocols, and especially the protocols for our different components and chips on our device to talk to each other. That wraps up this lesson and actually wraps up our theory section for electrical engineering for hackers. So I'll see you over in the next section where we're actually going to look at our very first serial protocol on our board. And we're going to hook up to that and start doing some readings on it. So I'm looking forward to that. I'll see you over in the lab when we take a look at that. Hey there, hope you're enjoying the course. We'll get back to it really quickly, but before we do, I wanted to call out again to just make sure you are subscribed both to my YouTube channel, which I'll link down below, and also to the TCM Security YouTube channel, this one that you're watching the video on. So I would really appreciate it if you just take a second and check, make sure you're subscribed, and if not, hit that subscribe button for us. Thank you. Welcome everyone. In this video, we're going to be continuing on our learning about digital serial communications by taking a look at UART. So UART is a type of circuit or a functionality of a piece of hardware that allows us to do asynchronous serial communication. UART itself is not actually a protocol. All it does is it just sets out a method that allows us to asynchronously basically transmit ones and zeros using electricity between either 2 circuits or 2 pieces of hardware. So we're going to start today's lesson by taking a look at what UART stands for and how the connections for it work. And then the rest of the lesson is going to be hands-on, which is why I've got the router and the multimeter here. So if you are following along at home, you'll need both the router and multimeter, as we're going to then be taking a look at how we can identify the UART connection on this router and verify the pinout for that connection. So I'm just going to move these to the side for a second here so we can chat a little bit about UART. UART stands for Universal Asynchronous Receiver Transmitter. And I'm just going to chat quickly about what each of these words mean in our acronym here. So universal, that's because this is a universally and widely used method for asynchronously transmitting serial data. It's very, very widely used. It's quite an old method, but you will still see it frequently used on electronics and come across it in hardware hacking. So asynchronous means that we have no clock synchronizing between our 2 devices that are communicating each other. So the transmission and receiving do not have to happen on a clock signal, and there's no shared clock. What we do need to do, though, similar to that previous serial protocol that we were kind of making up in the last lesson, is agree on a baud rate or speed that we're going to be transmitting at, so the receiver can then decode those transmissions. And then the receiver transmitter, this one's pretty straightforward. It just stands for that the devices are able to both receive and transmit. Now I've drawn out 2 devices here so we can look at the pinouts for standard UART and how they're connected. So I've got device A here and device B. So generally with UART communication nowadays, it's going to be handled by a functionality of a processor or some other integrated circuit. So that's why just at its very, very base level, I've drawn these as chips, 8-pin chips, and generally you're going to have many, many more pins on the chips, and you'll have to look at the pinouts for them to see what pins are used for UART. And just to simplify it, I've just drawn it as these 8-pin chips. So just to keep in mind also, when you're looking at this on a circuit, generally you're going to have this soldered to a PCB, and then we'll have traces that go off somewhere, maybe to a header or other connections for these pins. So UART generally is going to have 4 pins, and they're going to be the TX pin, and TX stands for transmission, the RX pin, where RX stands for the receiver, then we'll have a ground and a VCC. So just like the TX pin you would expect it to be, this is the pin that transmits out. So if we want to send out our serial communication, we're going to send out those voltage levels and those voltage pulses that we looked out on the transmit pin. The receive pin is we're just going to listen on this pin and measure for changes in voltage levels. So if we are to hook up another device's transmit pin to this receive pin, then we're just going to sit and we'll hold this voltage level low here on this until another device is going to put it high, and then we can read. We have a ground because for this serial communication to properly work, we need to make sure that both the devices are sharing a common ground. And the reason for that is we need to make sure that both devices are able to accurately measure what that high voltage level is. Generally it's going to be 3.3 or 5 volts. So let's just use 3.3 volts for this lesson. If this device is going to be transmitting and reading 3.3 volts, we need to share the same reference to measure it from, so they're both on the same page. Finally, we have this VCC for supplying power, and this is generally not used, especially in hardware hacking, but where we can use this is if we need to supply power from one device. So for example, the device A to device B, we could hook this VCC pin up and then supply power to a device that doesn't have its own power supply. So an example of where you might use this is if you have a sensor or something like that that's using UART communication to send back its data, and it's just a small sensor, doesn't have any power, then we can hook up the VCC and grab some power off that. So I'll just really quickly draw up the lines here to show how generally we hook up 2 devices. The transmit from one device, it actually goes not to the transmit of the other device, of course, but it goes to the receive. So it's going to go to the receive here. And then the opposite is true from the other device. Transmit would go here, and then it would come over to this device's receive. We're going to hook the grounds together. So that one's nice and easy. And then the VCC, I'm just going to draw an X here, and generally what X stands for is no connection. So we don't actually need to connect those on most applications, and for what we're going to be doing in this course, we can just leave the VCC unconnected. So just one other quick note here on the transmitting and receiving functions of these devices. Depending on how the designer of the software that's running on these devices and the circuitry that they are using, sometimes they'll only just be designed either to transmit or receive. So for example, maybe we don't want to actually take in any commands or anything like that on the receive pin. So it will either just, it won't be connected at all to a header, or maybe the software is just going to ignore whatever is on that pin and will only just transmit data out. And the opposite is true. Maybe we won't actually transmit anything out and we're just going to be listening to receive data. It's also up to the designers of the circuit to determine whether or not we're going to allow both devices to communicate at the same time. So UART will allow for this just on how it's set up, and with having these 2 separate lines, we can actually have both devices, so device A and device B, transmitting and receiving at the same time. However, it's going to depend on how the software is set up, whether or not what is going to be expected is, for example, for device A to send out a message and then it won't transmit. It will wait until it receives some sort of message back from device B. Some protocols enforce this, but remember, UART itself, it's not actually a protocol. It's really just a method for us to essentially send ones and zeros from one device to the other device. And then what we do with those ones and zeros is really up to the designers of the circuit, whether or not they build a protocol out on top of that, or they just use it to send raw data or raw messages, like we saw in our last example, where we just used the ones and zeros to send ASCII characters, and that allowed us to send a message. This should give us enough information now that we can set this aside and we can take a look at our router PCB and try and identify the UART connections on there. So when I'm starting to do some initial recon on a device that I'm going to be testing or doing some sort of hardware hacking on, the very first thing I look for is a UART connection. And now to me, they stand out like a sore thumb when I see them, because they're generally a really good source of low-hanging fruit for us, or an easy win to get a foothold or some sort of information from the device. Now, the UART connection here is right here. We've already taken a look at it. And what we're generally looking for is some sort of connector or pads or through hole like we have on this device, where there's 4 of them in a row like this. And that doesn't necessarily always signify it's UART, but it's a really good spot to start. Now on this device here, it's actually really good for us. They've labeled the pin out for us. You can see here we have the VCC, the ground, the RX, and then the TX pins already labeled. So this is a really, really good indicator that it is going to be UART. Now on most devices, they're not going to make it this easy for us. Generally, they won't actually be labeled with a silk screen. So what we need to learn how to do is identify which of these pins are which, and actually be able to check and see if this is a UART connection. And we can do that with just the multimeter. Another thing that I will say also is, even though these are labeled, it's still a really good practice to check our voltage levels and check the pins and make sure they actually match. Later on in this course, we're going to be using this UART connection to connect back to our computer. And when I connect anything to my computer off of circuitry, I really like to check the voltage levels and make sure everything is okay, because I don't want to damage my computer. Luckily, from the previous lessons in this course, we already have all the skills that we need to test these with our multimeter. So I've got it right here. The first thing that we're going to test with it is I've just put this on the continuity setting, and we're going to double check and make sure that this one, which is labeled ground, is actually a ground connection. You may remember we actually already tested this, so we're going to do it quickly here again. But we also identified this little bare metal pad right here that's denoted with, I believe, a P1. This is a ground connection as well. So we can just check the continuity really quickly between the ground and this P1. So for continuity, the polarity doesn't matter, so you can touch either one of the leads to each one, but we need to touch one lead to this P1 here, and then the other one to ground. And I immediately get a beep, so that's perfect. We know that this one is in fact a ground. Now, to test these other pins, we're actually going to be measuring the voltage levels. So what we need to do is go ahead and plug in the router, and I'm going to do that right now. Okay, so I've powered on my device here, and we see that it looks like it's stabilized in its boot up. And I've just brought my multimeter up a little bit closer so that it's in focus and easy to see the voltage we're reading. And I've switched it to the DC voltage setting here at 20 volts. So you'll want to do the same if you're taking this measurement. And the first thing we're going to check is the VCC voltage. And what that's going to do is give us an indication of what voltage level the UART is operating at. We're expecting to see either 3.3 volts or 5 volts here. So to measure that, again, we can just do from the VCC pin here with the red lead to that same ground that we've been using. And if I hold this on here tightly, we get that perfect at 3.3 volts. Perfect. So we know that that VCC pin is labeled correctly, and we're operating at 3.3 volts, which is important to check. The next pin that we're going to check is the RX pin, and we know that this one should be 0 volts because we're only going to be listening on it. So when we measure the voltage at this one, we're going to be expecting 0 volts. So in the same manner as the VCC, we'll check the RX pin here. Perfect, it's right at 0 volts, and that is what we're expecting. The next pin that we're going to check is the TX pin. So unless we happen to catch a transmission, which is pretty unlikely just during this regular operation, then we're expecting to see this at 3.3 volts. So let's check that now. Perfect, right at 3.3 volts. Okay, so you may be wondering, if these weren't labeled, how can we tell the difference between which one is the VCC and the transmit? So what we can do is we can force a transmission on the board. And the easiest way to do that is actually just to reboot the router, or, unplug the power supply, replug it in. Have you ever watched like your BIOS on your computer? When you're starting up, there's a lot of messages that come through. There's a lot of logging that takes place right at startup. There's a lot of important, messages printed out. And that's the same with this router as well. If we unplug it and then reboot it up, we should be able to see a bunch of transmission taking place. So what I'm going to do is I'm just going to unplug this and then plug it in, and then pretty quickly I'm going to try and probe the transmit pin again so we can catch those boot up messages. And what we'll be looking for is we'll be looking for that 3.3 volts to drop down to something in the 1 volt or 2 volt range. And we'll talk about why that's happening in a second here. So I'm just going to unplug it and plug it back in. I'm going to start probing now. You can see this 3.3 volts is jumping all over the place here. You can see some transmissions happening right there when it drops down. Now, the reason this is happening is, if you remember from when we were looking at the diagrams of that serial communication, when we actually have communication, it's happening very quickly. We have all these blips of ones and zeros. So we're holding the line high at 3.3 volts to send the 1, and then we're drawing it low to send the 0, and so on. And this happens really, really quickly in actual UART communication, especially on more modern electronics. And our multimeter, it's just not fast enough to pick up those changes. So what it sees when it's measuring, and we have those blips of transmission where we quickly switch from 0 to 1 or from 0 volts to 3.3 volts, is we pick up an average of that. So that's why we see it coming down into the 1 point something volt or 2 point something volt during those transmissions. So this is a really exciting finding for us. We visually identified what we thought was a UART connection. We were able to verify the pinout on it with our multimeter. And then during boot up, we were actually able to identify what we believe is a transmission taking place. So what we're going to do in future lessons is look at that transmission and use that to further learn about how UART actually works. I'm going to move the router and multimeter out of the way here because we should probably take some notes about what we found here. Again, apologies for my really bad handwriting, but I just wanted to quickly show you what notes I've taken for here. So we visually identified a UART connection. We tested that the voltage level for it is 3.3 volts. We then confirmed the pin configuration that it matches the silk screening, and then we actually identified a transmission during boot up. So important to keep these notes for our reporting later and keep track of what we've done. And this is a really great finding that we are going to take a look at in more depth in the next videos. So that wraps up this video. I will see you over the next one. Welcome everyone. So before we move on to part 2 of our intro to UART and start looking at the transmission that we actually discovered when we were probing the router in the next lesson, we're going to need to make a slight modification to this router. So you notice the UART connection, if I just bring it up closer to the camera here, our UART connection that we identified in the last video, we just have these through-hole pads right here. And these aren't going to be very good for us to connect to with the tools that we have. So in the next lesson, actually what we're going to be doing is we're going to be connecting this protocol analyzer and talking about it in more in depth. And we're going to use this to be able to check what's going on with that transmission. And you'll notice to connect to it, we've got these female leads here, which they're not going to connect to what we have on the board. And same with this UART to USB adapter here we're going to be using, it's the same thing. So we're not going to be able to connect these directly to the board. And I'll just move these out of the way because we're going to use them in future lessons. So what's happened with this board most likely is that during development and testing, the designers and testers of this board, they would have been using this UART connection to get their logs out and to issue commands to the router and do various testing that they need to do. And at that point, they would have either manufactured it so that there was a header pin connected to this, or they would have just added one themselves. And then once it's gone into production, so we have a production unit here, they would remove this header because as consumers, we're not going to be needing to open it up and use this UART connection. Of course, as hardware hackers, though, we love that they've left this here and we're going to want to use it. So what we can do is we can add in our own header connection to it. And there's two ways that we can do this. The way that I'm going to cover in this video is one way that we can do it without soldering. And then in the next video, what I'll show you, and this is totally optional and up to you if you want to do it, is you can solder the header pins to this. So just a quick note before I get into the details on how we're going to do the method without soldering. I do want to say that it's not the best option and it's not the best way to do this. The reason for that is if we do this without soldering, we're going to be opening ourselves up to potential issues down the road with the connectivity between the header pin and these pads. And this can cause just really annoying nuisances down the road where we're not sure if the problem is with what we're doing and how we're setting up our communication, or if we just have a bad connection here and we're not able to properly transmit those electrical signals. So if you are comfortable with it and up for the challenge, I really do suggest soldering. If you were doing this in a professional capacity, then you would definitely be soldering this. And if you're wanting to get into more hardware hacking down the line, then it's a really good skill and an important skill to have to be able to at least make these through-hole solder connections to either do soldering or remove components by desoldering. So with that being said, you still can do everything in this course that I'm going to be doing with this header connection using the solderless method, as long as you just keep in mind if you have issues to come back and double check that connection and make sure your ground connection and voltages are all still proper. So I'll just set this down and bring over here what we're going to be doing in this lesson. So I've got the header pins here, just a set of really basic through-hole headers, and they come in these strips, and then you just break them down to how many you need. So we'll be snapping this down to the 4 that we need in a second. And then I've also got this twist tie here that it's got a plastic wrap around it, which is perfect, so it's not going to be conductive and mess anything up on our circuit that way. And it's this twist tie that comes with our router, and I have mentioned a couple times to save it. And we're going to use this to actually attach that header down in such a way that it should give us an okay connection. So I'll just set this aside for a second, and I'll bring the board closer, and I'm just going to pull the PCB out of the plastic container. And if I hold it up closer here, just from the edges, you'll notice that we've got this hole. We're kind of lucky. I'm not entirely sure what this hole is here for, but it's drilled into the board right here. And I'll just stick my pointer through it so you can see. And again, down here, it's drilled through. And we can seat those headers in here just without soldering. And if we do that, they're going to be too loose to actually have an electrical connection. But if we tighten them down by putting the twist tie through here, wrapping it around those header pins, and then twisting that twist tie, we can make it so that there's going to be enough of a connection here. And I've tested this quite a few times. And as long as you get the twist tie in here good and you tighten it down, then you're going to be able to get good communication both through the protocol analyzer and to the USB to UART adapter that we're going to be using later. So I've already used these a couple times, and so I've snapped them off. So they're a little bit shorter than how they come, but it's going to be the same idea. What you can do with them is they are perforated, and you just grab them and snap them to the length that you want. So we're going to use 4 for this. You may recall that we only actually need 3 of the pins, but the more we have, the better connection physically to the board we're going to get. So it's better to use that extra one, even though we're not going to use it. So I'm just going to grab it here, and I put my thumb, if I just cover up 4 of the pins, and then just put the pressure on it there, it snaps right at 4. So we've got that 4 pins here. And I'm going to take these and just slide it into the holes to start with in the connection. And it doesn't matter what the orientation of these are. It can go either way, but you're going to want the longer ones on the top and then the shorter ones in the bottom. All right, so I'll just drop them into this hole here. All right, so if you're following along, and then if you do this and you notice, like, they're really loose. They're not, like, I just touched them and they fell out. So it's not going to be sufficient for us to have any type of electrical connection. The one thing I want to show here now, and is if I just tilt this a little bit here, what you're going to want to do to get this connection to be good is you're actually going to want to tilt these on an angle just a little bit like this, like I have here. And the reason for that is I'm just going to set this down. So I'm just going to show kind of with my hands what I mean by that and how the pad works. So I'm just going to set this aside for a second so it's a little bit clear. So if you just think of my hand here, this circle being the pad, and then my pointer being the actual metal lead that's going to go through it. So right now what's happening is we're putting that lead through and it's fitting very loosely inside of there. So we're not getting a good connection. And what we should be doing is then, putting some solder in here, and that's going to hold that in place and also provide that interconnectivity. But one way we can get around that is, the inside of the pads on this router, they actually have that metal connectivity in them. So like, it's not just the top pad itself, it's also the inside. So if we bend, this is going to be really extreme, but if we bend the pin over, then it's going to force a connection on the inside. And that's actually going to be what allows us to have that connection. If you just do it straight up and down like this, and you connect it with the zip tie, then you're not actually going to get a good connection. So I'll just bring this back over here, and I'm going to try and show it as best I can on camera, but it's honestly kind of finicky, so I'll do my best to show it on camera, and if I can't get it on camera, then I'll show you the end result. All right, so I've got it here to where I think I've got a good connection. And, if I touch it lightly, then there's no movement or wiggle, which is what you want to see on this. You don't want to give it a big push because the twist tie is not going to hold it that tight. You're going to bump it out. But as long as you don't have any wiggle, then it's probably going to be good. But what I do suggest you do, and this is actually pretty important to test this, is we're going to go back now and actually retest, just like we did the first time onto the bare pads. We're going to test at the end of these pins because that's what we're going to be connecting to and make sure they are still okay and we have that good connection. So I'm going to put this down, grab the multimeter, and just really quickly test those. Okay, I've got it back on the continuity setting and we're just going to really quickly test the ground. So same thing we did before, but we're actually just going to test to the end of this pin. And it's a good thing we checked this because I thought that this was good on here, but I don't actually have that good connection. So I'm just going to revisit and make sure I'm pulling this down tight enough. Okay, I've just tightened this down again. I'm not really sure if you can see any of the changes I made, but I just made sure to get it a little bit tighter and try and exaggerate the angle that it was on here and how I have tightened this down. And I'm just going to test that connection again now. So I'll check the ground again with the continuity tester. Perfect, so I'm getting a beeping immediately, and I'm still going to check the other pins because just because we have that ground one down tight enough doesn't mean that we have the other ones seated. So I'm just going to plug it in and we'll at least test the VCC and transmit pins and make sure they're all good as well. All right, so I've got it plugged in. I'm just going to switch my multimeter over to that 20 volt DC reading again, and we'll test quickly the VCC and ground pins in the same method that we did before. Perfect, so VCC is working, and I'm just going to test the transmit pin while I'm here. All right, and the transmit pin is working. So just a quick note when you're testing them too, you're going to want to be probing fairly lightly on these pins to make sure you have good connection. Because if you're actually, pushing really hard down on these pins, then that kind of defeats the purpose of checking for the connection. You want to be simulating as if you were just connecting something to it where there's not going to be any pressure. So make sure you are touching lightly. And if you run into communication problems down the road with your UART connection and you did go this method of using the zip tie, then what I would do is just come back and retest every one of these pins and make sure they're working as expected with the multimeter, because eventually, this is going to loosen up and you're going to lose this connection. So keep that in mind. With that being said, in the next video, I'm going to show how to solder this and make it more permanent so we don't have to worry about that. If you're going to skip over that video, I just wanted to let you know about that, because when you're going to see me doing this in the future lessons, you will see this soldered in place because I'm going to do it in that video. You won't see this connection. So I have tested quite a few times just to make sure that it's realistically doable. And you can connect the UART to USB adapter and the protocol analyzer to those header pins with this method and reliably get that data, as long as you make sure you've got it tightened down. So that wraps up this video. I'll see you either over in the next one where we do some soldering, or in the final UART video where we're going to connect our protocol analyzer. So I'll see you over there. Welcome everyone. So in this video, I'm going to be demonstrating how you can solder those header pins onto the router UART connection in order to not have to use that twist tie method, which is going to produce a much more reliable connection if you do choose to solder it. And it's entirely optional if you choose to do that. Again, you can just use the twist tie method that I showed before. So if you're already familiar with soldering and you just want to skip to the part where I actually am soldering the header pins on, then feel free to skip ahead. But I am going to start this lesson with just showing the basics of soldering and how we can do through-hole soldering in case this is your first time doing any soldering. So if you do want to follow along here, at a minimum, you're going to need a soldering iron. So I've got mine right here, a soldering station, and then some solder. You're also going to need a few items for safety. So the first one is, and I'll show right here, I've got these on. So I always wear safety glasses when I'm soldering. And I know that may sound silly to some people, but if you have worked with solder, you'll notice that sometimes the way that it drops and splashes, it can be very erratic in how it splashes. And the last thing you want to do when you're looking up close at something to make sure you're getting the solder right is have a piece of hot metal drop into your eye. So also generally when you're soldering, you're going to want to have something to remove away the fumes so you're not directly breathing them in. Most solder, including the one that I'm using, it has lead in it, so really nasty stuff to breathe in. So I don't have my fume remover on right now, actually, just because I'm only going to make a couple of solders and the sound of it really does mess up the recording quality of the sound, but something to keep in mind that you should also be running that. And then just a couple of other quick safety things. Honestly, this goes without saying, but to be honest, I'll raise my hand and say that I've burned myself with a soldering iron before. These things get extremely hot. We're going to be, essentially melting metal with it, so they get very, very hot. And, any part of them that is metal gets hot. So even though it's just the very tip of it here, all this area, the cage, all of that gets super hot and you could burn yourself on it. So, you don't want to be like this meme lady that I'm going to pop up on the screen right here. And then finally, something to keep in mind is that whatever we are, soldering to, we're going to be touching and heating up as well, and it's going to get hot. So I've got a couple resistors here that I'm just going to be using as test pieces to demonstrate the soldering. And when we're soldering it, like even if we're soldering this end and then we're trying to hold it in place on this other end, well, the whole thing is going to get very hot. And I've personally done this myself before, where I'm just trying to really quickly hold a piece in and not use a third hand or something else like that. And you can burn yourself because the whole actual piece of metal is going to get hot. Again, it's designed to conduct electricity, these wires, so they're also going to be very good conductors of heat. So something to keep in mind. With those couple of safety things out of the way, let's get started on our actual soldering. So what I'm going to do is I've got a piece of proto board here that I've broken off, and I just was using this to practice soldering. So the way these work is I've got a whole one here. I just didn't want to waste a whole one for this practice. Is they're kind of like a PCB in that they have all these pads on the back like you would see in through-hole components on a PCB. And then, there's just nothing on this end. There's the drill holes. And these are designed for prototyping when we're making a circuit that we want to be more permanent, but we don't want to actually design a PCB. So we can just put our through-hole components in here, solder them onto the back, and then it's up to us to create jumpers instead of having the traces like we would on a lead. And another use for these is they're great to practice soldering if you want to get a practice in without actually doing it on an actual board where you might cause some damage to anything. Okay, so I've got mine here, and you don't necessarily have to use a third hand, but it's going to make your life a lot easier if you have one for soldering. So I'm just going to mount this actually in the third hand here. These two. And the nice thing with these 4-1s is we can actually use these other hands then to hold components in if we need. And I've got my resistor here. You can see I've actually been practicing with just a few other before I turn on the camera just to make sure my soldering iron was hot enough. And what you can do with these resistors, if you are soldering any through-hole components like these resistors, is we just bend the leads up. And I'll just pick a couple holes here to slot this through. It doesn't really matter since we're not, actually putting this resistor anywhere. And then with these leads, what we can do is we can just fold them down to hold the resistor in place. So it's kind of nice with resistors and other through-hole components when they have these leads. We don't have to worry about holding them in place. We can get this to hold it down. So I'm going to grab some solder here and demonstrate how we actually make these solder connections. So the first thing you want to do just to check and make sure your soldering iron is hot is we're going to do what's called tinning the tip. And what that is I'm just going to touch a little bit of this solder to the tip of the soldering iron and make sure it melts and we get a good connection here. So perfect. It just immediately melts and I keep a little bit of that on the tip. Now when we make these solder connections, what you want to do is we actually want to heat up the pad and the component lead and then touch the solder to those and have the solder melt, as opposed to trying to just touch the soldering iron, get the solder to melt and have that then try and glob onto the leads. So I think it's easiest if I just show that for the first time. So what I'm going to do is I'm going to hold the soldering iron up to the pad here and let it get hot and let the lead get hot. And then I'm going to touch the solder to that area and pull it away. And perfect, we get a nice solder joint there. And I'll just show it on the other one. Again, I'm just touching the solder to the pad and the resistor lead. And then I'm touching the solder to that pad and resistor lead. I'm not necessarily touching it to the soldering iron tip itself. You see here we get two nice solder joints. Okay, so I just moved the prototyping board a little bit closer to the camera so it's really clear what I'm doing. And I've got another resistor here. And what you can do with these through-hole components, if I can just show it in front of the camera, is that we could bend over the leads like this and then just slide them into the hole. So that's how we solder those in. And I'm just going to pick a couple holes at the top here and we'll just slot this through. It really doesn't matter because we're just practicing what ones we do. Okay, we'll do this one on an angle here. So I got the top one here and then over here. I'm just going to pick up my soldering iron here. So the first thing that you'll want to do when you're making a solder is what's called tinning the tip. And this is a good way also to test that our soldering iron is hot enough. So I'm just going to just do a really quick tap of the solder to the end and make sure that it actually melts on there, which it did. So that shows us that it's hot enough. And then what we want to do when we're making these solder connections is we don't actually want to be, melting the solder with the soldering iron so it's liquid and then kind of trying to touch that or attach that to these leads. What you actually want to be doing is we want to touch the lead and the pad that we want to solder with the soldering iron and let it get hot. And then we touch the solder to that pad. And you see here we've got a really good solder joint by doing that, because the way that the solder works is it's actually going to want to flow towards the heat. So what that does is it makes the solder pull nicely around the pad and the component, and it doesn't go anywhere that we don't want it to do. So I'll do another one here, right here. Again, you can see I'm actually just touching the lead and the pad, and then I'm going to come in from the side here and do a really quick solder like that, and we get a nice solder joint. So I've got a couple examples of bad solder joints on here for when I was testing, and just to show you how those happen. So, for example here, this is what happened when I was just playing around with dropping the solder on. So you'll actually get what's called a bridged connection. So we've got this chunk of solder that goes across two, and we've done that here. So I just show you here quickly, how we can get that. If I use these components right here, and I'm just like kind of melting the solder and trying to put it on. See here that it does not, honestly, it's not sticking very well. I'm getting like these globs, and that's what gives us the bridge and a bad connection. So again, that's why we just want to be touching the soldering iron to the pad or the lead, and then the solder to that, and that's what lets us get that really nice connection for the through-hole solderers. So if this is your first time soldering, I would really highly recommend getting a couple of these and actually soldering them. So what I'm going to do now is I'm actually just going to do a practice as well with the header. I've got a spare header pin here, and we'll just pick a spot here and slot it in. So you see, I'm making use of the third hand for this because there's actually no really good way for me to, hold this in place with my hand and then solder it. If you can see it, it's right at the top here, these connections. So I'll just demonstrate a few good solders in how to do those. So the one other thing I will just quickly mention with soldering is you will have noticed there that I didn't linger when I'm making these solder joints. As soon as I notice that it's melted and I've got the solder in the spot where I want it to be, then I'm actually pulling it away. And the reason for that is when we're soldering, some components, especially like transistors, diodes, and integrated circuits, the extra heat from the solder gun, it can actually cause them to burn out. So we want to be, as quick as we can while still getting that good solder joint. So now that we've got a little bit of practice in on that proto board, I'm just going to grab the PCB for the router here, get it set up in the third hand, and then we'll take a look at soldering the header into the router PCB. Okay, so I've got the router installed into the third hand here, and I've got it really zoomed in so I can show you how I'm going to make those solder connections. These 4 pads right here, and this is the underside of the PCB. You'll notice that there's no components or silk screening. This is the underside of that UART header. So what I'm going to do is I'm just going to stick the header pin into there, and I'm going to make use of the third hand tool as well to hold it in place here. So I've just got it snapped in place there with the third hand tool. You can see the leads are coming through here. And if you don't have a third hand tool, what you can actually do is you can hold it in place with a little bit of tape or even some sticky tack or something like that so that you don't have to be holding it with your hand. So same as before, I'm just going to test and make sure my soldering iron is hot. Best to do this actually not over the board like I was just about to there. So I'm just going to check it, but I'm going to check it out of camera here. All right, mine is hot enough, so I'm ready to actually get soldering. Again, we're just going to be touching the soldering iron to the pad and the lead, and then the solder to those. We get a nice clean solder, and I'm going to move on to the next one. Nice clean solder, moving on to the next one. Perfect, and those look good to me. So what you'll want to check when you are, visually inspecting these is to make sure you don't have any bridges. So you can see I can actually fit my pointer here through, and I don't have any solder that's touching, because if we do actually get solder that's going across here, what that's called is a bridge, and then we're going to have connectivity between the 2 points, and that's not good. That being said, what I am going to do now is I'm going to, move the soldering iron out of the way, turn this off, and we're going to do the same thing that we checked when we were using the twist tie method, and we're going to check to make sure all of our connections are still good. We've got that ground connection and the voltages as we expect them. Okay, so I've got my multimeter here, and then same as before, we're going to start by using the continuity setting to do a continuity check between the ground pin and this ground plate down here. And I get a beep immediately, so that's perfect. It means we have a good solder joint and we have a good connection. And I'm just going to check the voltages on the VCC and the transmit pin as well. So plug your router in if you are following along at home. I'm going to switch my multimeter over to the DC voltage setting again at 20 volts. And then the same as we have previously, I'm going to start with the VCC, which is the top pin here, and probe from the VCC to the ground here. All right, and I immediately get that 3.3 volts, so that's as expected. And I'm going to check the TX pin here in the same fashion. And we see it at 3.3 volts as well. So that's perfect. If you want, you can check the RX pin. Should be 0 volts. Okay, perfect. 0 volts, just to make sure there's no bridging or anything like that. And perfect, it's at 0 volts. So we know that all of our solder connections are good, and we are good to go. So if you did take the soldering route, and this is your first time soldering, and it all worked out like this, then congratulations and good on you. That wraps up this video. I'll see you over in the next one. Welcome everyone. In this lesson, we're going to be continuing on learning about UART. And in doing so, we're actually going to take a look at the transmission that we identified on the router PCB that was taking place during boot up. Now, to do so, we're going to also be learning about the next tool in our hardware hacking toolkit, which is this device right here, a logic analyzer. So what logic analyzers allow us to do is to connect to the various communication points on a circuit or a PCB, and then record any of the digital communications that are going on that channel as a capture. And then what we can do with that capture actually is with the software that comes with these analyzers is we can actually use it to decode those transmissions and figure out what's actually being transmitted. Now, that's as long as we're able to figure out what, protocol is being used and the various parameters that are taking place with that communication. Luckily for us, if we understand how the protocols work, then when we look at these captures, we can usually get a pretty good idea of what is going on and the different parameters that we'll need to set to decode them. So I think it's easiest if we just jump right into it and get this analyzer set up to capture the traffic from that router. Now, if you chose not to buy one of these, that's okay. You'll be able to follow along with most of this lesson. The great thing about the captures that you take with these is they can be saved for analysis later on. And I will save all of the captures that I take and make them available so you can open them up with the software still and follow along. So on this analyzer right here, we've got a nice picture that just demonstrates the pinouts of the pins right here. And it's just a transposition. So, if you were looking at the top of it like this, that's how these pins represent. So the two most important ones that we've got to take note of are the ground pins. Again, we need that ground for our communications to be able to work. So I'm going to hook my jumper up to that first. And I'm going to use the black wire just because that's generally the one in electronics that's used for ground. But you can really use whatever colors you want here. The colors do not matter at all. I'm going to connect my black one to the bottom, one of the bottom two pins. Either one is fine. There's two ground connections there. And then for the UART communication, we actually are only going to need to use one channel. And that's because we're just going to be listening to that transmission. Again, you can think of this as being like the receiver, and we're going to receive that transmission. So we just need the one channel. We're not going to be sending anything back or transmitting anything. So we don't need a second channel. And you can use whatever color you want for this. I would suggest you use channel 0, but realistically you can use any channel except for ground. The nice thing about channel 0 is you see we've got this power up here at the top and this channel 0 down here at the bottom. Well, these are LEDs, so when you plug this in, you're going to get the power indicating that it's turned on. And then this channel 0 LED it will actually light up when there's communication on channel 0, and it only works specifically for that one channel with that indicator, but it will give you a good indication if you've got everything hooked up and you're actually getting data being transmitted. You'll see this channel 0 flashing. So that's why I'm going to use channel 0. And I got the purple one right here, so I'm going to use that. And it is this top left pin right here that is channel 0. Okay, so I've got it pushed in. Sometimes these pins can be a little sticky, so you just need to use a little bit of force, but I've got these two hooked up. So what I'm going to do now is I'll just bring the router over here, and we're going to hook them up to the router. Before I do that, though, I will just mention, you notice I don't have the protocol analyzer plugged in yet to computer, so don't plug that in yet. And also make sure your router isn't powered on when we're going to be plugging this in. We'll turn it on later once we've got everything set up on our computer and we're ready to make that capture. Okay, so I've got the router here, and I'll just bring these pins up nice and close so we can see them again. And again, we're just going to be connecting the ground pin. So that's this one, if I can just grab it right here. So the ground pin and then the transmit pin. So the black will go to the ground and then purple will go to transmit. I'm just going to hook those up quickly right now. Okay, so I've got those hooked up. If you're following along, make sure they're hooked up the same as well. Just do a quick double check. Make sure you've got black to the bottom ground pin of the analyzer and then purple to channel 0, black to the ground on the router, and then purple to the transmit pin. I'm going to head over to my computer now and we'll take a look at how to install the software and the drivers for this. And then after that's done, we'll plug the analyzer into the computer and then turn the router on. But just really important, until we do those, don't power on either of these. Okay, so I'm back over at my computer now, and you may have noticed in the past videos when I was on my computer that I'm using a Kali Linux machine, and I'm actually running this as a VM using VMware. Now, I'm not going to go over specifically how to set up a Kali VM in this. I'm going to assume if you're watching this through the TCM Academy that you're already familiar with how to set up that VM. I would suggest using Kali Linux because it's going to allow us to install or already have all the tools that we'll need for the rest of this course. So before we go on with this lesson, I just want to make a quick note about that. With that out of the way, we can get started on installing the software that we're going to need to connect up to our logic analyzer. And what we're going to be making use of is some software offered through the SIGROC project. So I'm just going to go check out their website right now. It is sigroc.org. Just like that. And if you want to read about their project, it's a pretty cool open source project that allows for us to have access to cheap logic analyzers like the one that we bought, and then make use of some open source firmware and then also their software that's going to connect to the logic analyzer and allow us to actually analyze those captures. So I just went to this website to check it out. We can actually get their software through the apt-get repository on Kali Linux. So what I'm going to do next is we'll just open up a terminal. Always a good idea to update your repositories first, so I'm just going to do that right now. And I'll let this run through. Okay, so in order to install this through apt-get, it's going to be sudo apt-get -y install, and then it's just sigroc. Perfect. So it looks like it is installed. Now, the actual specific software we're going to be making use of to view the logic captures and also make those captures is called PulseView. So that is the software that's created through the SIGROC project. So I'm just going to launch that up right now. All right, so this is the software we're going to be getting used to using to take captures with our logic analyzer and then also to analyze them. So I have my router powered off now, as you should as well. And I also have my logic analyzer not connected to my computer through USB. But what we can do now is we're going to connect the logic analyzer to our computer through USB. And then if you are using a VM like me, then you'll have to make sure you connect that USB device to your VM as opposed to the host machine. So I'm just going to plug in the USB cable right now to my logic analyzer. All right, and it should show up as this Lakeview USB device, and it's perfect that it's just popping up for me. So I'm going to click OK. So if you don't get that pop up, for me, I'm on VMware Pro. So if I come up here and I do the drop down here and go VM and then removable devices, then you can connect or disconnect it through here. So it's going to show up as this Lakeview logic. And it's similar if you're not on the Pro VMware. And then it's also very similar if you're using VirtualBox. So remember to connect those. So I'm just going to make sure mine is connected right now. So this logic analyzer already actually comes loaded with one of the open source firmwares that's developed through the SIGROC project, which is the FX2 LAFW firmware. And the reason we need to know that is we're going to need to set up PulseView to communicate with our new device. So what we're going to do is just go up here and we're going to click on demo device in the drop down here, and we're going to connect to a device. And then we're going to have to choose a driver. So from this drop down here, we're going to go and we're going to pick this FX2 LAFW generic driver for FX2 based LAs. So we'll click on it here. And then we'll just leave it selected as USB. We have it connected through the USB. And then we're just going to click on scan for devices. And it's going to be this one right here. This Slea Logic with 8 channels is the one that we are going to grab. So I'm not entirely sure why the device is named as this. This is the name of another company that makes logic analyzers. So I don't know if these makers at one time were trying to pass this off as a clone or not, but we're going to be using all of the open source drivers and this open source software with it. So you can just click OK, and it's going to add that device. Now, if you get an error at this point about the device not being supported or there's an issue connecting to the device, I've noticed that if you have the USB for this logic analyzer plugged in through a USB hub or something like that, it really doesn't like it. So make sure, if you can, to just try and plug this directly into the USB on your computer, and try not to have any hubs, or in my case, I had a KVM switch that I was plugging into and it didn't seem to like that. So with our device connected, we're actually almost ready to start taking our first capture. But what we're going to do first is we're just going to make 2 quick changes here. So the first one is just how many samples we're going to take. And we're going to up this because this is just going to run for 1 second and we want to take a capture longer than a second. So I usually just put it at 100. And then if we use less than that, then that's okay. It just won't stop it ahead of time. If you notice that you're running a capture and it's just stopping, you probably forgot to update this, because at 1M, the default, it's just going to run for a second and then stop, which isn't going to be long enough for our scenario. So the next thing we're going to change here is this frequency that we're going to sample at. 20 kilohertz is going to be a little too low for us. I'm going to up it to 1 megahertz. Our device will support up to 24 megahertz, the logic analyzer that we have, but in testing, I found that it honestly, it can't always hold up to 24 megahertz. And what will happen is it will just stop the capture at that point. 1 megahertz is going to be more than enough for this UART capture that we're about to take. Okay, so we're almost ready now to start our capture. And what we're trying to capture here is that boot up transmission on the router. So we're going to want to make sure we have the router ready to be powered on shortly after we start the capture. So what I've done in this case is I have my power brick, it's plugged into the wall, and I just have the end of that near the router ready to plug it in. And I've already got my cables hooked up from the UART header that we attached on the router to the logic analyzer, and those are connected up how we did in the last video. So all I need to do is I'm going to hit the run, and then I'm going to plug in my router. So what we're going to do is, this is to start the capture. So I'm just going to start the capture right now, and then very shortly after, I'm going to plug in my router. Okay, and if you just slide this bar over here, you can see right here, this is where I powered on the router. And then as I slide over, you can start to see these blips. And if we zoom in on them, so I'm just using my mouse scroll wheel, we start to get some transmissions that we're capturing. So I probably had it run long enough now, so I'm just going to stop it here. And we now have our very first logic analyzer capture of our UART signal. So if you, for whatever reason, were not able to get this working, or you chose not to purchase a logic analyzer, what I'm going to do right now is I'm actually just going to save this capture, and then we'll end the video here. And in the next video, we will open up this capture and we'll take a look at how we can decode this UART signal in some of the different characteristics of UART. So good idea to always save these just for our reporting and so we can have them later. And to save it, we're actually just going to come up here to the save icon. I'm going to click save. And we'll see here it defaults as this srzip session file. So that's the one that we want to leave it as. And I'm just going to save it on my desktop now so I can find it. And we'll just call this router. Actually, we should name it TP-Link router UART boot up capture. And I will save that. Perfect. So I'll end this video here and I'll see you over in the next one where we open up that capture and then take a look at decoding that UART transmission. Welcome everyone. In this video, we're going to pick up where we left off in the last lesson and open up that capture we took in pulse view of the UART transmission on the router. We're going to look at decoding that and then also take a look at some of the characteristics of UART transmission. So let's get started on that right now and open up pulse view. Okay, and we don't actually need to worry about connecting our device or anything this time because we're just going to be looking at that previous capture that we took. So in order to do so, we can just go here and click open. And then if you, from this drop down, just go all files. And then we're going to choose this TP-Link router UART boot up capture or whatever you saved it as from the last lesson, if you're using the one that you saved. And click open, and then perfect. We can see here we've got that same capture and we left off right where we were at. So if we just zoom in, and again, I'm using the scroll wheel here to zoom in, and you can use the mouse left button to drag and move it along. So we can see we've got all of this UART capture going on. I'm just scrolling through it right now. But you know, to us, this isn't super useful to try and figure out what's going on by just looking at these raw captures right here like this. So what I'm going to do is I'm actually going to apply a decoder to it, and that's going to help us decode what's going on with the UART. So to do so, we can click this button right here, which is for decoders. And we already know it's UART communication, so I'm just going to search for a UART one. All right, so what I like to do is I'm just going to grab this and pull it up to the channel that we're working on, which is this D0 channel. And since we don't need the other ones, just to clear them out of the way, I'm going to quickly delete them. So you just right click and delete. I'm just going to help clear up our view here a little bit more. All right, perfect. Now you see it saying here there are no channels assigned to this decoder. So we'll just click on it here. You can leave it, you can change color if you want, but I'm just going to leave it and call it UART. And we're going to choose the receive line. So we are receiving here, remember? So that's why we're going to choose the receive line, even though we are connected to the transmitter. We're the receiver. And I'm going to set that to D0 here. All right, and then you'll see we have all of these characteristics that we need to set. And I'm just going to leave it here as the defaults because right now our device is actually just using the defaults. And I would say honestly about 95% of the IoT devices that I come across that have UART enabled on them, they use these defaults as well. So good to remember. So that is the baud rate is at 115,200. Data bits are 8. Parity is none. Stop bits are 1. And then this bit order is least significant bit first. The only change I'm going to make here is this data format is it's going to display it in hex, but I'm thinking that this transmission is actually probably going to be ASCII data. So if we want to see that ASCII data in plain readable letters, we can just choose here, ASCII. And that is all perfect. So we can just close this. Now, if we pick a pulse here, and I'm just going to scroll out and see where we are in the actual message. All right, let's grab one of these ones. This is one of the very first ones here. And if we keep scrolling in, and I'm just going to go to the start of this message here. Right over here, maybe. We can actually start to see the text that's being sent out as part of that boot log. So right here, we're even already starting to get some banner grabbing here, flash manufacturer ID. And then we're starting to get some IDs and even, a warning message here that's coming in about this chip. Now, if you're curious, you can scroll through here and take a look at all the boot messages. Again, if we scroll out here, like there's a lot of data that's being sent at boot up, and you can read it all through this, but keep in mind, this isn't the best way to actually view this data, and generally that's not what we're going to use this logic analyzer and the decoder for. This is more just for us to get a sense of what is going on with that transmission, what the properties are, and if we can't get it working to communicate with it, then we can use this logic analyzer and the capture to debug that. On our router, it's pretty straightforward. The pins were already labeled for us, so we knew it was UART, we knew which pins were being used, and we're using all standard settings, so it's pretty easy for us to figure it out. But it's not always going to be like that. And to prevent you from, pulling out your hairs, just trying a bunch of different combinations when you're trying to connect to the router, sometimes it's easier to get a capture of the data and then just inspect it, and you can kind of figure out what's going on. Now, in order to figure out what's going on, you're probably going to need to understand what is actually going on beneath the hood here with the UART and this decoder. So that's what we're going to take a look at right now. So I'm just going to zoom back in on the start of this message right here. Maybe not this one because it's all equals. Perfect. So we'll take a look at this flash manufacturer message. And I'm just going to zoom in actually just on the very first part of it right here. Okay, so if I pull back up the UART properties here, the first one we'll talk about is the baud rate. And we've already chatted about this briefly when we were talking about that, imaginary serial protocol that we were coming up with, the really basic one. And what this is this is the speed of the transmission. And essentially this is the amount of symbols per second that we are going to be sending. And you remember both the receiver and the transmitter have to agree on that same speed so that we can decode the message. Now, if we didn't know what this baud rate was, and we tried some of the standard ones and we couldn't figure it out, we can calculate that. So the first thing in order to calculate it is we're going to actually have to take a look at the symbol width. And in order to do that, we need to find one of these pulses that represents just one symbol. So what you're going to look for is the smallest symbol that repeats itself. And I'm looking here, and in this transmission of data, I can see, these two here, but it's not super clear sticking out. So I'm just going to zoom out. And then, when I start looking more, I can see this kind of repeated, here's one, here's one, here's one, here's one, here's one of this looks to be the lowest width pulse. So I'll just grab this one right here. And if you click up here on these markers, it's actually going to allow us to take a measurement. So what I'm going to do is I'm just going to drag it over this here. And we'll see here that it is 8 microseconds. And you'll recall that the way to calculate this baud rate is it's 1 over this time. And we don't have to use the calculator. The pulse view is going to do it for us. And it's measuring it as 125 kilohertz, essentially. Now, you'll notice this is off a little bit from the baud rate that we chose. And the reason for that is just going to be based on the sampling frequency that we chose. It's going to be slightly off. But the beauty of UART is we can actually be off by, plus or minus even 10% of that speed, and we're still going to be able to decode the message. So perfect. I'm going to clear these markers away just so it's a little bit easier to read. So that takes care of the baud rate. If we just go back to this F and zoom in on it, the rest of these UART characteristics that we have to set up, they all pertain to how we are actually going to be sending the data in each, what I'll say, kind of like portion of the transmission. So we already chatted about this a bit, but in networking, each, portion of data that we sent, we call that a packet. And that represents, a little bit of information, sometimes at the start and end in the header. And then it has the data in the middle. Well, in these lower end digital hardware communications, UART is not even a protocol in and of itself. We call each individual piece of data that we're sending like this a frame. So in this example right here, from here all the way over to here, this makes up what we call the frame. And then inside of that frame, we're going to have a few specific characteristics that help us to send that data and have it be decoded. So outside of the frame, though, is the first thing that I want to talk about, and that is this area right here. So you may have noticed when we started up the router that as soon as we powered it on, we saw the UART transmission line go to high. And we also saw that when we were probing it with the multimeter, that when it wasn't transmitting, it was just kind of in that idle time, then it was actually just at that 3.3 volts constantly. And what this time is usually referred to when we're not transmitting is we actually call it the idle time. And the idle time will generally almost always hold that voltage on the transmission line at the high level. And there's a few reasons for this, but the main reason is that it allows us to fail off. And what that means is that if we have some sort of failure on our communication line, so our transmission line gets broken, whether that's a trace or something gets unplugged, or there's just an error with the transmitter itself, then we can detect that error because the receiver will see that UART line as low. Whereas if we just held our idle time as low, then we have no way to determine whether or not we're just not getting any transmissions because it's not sending anything or there's something broken. So you'll generally see that idle time at that high voltage. Now, in order for us to signal that we're actually starting the transmission, we need to have some agreed upon way to do that. And that's what's happening right here. You'll see we have the start bit. And the start bit in UART is always going to just be one low symbol. So in our case, it's bits. So it's just going to be one single zero or one single low pulse. And that indicates that we're going to then start transmitting the data after. So you see here afterwards, we have this binary here, and this is all of the pulses that make up the data. And usually this is going to be 8 bits, but we don't necessarily have to send 8. You saw in the UART decoder properties that we can actually change this to 6 or 7 bits, but usually you're going to see it as 8 bits because of course that makes up 1 byte. And then this 0 1 1 0 0 1 1 0, this is what then represents for us this F in the ASCII. So the next parameter that we need to agree on, and you may have seen this in the decoder there, is the stop bit. So if we take a look, that's actually right here. This is the stop bit, and it's kind of cut off here, but that's the stop bit. And the stop bit, just as the name kind of implies, this signals that this is the end of the frame, and we're going to then either go back to idle time, or we're going to, in this case, if we're just transmitting right after, we're going to send another start bit, and that's going to start another frame worth of data to be sent. So you'll always have at least one stop bit, but some devices will use more than one. You can use, potentially 2 or 3 stop bits. And the reason for that would just be if you maybe need some more time to allow for processing to take place or something like that. By default, it's almost always going to be 1, but this is changeable. So that's why you will be able to see it in those decoder options. So the last setting that we'll chat about, and it's not being used in this transmission, and with IoT devices, you're very rarely going to see it actually used, is the parity bit. And what parity does is we can actually perform some bitwise math on the data that's actually being sent. And then we choose our parity bit to be either even or odd. And what that means is that when we perform that bitwise math, if we use the parity bit, then it should make the operation of that bitwise math even or odd, depending on what we choose the parity bit to be. And if it isn't even or odd, then we know that we have some sort of error in our transmission. So it's kind of like a really, really basic way of doing a checksum for error checking. And you won't really very frequently see it used. So I just want to call attention to that. Usually you'll just see it left as none. So the last characteristic we'll chat about, and this is actually a funny one that we picked this F here now that I'm looking at it, is this least significant bit first is sent first. So the reason for F that's so interesting is that it's almost like a palindrome of itself, and that even backwards it's the same. But what that's essentially saying is that this hex number, if you're reading in its binary representation of this 011001110, this is the most significant bit here, and this is the least significant bit. This one, obviously, this represents the least amount if you were to convert this to hex. So this one is sent first, being the lowest one. So what I'm going to do is I'm just going to clear this writing off, actually, and we'll just take a look at a different one. And what I'm going to do is I'm just go back quickly back into the UART here, and I'm going to switch and I'm going to switch it from ASCII to actually look at the binary. So you'll notice the binary data here, it doesn't actually match up with these, what it's decoding it from. So here we have 00110, and then here we have 0110. And that's how it's showing that that least significant bit is being sent first. So it's kind of backwards, right? So here we have 0, that matches with this 0. Here we have 1, that matches with this 1. Here we have 1, that matches with this 1, this 0, and so on. So just something to keep in mind when you're looking at those bits. So if you keep in mind these different characteristics of UART transmission, and you think you have a UART but you're not able to decode it, then what you can do is, without the decoder, we can zoom in and start looking at the bits and trying to frame it ourselves and figure out what's actually going on there, and maybe identify, for example, that we have a parity bit or something, or maybe realize that it's not actually UART that we're looking at, and it's some other protocol or type of communication. With that being said, I'm going to wrap up the video here, and I'll see you over in the next one. Welcome, everyone. So if you're anything like me, then in your spare time, you might like competing in cybersecurity capture the flag events, or CTFs. And one thing I've noticed that's becoming much more common in these Jeopardy style CTFs, where they have different categories, is that they'll actually include a hardware hacking category. Now, of course, with these CTFs, hardware hacking can sometimes be challenging to include because we can't provide everyone with hardware. We have to come up with a software solution. So to overcome that, one of the most frequent things that I see being done is that the challenge will just be to decode a logic analyzer capture, and the flag will be, somehow hidden inside that capture. And, maybe it will be just a standard protocol that you need to understand and then decode it, or they'll, make up some kind of fancy protocol or something like that that you actually have to, put some thought into and analyze. These are a great way to, practice using the logic analyzer software. And then also, if you are just trying to be competitive in CTFs, I honestly find that these are usually a really easy amount of points, because I think people are intimidated by them. So not a lot of people try them, but if you understand how to use the logic analyzer software, then, most people, you can usually decode these and score your team some easy points. So I put together 2 challenges here for you to solve, and let's just take a look at the info for the first one just to get an idea behind what's behind it. So I'll look at broken transmission first here. And if you look at the info here, it just says, can you help us decode this transmission? Looks like there was some error during transmission and we can't seem to figure what's going on. And then just one hint here that the flags are in this format HWH with the squiggly brackets, and then it's all in this uppercase LEET format with the underscores in between it. So if you want to take a shot at solving these challenges, there's just the pulse view file right here that you can open up and then try and decode the flag. Again, it's in that format that's in the info.txt. So if you want to try this on your own, just hit pause on the video right now. And then when you come back, I will show the solutions. Okay, welcome back. Hopefully you're able to solve some of these. If not, that is okay. I'm going to go over these solutions right now. So we will look at broken transmission, and I'm just going to launch it up right now so we can click on the pulse view file here, and it should just open it up for us. Okay, so I'm just going to move this over here and zoom in. And when I'm initially looking at this, to me, It's starting to look like UART. Of course, we've just got the one signal here, so we know it has to be asynchronous. There's no clock provided or clock signal. Another good clue is that we have this line being held high here, and then in between transmissions, same thing, we have this line being held high. I'm going to zoom in a little bit more, and I'm seeing again what looks like these blips of UART transmission. So what I'm going to do is I'm just going to start by adding a UART decoder here. And we'll just take a shot in the dark. One thing I'll usually do is I'll just, we'll pick the channel here and I'll just run with all defaults and see where that gets us. So we will just leave it as all these defaults, the default baud rate here. I'm going to zoom in. And you see, unfortunately, we get a framing error. So what that means is that it wasn't able to, find frames that match those characteristics that we set out at. And generally, what this means is that you have the baud rate wrong, but it could be any one of those other parameters that we chose, like the amount of data bits or the stop bits or the parity, for example. What I suggest is, if you have framing errors and you can't figure these out, start with the baud rates and exhaust, trying the baud rates and a bunch of different baud rates and your measurements before you start going on to any of these, because a lot of times, the data bits, parity, stop bits, this least significant bits first, these are all going to just stay as standard, even in CTF competitions. So start with the baud rate first. With baud rate, you have two options. You can just start by measuring it, which is always a good thing to do with measuring it. Or you can look at a list of standard baud rates, because there really is only a certain amount of baud rates that are generally used. Now, in a CTF, someone might be doing something kind of weird or wonky and just running with a non-standard baud rate, but a lot of times you'll see standard baud rates being used. So for CTFs or not, I always suggest take a peek at those. So let's open my web browser here. I'm just going to go to Wikipedia, and I believe it under serial port, there is a list of these. So if we just look here, if you scroll down a little bit, common serial port speeds, and you just see a list of this bit rate or baud rates, and you'll see a bunch of the common speeds. So what we see here is this 115,200, probably the most common one. The second most common one that you'll see a lot is this 9600. So you can try and brute force and just use these speeds. But what I like to do is I'll use these in conjunction with a measure. So if you just jump back to our measurement, and if we zoom out a little bit, I'm seeing this symbol, this short symbol, repeating over and over again. So I'm going to zoom in a little bit on it and just take a measurement here. Okay, so I'm seeing it as this 14.4928 kilohertz. And that translates to a baud rate of, if we just take this decimal and move it over 1, 2, 3, that is 14,492, which that actually lines up, if we go back to here, it lines up with this 14,400. So I'm going to give that baud rate a shot, because we do remember, sometimes our measurements can be slightly off for the timing depending on the frequency that it was sampled at. We'll just hop back in here. And I'm going to put this at this 14400. And I'm also going to not forget to put this in ASCII. Generally, you're going to see it in ASCII in the capture the flag. And if we zoom out here and kill this measurement, all right, we got 0xAF. So looks like some sort of hex code being sent, another hex code being sent, and then as we scroll over, we start seeing some ASCII here, so that's a good sign. Loading firmware version here, loaded, handing over to kernel loaded, preparing transmission, and then we get the secret code is this HWH, we get this left bracket, broken underscore, and then we get ... detecting noise on the line, falling back to lower transmission speed. And then it looks like we got a pause in the transmission. And we've got a break here where it looks like now we have another framing error. And when I look at this, I'm seeing, if I just scroll out here, you can really see it obviously, that these pulses are a lot longer than these ones. And we did say that it was falling back to a lower speed. So, what can happen sometimes with these transmissions if the processor can't handle it or something's going on is that we need to lower the speed in order to not have errors and allow it to process. So maybe that's what this challenge would be mimicking. And I'm just going to zoom in here, and it looks like we've got this repeating again of these symbols. So I'm just going to take a measurement of these symbols here. All right, and it looks like we are at 1.1976 kilohertz, which if we jump back over to our list again here, we got this 1200. So I'm going to run with that. And one of the nice things in Pulse View is that we can actually drop in a second UART decoder on that same line. So I'm just going to do that right now. We just search for UART again. And we can add a second decoder. Just going to get rid of this measurement since we don't need it anymore. Set this as D0, but we're going to set this as that 1200. And then if we zoom out here, oh yeah, don't forget to set it to ASCII like I did. And we're starting to get measurements. So we get this, the rest of what appears to be. We're going to need to look at this UART. So it's hardware hacking broken underscore, and then the 7, which in lead speak is the T. And if we scroll over and zoom in, then we get the rest is transmission underscore received. And then it just says end transmission. So perfect. We got the solution right there. So hopefully you're able to figure it out. This is one challenge that I've seen this kind of theme or something very similar used before in hardware hacking CTF. So something to keep in mind, and just good practice for determining those baud rates and how we can decode the messages. So I'll wrap this one up here, close it, and we're going to take a look at the second challenge. Okay, so the next one is this beep, 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 and we'll take a look at that right now. Let's take a look at the info for it. All right, the briefing says, we've interrupted this strange transmission and are trying to figure out what it is. Seems like it may be using some ancient communication protocol. Hint, flags are in the format, and we give the same format again. However, they may be encoded in the transmission. CyberChef is a great tool for decoding strings during CTFs. So if you're not familiar with how CTFs handle hiding the flags, sometimes they will encode the flags in one of many encodings, hex or URL or base 64. And there's multiple reasons for that. A lot of times it's just so that it prevents people from doing a search or like a grep or something like that on the starting string of the flag. And CyberChef is a great tool, if you see these strings to figure out what's going on. So hint for that. Just going to close this and let's launch this up. Okay, so I'm looking at this and immediately it does not look like UART to me. We're just getting one channel here and there's no clock or anything. And I'm seeing that the line is low. And the other thing that I'm seeing is these pulses are, they're pretty long. So in order to solve this, you've kind of got to, this is a challenge that's a little bit more out there in terms of not being a standard communication protocol that you're going to see. But you will see this in CTS where people use, older protocols or things like this. The name of the challenge gives it away a little bit, hopefully as a hint, and then also in the info.txt that what we're actually looking at right here is Morse code. And if you're not familiar with Morse code, there's actually just two symbols that are used in Morse code, kind of like binary, where we have what's called a dot, so it's a short transmission, and then a dash, which is a long transmission. And then these combinations of dots and dashes, they actually make up letters and numbers, so they make up all of the characters. The cool thing about PulseView is it actually has a Morse code decoder in it, so we can just pop this up, and if you search here for Morse, we have a Morse code decoder, so I'm just going to add that. It's super cool that it's got one of those. So we're going to pick the channel, the data line here, and you'll see here we've got this time unit that we need to decipher. And the time unit in Morse, if you're not familiar with it, is it's all based on the length of the shortest symbol, which is the dot. Because the way that it works is, then every other dot should be the same length as that. And a dash is the same length as 3 dots. And between words, we'll have a pause that's the same length as a dash or 3 dots. So in order to get this time unit, we just need to measure the pulse width of this single dot, which I'm going to do right now. So we'll just add in a measurement. And there's one right here, so we'll just grab this one here. If we zoom in on it, looks like it's about 50 milliseconds. We can just go back into the Morse decoder here, and I'm going to set this as this is 0.05. Perfect. And then if we scroll out, we actually get this word here, which it gives us, this Morse word. So what I'm going to do is I'm just going to go here, and I'm going to go copy annotation text to clipboard. I'm going to go back into browser here, and I'm going to look for CyberChef. This one right here, load it up. I'm going to paste it in here. And then, so you're just going to have to get used to this if you want to do CTFs. You can either try, the different encodings. But when I look at this one, I can just see right away that this is a hex encoding because we've just got all of the, hex digits in here, 1, 0 through 9, and then, the letters A through F. So I'm just going to go, from hex here, drop the recipe in here, and then look at that. It gives us the output of the flag is this HWH. Morse is serial, which it is true. Morse code is probably the first actual implementation of a serial communication where we're just sending, those datas one after another. And it's almost still like bits where we have only 2 symbols. We have a dot and a dash. So hopefully you were able to figure this one out. If not, that's okay. This one is a little bit more of a challenging one to solve. With that being said, I hope you had fun with these capture the flags as well. This wraps up this challenge, and I will see you over in the next video. Welcome, everyone. So we're going to get hands on the keyboard hacking of our router started very shortly in just a couple lessons. But before we do that, I think it makes the most sense to talk a little bit about IoT penetration testing and the methodology that we'll follow for IoT pen testing, and just how that differs a little bit from the regular network penetration testing or maybe web penetration testing that you may be used to. And in doing so, we can chat about how our goals will be the same in some areas, and in some areas they'll be different. And this is going to help us a lot when we're doing our recon and penetration testing of the router, because we'll know what exactly we're looking for and what goals we have. I think the best place to start is actually to look at the architecture of an IoT system or ecosystem, because there's a lot more components that actually make up this IoT ecosystem than just the specific IoT device itself. So with that being said, I'm just going to hop over to the whiteboard, and we're going to take a look back at our smart lock and kind of try and design out all of the different pieces of that system that we would need to give it the functionality that we want in a smart lock. Okay, so as I mentioned before, we're going to be looking at this kind of imaginary smart lock that we were looking at in lesson 1, and we'll talk about building out some of the features that's going to take it from just being, a regular pin combination lock into being a nice smart lock that's going to have the features that make it attractive as an IoT or smart device. So of course, at its base level, we've got this pin pad, and then of course it's going to connect to the door. And at a very basic level, when you enter the combination, maybe 1, 2, 3, 4, then the door opens. But that doesn't make it a smart device or really make it super useful outside of just being a regular pin combo. So maybe one of the first features that we want to add in is that users can access this through some sort of interface, and they can add or manage what pins are available, and they can add users, for example, and give them pins, and maybe they want to do that through some sort of application. So the next thing I'm going to bring into our design is we'll just bring in a phone to represent that. So I just brought in the mobile phone here, and you can do this from your computer. Sometimes people do it from their computer, but I think a lot of people are using their mobile phones for this today. So it's a good representation of how a lot of it functions in the real world. I'm just going to draw this little cloud here around us, because we'll say that all of this communication here is my really bad cloud, that this is all happening and this is in the wireless local area network. So we'll say this is the WLAN, and then we can have communication locally as long as we're both on that same wireless network between the two devices. And it's basically just going to be using whatever ports are open on this. So, sometimes you see SSH being used for these apps. Sometimes there's even Telnet. It's kind of the wild, wild west of these IoT devices. Maybe this device has like its own little web server that it hosts for configuration or setup. Very common to see that. So maybe we'll see something on port 80. And we're going to look at this more in depth later, but it's just basically, we have this local area connection of, whatever ports are open we can be using. So what I'm going to do now that we have kind of our first interface here is we can actually start mapping out our attack surface for these devices. So I'm just going to start keeping a list. And as we add more features, we can talk about how those could be exploited. So the very first thing on our attack surface here list, and these are not in any particular order, by the way, I'm just kind of listing them by how we add features, is that local area network. So we'll just call this the internal network. So if we're going to be finding exploits or things like this, then it's going to be where someone already has access to that local area. Usually it's going to be a wireless network. So maybe we don't want to actually have to use the Wi-Fi to unlock this lock. And this is something that's very common with these smart locks. Maybe we just want to open up the phone and we put it close to the lock and then it opens up. So something that's really common with these smart locks and other IoT devices is that we're going to use some other form of what I'm going to just call short range wireless to communicate back and forth. And this could be something like maybe we use Bluetooth. So I'm going to say BT. Maybe we use NFC, for example. Maybe we use, RFID. Or maybe even some other type of proprietary protocol. So this is another attack surface for us here. So I'm going to call this short range wireless here. And that gives us another attack vector. So that covers if we are at home basically, or we're close to the lock. Maybe, we had some really nice features here, and some of these smart locks, this is where they'll end. They just have that, NFC communication where we can, set it up through the local area network, and that's all people want. But maybe, for example, I am at work, I'm away from home, and I'm worried that I forgot to lock my door. And I want to check if it's locked, or I want to be able to either lock or unlock it from anywhere, basically. I'm on 4G or I'm on a different network. I want to be able to lock it. So in order to do that, I'm just going to bring in another phone that we'll say is, outside of the WLAN. It's just in the, wider area network. It's out in basically the internet. As designers now, if we're trying to, figure out this architecture, the one option we have is that we can try and set it up so that, we can come from outside the internet, and we're going to try and, come into this home network, through the modem or whatever this gateway is, and then inside into the network. And, if you've ever tried to do something like this at home, you may know that this can be a pain to set up. There's a lot of security implications to it. And for the average consumer, it's maybe something that's, quite tough to set up. So what we're generally going to do is we're not actually going to, communicate directly, from our app or whatever outside of the local area network in. So what we'll generally do in these ecosystems is we'll bring in some sort of cloud service, and then we're going to initiate some sort of connection, outside of this WLAN. We're going to reach out to that cloud service, and then we're going to have that communication going back and forth here. And generally there's going to be some sort of API endpoint that's communicating here, and also probably at this end here. So for example, if we wanted to maybe, check the status of the lock, then we could just ask over to the API that's running the cloud service, and it would give us the response of the lock back. And we would have that communication here back and forth between the lock and the server. That's kind of like this polling method of communication where it's constantly updating. And then, for example, so if we wanted to say from the app, hey, can you unlock the door, for example, it's going to send that message over into the cloud server. And then when this device polls, it's going to check and see that it should unlock itself, and then it's going to unlock itself. And then we don't actually have to worry about sorting out any of that communication that comes, from this external device directly into the network. So this adds us another 2 pieces of attack surface that we should write down here. So the next one is this mobile app, right? So we should be taking a look. If there's a mobile app for our IoT device, we should be definitely taking a look at that. And then the 4th one is anything external, but I'm just going to put it as API because that's generally what it's going to be. So we should be taking a look at that external API interface. So then there's one other attack surface that we haven't talked about, and which is one thing that's kind of unique to IoT devices, and that's we haven't really talked about the actual hardware for this smart lock itself. So I'm going to use the abbreviation of hardware here, and this is where we have this unique attack surface or avenue that we generally may not have in the traditional web penetration testing or network penetration testing, where we can actually go out and buy this IoT device ourselves, or if we're doing penetration tests, it's going to be given to us, and we have access to the underlying hardware where we can then use that as an additional attack surface. So I'm going to add that here as the 5th one, and I'm just going to use the abbreviation of hardware here as HW. So in this course, this is actually what is going to be the main focus of our IoT hacking, is this hardware portion itself, the unique aspect. The reason for that is because, so these other ones, so especially, the internal network assessments, the mobile app assessments, the API, and then if we have a web server that's being hosted, all of those, there's really good resources if you're coming through TCM Academy for specifically, you've got the practical ethical hacking course, which goes over the internal network and some external network. We've got a great mobile app penetration testing course. We've got a good web app penetration testing course. Those are all really covered in detail. And for IoT devices in this IoT infrastructure and architecture, 90% of what's covered in those courses is just going to apply to these. They don't differ too much, with a few caveats that we will cover in this course. So that's why we're going to be focusing mainly on the hardware aspect in this course. Now, the one thing I want to point out about the hardware aspect, or vulnerabilities or exploits that we find with the hardware, is that depending on the device's functionality and what it does, a lot of these hardware, what I would call vulnerabilities or exploits or things like that, generally a lot of times the manufacturers are not going to be as concerned about them. So if we look, for example, at the smart lock, this is a good example and why I've brought it in. If we look back at that kind of made up vulnerability or exploit that we found, where in our penetration test we were able to open it up and then there was an exposed UART connector that an attacker could connect to, and they got the pin printout from that. So that's a great example of, a purely hardware hack where the vendor is probably going to be concerned about that because, an attacker from the outside of the house could then, breach the system and unlock it. However, if we look at the router we're going to be looking at, and, maybe we just take a very similar example where an attacker could open up the router, connect to the UART, and for whatever reason, it outputs the Wi-Fi password. And then the attacker can get on the Wi-Fi. Well, is that really a vulnerability or an exploit? I mean, the attacker then has to, enter the person's home. They have to get to the router, and a lot of routers, they already have a WPS button on them where you can push them and get access to it. So maybe that's not necessarily considered specifically a vulnerability. So generally what we're looking to do with these hardware hacks is we're actually looking to take either the access or the information or whatever we can find with them to then amplify or make it more efficient to attack these other different avenues, like for example the external API, maybe the mobile app, or even this internal network hacks. So maybe from our hardware analysis, we're able to find, for example, some bash scripts that we can take a look at and reverse engineer, or even some sort of executables that we can reverse engineer. And then this makes it easier for us to find, for example, maybe a command injection or a buffer overflow that we can, abuse either through the API or through the mobile app, or maybe even just on the internal network. And these are the kind of exploits or vulnerabilities that security researchers and even the, if we go to the other side, the black hat hackers are going to be looking for. So if we're doing this as a penetration test, then of course it's our responsibility to, check all of the avenues and report on them. But as security researchers, those are kind of the big things that they're going to be looking for. So just to give an example of some of this actually out in the wild, I wanted to share a recent blog post that I found interesting from the Zero Day Initiative. So if you're not familiar with the Zero Day Initiative, I would definitely recommend checking out their blog and this Who We Are. But one of the things they run is they actually run this Pwn to Own contest that just recently happened where they invite security researchers to come bring pieces of hardware or equipment, and then they actually, if they pwn them, then they get to own them. But now it's changed into actually just getting cash prizes. And this blog here is actually chatting about a very recent discovery in another TP-Link router, so the TP-Link Archer. And there's two teams that found both a local area, so that, WLAN or that local area that we're talking about. They also found a WAN, so this wide area network or external entry. And they both won cash prizes for this research, which is super cool. The other thing that I noted about the vulnerability is actually, if you look at the top here, they're observing these exploits already be attempted out in the wild by the Mirai botnet, which is a very famous botnet that is known to target IoT devices. So these exploits that have been found and published, they're already being used out in the wild by this botnet to get into people's internal networks from the external. So not great. The other thing that I wanted to mention too is, so sometimes these security research teams afterwards, they'll write up how they actually found these exploits. If you look through the blogs on here, there's lots of great blogs about how these exploits have been found. And very, very frequently, they're going to start with some sort of hardware hacking or hardware analysis so they can get some sort of internal shell to do debugging and also dump the firmware and then reverse engineer that firmware, because it just really gives you a leg up in your analysis and looking for these vulnerabilities and bugs if you can start with that shell or some sort of connection in the background and then the actual executables that are running in the background to be able to reverse engineer those. So something to keep in mind. That wraps up this lesson, and we'll hop over to the next one. We're going to start taking a look at the recon phase. I'll see you over there. Welcome everyone. So we left off our last lesson talking about the TP-Link Archer router and the exploits and vulnerabilities that were found through the Zero Day Initiative. And you may recall that there was actually vulnerabilities for both the internal network side, so through the local area network, and also even scarier through what we call the wide area network, which is the internet connected side or the internet facing side of the router. So in our last lesson, when we were talking about this, imaginary smart lock that we were coming up with, in our design, we actually didn't directly expose our IoT device to the internet. However, there are a couple scenarios, either intentionally or unintentionally, where this happens. So I just want to take a quick lesson and chat about those. I've updated our drawing here and I've actually added in a router. So I'm just going to draw again this kind of cloud here, and we'll put it at the edge of the cloud. And then we'll say everything on this side of the router, on the inside, this is that WLAN. So this is the local area network. In our case, they're all wireless, but this could also just be a LAN to wired. But the idea is that, so they all have private IP addresses, all of these devices, and they're sitting inside of our home network. And then on this router, we of course have the WAN port, which is what connects it either to a modem, or in some cases, these routers, they are a combination of a router and a modem, and they'll do that directly, but that actually is then going to connect it out and be internet facing. So what can happen with this wide area network connection side is that sometimes, either intentionally or unintentionally, we will expose ports out to just the broader internet. And this, again, of course, really opens up the attack surface for these devices in that we now have these ports that generally would only be exposed on the internal network, actually exposed out to the external internet. So outside of having this direct, wide area network connection and ports exposed to the internet, there is another way that we can have devices that communicate, directly outside of our local area network to devices that are out on the internet. And before we talk about that, what we should chat about quickly is why we do generally this polling with the cloud-based connections. So in our previous lesson, we chatted about how if we want to have our smart lock, for example, talking out to a device that's just out in the internet, like an app or something like that, out in the internet, then what we're actually going to do is we're going to pull back or initiate this kind of phone home connection to an API endpoint, what's most likely an API endpoint. And we're going to have this device reach from inside the network outwards and initiate that connection. And this is much easier to get started than trying to come, just from any device outside of the network and back in. And one of the main reasons for that is, of course, we're going to have some sort of static IP, or we're going to have a domain that's attached and associated with this, so we don't have to try and figure out what the IP is coming back in. And also, if we're going to be, sending this request out and then it's just going to be connecting back in, well, generally our firewalls and our devices on the exterior are going to, by default, allow these connections back to us. It's no different than if we opened up an app on our phone or a web browser and we're just going out to the internet and then we're expecting a response back. So it's going to allow this back into our network. And then, of course, from our smartphone, then we can just talk to the server and it can pass on any data we need through this kind of like polling and phoning home connection. So one interesting thing with IoT devices that you can sometimes do and sniff out is just you can see all of the different connections that it's making back. It's going to be a lot of times more than just one of these API endpoints or servers. And some concerns with these IoT devices, one particular concern that I have is all of the privacy concern and the different stats and things that it's collecting from the internet and, constantly sending those back. So we're not going to really focus on specifically those privacy concerns, but, just something of interest is all those connections and phone homes that it makes back out of the network. So this polling and opening up this connection and passing the information back and forth. For our smart lock, this works really well because really we just have very minimal amount of data that we need to send. We just got to kind of say like, what's the status of the lock? Do we need it to be unlocked, locked? Maybe there's a little bit of management data, but really we're chatting about very minimal amounts of data. Well, you see, I've also added in here an IP camera into the mix. So just your standard IP camera. And if we were away from home and we want to check, what's the feed with this IP camera? Well, if we're streaming, even in a standard definition, that's a lot of data to be putting through cloud infrastructure. And maybe we don't want to do this because that's going to incur like a big monthly fee for us. So we want to have some way to go directly from our phone and we'll just utilize our own internet instead of this cloud infrastructure to upload this. So how can we securely and without having to do too much configuration actually just get this direct connection from outside of the internet and then into our network? Well, one very common thing that you'll see for things like IP cameras or other devices where we have to either exchange a lot of data or we don't want it to be stored in a cloud server is we can use a peer-to-peer method where what we'll do is we'll actually initially have a handshake where we'll reach out still to our cloud infrastructure. And we'll ask it, how do we get in touch with this IP camera? And the IP camera is also going to constantly be in contact with this cloud server, pulling back, and it's just going to be sharing, its location and its IP address, so how it can be connected to. And then our cloud server is going to then, pass this information back to whatever this client is in this kind of peer-to-peer handshake. So we call this P2P handshake. And then once we have that handshake, then our actual device that's out in the internet, it can connect back directly into our device and we can then send that data out. So this isn't too uncommon, especially for things like IP cameras, and this is definitely another avenue that we can look to exploit or attack. And this is definitely something that black hat hackers are exploiting out in the wild. So we're not really going to focus too much on this, exposed to the internet portion in this course, but I just wanted to make sure that you were aware that this is also another definite attack surface for some IoT devices. And it's definitely one of the more scary ones because it is a really good avenue for hackers or attackers to be able to breach this perimeter of a home network and then get inside. So the one thing that I do want to show just really quickly is how we can find these devices and how hackers are able to find them. And to do that, we're going to hop over to the browser and we're going to take a look at Shodan. So I'll meet you over there. So if you're not familiar with Shodan, it's definitely worth a check out. You can get to it from shodan.io. And you don't need an account. You can purchase different subscriptions to this, and it's going to increase the functionality that you have. But even on the free account, you can get started and start seeing some pretty interesting stuff. So you see here, it's the search engine for the Internet of Everything. And it allows us to search for devices that are connected to the internet, either intentionally or unintentionally. And it's very interesting for finding various devices like routers and IoT devices, and really gives an idea of just what's connected out there to the internet and how hackers can exploit these vulnerabilities that they find in IoT devices that are actually connected to the internet. So the way that Shodan works as a search engine is it actually caches the header to responses when it kind of grows out and crawls the internet. So, if the device manufacturer or its part number or serial number or anything like that is in the banner of that response, then we can actually search for it. So if we, pull up, for example, I was already searching just to check this, the part number of the router that we're experimenting on. Well, if we search for that and we just run a search, can see that there is actually 33,550 of these devices that are actually connected to the internet, which is pretty crazy. And the top port is 80. So we have a lot of these web ports exposed to the internet. So, hopefully they're using good passwords and strong passwords for those, but definitely something that's dangerous to be exposed out to the internet. And you can see here, interestingly too, it gives us the country. So we've got almost, 7,000 of them are in Russia. So another interesting thing that Shodan is famous for, and I will just show you, is finding webcams or IP cams that are directly connected to the internet. And a really popular one is this webcam XP to search for, because I believe in its default configuration. So this is a much older IP cam or webcam, and I believe in its default configuration, it was just generally exposed out to the internet. So people are still running these, whether it's known or unknown. These are exposed to the internet, and you can see Shodan actually even caches an image of this, so you can actually see what is being displayed here. We got this banner grabbing of the webcam XP, and if we scroll down, we can start seeing some feeds. So this is the current day right here, actually right now, and we can see some feeds on here. And I'm not even going to scroll, any further, because you can see some really interesting things on here and find some really interesting things. With that being said, I do just want to give a really quick warning of, the ethical hacker spiel and, being really careful about the legality of what you're doing. So I'm just looking, and I would say, for me and for the region I'm at, this, kind of hands off, just looking, that's okay. It can be really tempting, though, with the things that you find on Shodan and what is actually exposed to the internet, to do even more than just looking and start, doing some poking around, entering default passwords in, all that kind of stuff. And I would be very careful and think twice about, how you do that or what you're doing and what is legal in your region. So that's all I'm going to say on that. And I'll wrap up this lesson here on IoT devices and their exposure to the internet. I'll see you over in the next lesson, where we're going to pick up and look at some OSINT for our router and how we can figure out some more details about it. So I'll see you over there.
Welcome, everyone. So now that we have an understanding of the IoT ecosystem, and more importantly, the attack surfaces that we have, we can get started with hacking. Similar to other types of penetration testing, like network penetration testing or web pen testing, or, honestly, really any type of pen testing, we're going to kick off with doing our Recon.
Now, when we were learning about electrical engineering in the fundamentals lessons that we were doing, we actually did some phases of Recon since we're repurposing the router as both a test subject for that learning and also our target. The visual inspection of the PCB, the probing with the multimeter, and then finally the discovery of the UART port with the logic analyzers would all be very important parts of Recon that we've already done. Now, before we actually get our hands on our target, or if we're actually just looking for a target without purchasing something, there's actually quite a bit of things that we can look for online or as OSINT. And that's what we're going to take a look at in this lesson. So I'm just going to hop over to my computer and we'll get started on that. So one of the very first places that I like to look when I'm doing hardware OSINT is to take a look at the FCC filings. Now, if you're not familiar with the FCC, stands for Federal Communications Commission, and this is a U.S. agency that regulates communications in the U.S., and one of the big things that they regulate is wireless communications, and that includes, basically anything that can communicate wirelessly or broadcasts any kind of wireless signal. We're not just talking about Wi-Fi. This would also be, any radio signals, things like Bluetooth, RFID, NFC. Basically, if it broadcasts anything out into the air, then it's going to be regulated by the FCC. So if these electronic devices want to be sold or manufactured or even used in the US, then they need to comply with these FCC regulations. And in order to actually comply with that, they have to submit some details and reports to the FCC. And then the FCC will approve that product. And any product that they approve is going to get an FCC ID. So if you flip over your router, on the back, you'll see this label with some details about it. And then if we zoom in and take a look here, you can see that we have this FCC ID here. And the first 3 or 5 digits are for the manufacturer. So on here, we have this 2AXJ4, and that is for TP-Link as a manufacturer. And then we've just got the part number here that makes up the FCC ID. And we can take this ID and we can go look it up and find the filing for this. Or if we don't actually know the ID specifically, we can usually just search with the part number and find it. So we're going to hop over to the browser right now and take a look at what we can find. Okay, so I'm over at the FCC website here, and you can see that it looks like it has not been updated since the days of dial-up. However, there is a lot of good information that can be found here for all the different hardware or equipment that we may be interested in hacking. Just to make a little bit of sense of this URL, I usually just bookmark it if I want to go here because it's kind of hard to remember, and I will link it below. But this OET, that is the Office of Engineering Technology, and what we're looking up is the equipment authorization. So these are the documents and images and everything that the companies will need to submit in order to get their authorization, and we're doing a search on that. So we can go in here, and the grantee code, this is that company code, so it's the first 5 characters in our case of the FCC ID, and then we can put this product code in, and we can do a search here. So you can definitely do a search on the FCC website, but I find that it's actually a little bit easier. There's some websites and tools that scrape the data from here, and they're actually a little bit easier to use. So I'm going to show one of those, and that's the one that I usually use. So it's called FCCID.io is the one that I like to use. And then we can just do an FCC ID search. So what I'm going to do is I've got that FCC ID copied here that we pulled off of the router. And now, if you don't know this or you're looking up and you don't have the router, generally you can just find it through the part number, but we've got the whole ID. So I'm just going to pop that in here. We're going to run a search. Perfect. And we've brought back one result here, which is perfect. It's for this TP-Link Corporation Limited wireless and router with this part number, which is the one that we were looking at. And if we scroll down here, we can see the exhibits, and this is what we are specifically looking for. Now with this router, you can see we just have the label location and the external photo, which really aren't that useful for us. But if we do a little bit more digging here, we get this FCC change ID document. So I'm just going to open that up, and it will actually preview the PDF on here, which is nice, so we don't have to download it to look at it. And if we read through this PDF, it says that they are looking to change the FCC identifier for currently approved devices from this. So they're just changing the ID from a previously submitted one. So what I'm gonna do is I'm just gonna copy this, and then I'm gonna go back and run another search. So if we just paste this in here with a little bit of digging, all right, perfect. Still the same thing. We got this TP-Link Technologies, 300 megabit per second. This is us, perfect. So if you scroll down here, now we've got a bunch more documents we can start to take a look at. We've got the manual. If we didn't have the manual, this is pretty easy to find, but we've got the manual here. Let's take a look at the external photo, make sure we're working with the proper device. Perfect, just looking at the external photo, this looks like the one that we have. And then this is where it starts to get pretty interesting here. So we've got this internal photo. So let's take a look at that. All right, so let's scroll down. Pretty poor resolution photos here, but if we keep scrolling down, pretty detailed picture here of the board. And you can actually see, interestingly enough, that it's already sticking out to me. We could identify that there's most likely a UART connection here. And you can see that they actually already have the headers here. So we're either looking at an older version of the board that had this header on it, or what's most likely happened is this is just a test board and they left this on for the testing. If you scroll down even further, this is great details here. We've got one of the chips here and we've got the manufacturer and then the part number. So what I'm doing right now is I'm going to copy all of this. So this for sure 100% is good details, and we'll go look at this further. And if we scroll down again, we've got another really high resolution picture here of this chip. And again, I'm going to take this manufacturer and this whole part number and save it for later for more investigation. Another one here. Perfect. Now, so you may be wondering, like, we already had the router open, of course, and we could find this information ourselves. But one of the nice things about the FCC filings is, I mean, if you're doing a penetration test and you don't have your hands on the router or your target yet, then you could start here and actually get some work done before you get that. Or if you're a security researcher, or, you know, this is also what the black hat hackers are doing, and you're looking for a target, well, this is one place to start. If you don't want to actually go buy or get your hands on a device, you're just looking for something, you know, that maybe has exposed UART, or you want to find more about it, well, we can do that for free from the FCC filings. If we just go back to the rest of the filings here too, there is one other thing that I want to show you, and that is these three filings right here that are listed as confidential. You see, unfortunately, we can't download those, but we have a circuit diagram, a block diagram, and the operation description. So if we could get our hands on these, that would be great. But unfortunately, they've made these confidential. So if we just look quickly at this confidential letter, it basically just says that these materials are trade secrets and proprietary information, and they're asking not to disclose these to the public as they might be harmful, and it looks like the FCC has granted that request. Unfortunately, most of the time these will be made confidential, but there have been times where I've come across filings that these aren't confidential, so always worth it to take a look and also see if you can find these. Even still, finding the pictures of the chips and their manufacturers and part numbers will actually give us quite a bit of information to go off into digging further without actually having our hands on the device. That wraps up this lesson. I'll see you over in the next one, where we take a look at the data sheets for these components that we just identified through the FCC website. I'll see you over there. Welcome everyone. So in the last lesson, we were actually able to identify some of the chips on the board, including their manufacturer and part number. The next logical step for us will be to look up the data sheets and see what additional information we can gather from there. Before we do that, I think it makes sense to have a really quick chat about embedded systems and how their hardware and software differentiate between the different designs. Now, this is a subject that could have an entire course or maybe even multiple courses on it. So just keep that in mind, that I'm going to be doing a really quick and broad overview of these ideas. And of course, there is a lot more information and depth and some caveats to what I'm going to say. So first, if you're not familiar with what an embedded system is or what that means, well, what that's relating to is when we have hardware and software that are specifically designed just to work together, and that software has been designed specifically to work on that hardware, and we're not going to be loading additional software or other features for the user outside of that system in its regular use. So examples of that are our IoT devices, where they just have one specific use, and the hardware and software are designed specifically for that. And that's in contrast to, for example, our personal computers, where we can add additional hardware and peripherals, and we can install, whatever software we would like, as long as the software is designed for the operating system we're running. So I'm going to split these embedded systems up by the type of software that's designed for them, and I'm going to break that up into 3 different types. And the first one is what is generally referred to as bare metal. So what I mean by bare metal is that, the designers or makers of the software, they're going to write all of the software themselves, everything, and they're not going to rely on any underlying operating system. So everything that their device is going to do has to be handled specifically by their software, and they're going to compile that and then put that directly onto their device and have it run. Of course, this has some advantages in that we then have the most control over our system. However, it also may be the most complex because there are a lot of things underlying that the operating system takes care of us as designers, and a lot of times it's easy to take those for granted. So if you don't want to handle, all of those background processes and everything that an operating system takes care of, but you don't want to move up to a full-fledged operating system like the ones you would be used to with Linux or Windows, the intermediary option is a real-time operating system, or what is commonly referred to, or you'll hear, as an RTOS. So these are very common in IoT or lightweight systems. And these operating systems, they still take care of a bunch of the background tasks. So things like scheduling of tasks, interrupts, memory management, and communication between different portions of the system or functions. However, they are designed for much more specific tasks, which makes them, of course, much lighter weight in their size. And it also allows them to run their tasks a lot more predictably, which means we aren't guessing about how long it's going to take to run specific tasks. And running the same task over and over again will give you the same outputs and the same amount of time. This differs from, for example, Windows and Linux, where if you, clicked on some specific task or to open something up, you may have noticed, depending on what's going on in the background, the amount of time that it takes to finish that task can vary. Real-time operating systems are a lot less prone to crashing as well. Another really important feature of real-time operating systems that differs from a standard operating system is that we can set the priority of tasks so that high priority tasks will be completed before low priority tasks, and ensures that they are completed when we need them done. This can be important for critical systems, for example, robotics. Outside of their just timing and predictability, their lightweight size also makes them an excellent choice for IoT devices, so you will see these commonly in IoT devices. Now, I've grouped these two together, the bare metal and the RTOS, because generally speaking, you're going to see these running on a microcontroller. So the difference between a microcontroller and what you may be used to in your home computer, a microprocessor, is that microcontrollers are generally less powerful. However, they will include in them some memory and some ROM, so some read-only memory to store our code. So we can compile our code and store it directly onto that microcontroller, and then it also has the RAM built in that it can access, and we don't need to add those externally to our design. I've added a picture here of an Arduino as an example. So if you're familiar at all with, hobbyist electronics, you may have used an Arduino. So this is an example, not of a consumer one that you would see in IoT devices, but just something you may be familiar with as a hobby designer. The Arduino is a microcontroller design. This is the microcontroller right here. And then we just have all these other peripherals to support, the inputs and outputs to it. So then the third software category that we will chat about is embedded Linux. So in this scenario, the designers will go all the way up to porting a Linux kernel and getting it to run on their embedded system. And then we're running a full-fledged operating system or close to the full-fledged Linux that you may be used to using. And of course, this offers lots of advantages for us in that the Linux operating system is going to handle all of the things in the background that we are used to it handling. So all of the scheduling, things like networking, it can take care of all of that for us. And then as designers, what we can do is just write bash scripts and binaries and have those take care of whatever functionality we need. So this can be a little bit easier on developers as it's a little bit closer to just developing for standard Linux. So generally for embedded Linux, outside of a few edge cases, we're going to be running it on a microprocessor. And the microprocessor is different from the microcontroller in that it's usually going to be more powerful. However, with it, we are going to require external RAM and an external ROM. So we're going to need extra chips that we're going to have to add onto our board and interface those with our microprocessor because we're going to need quite a bit more RAM and quite a bit more ROM to run a full-fledged operating system. And we're going to use external specific chips for that. So an example for a hobbyist board, if you're probably familiar with this, the Raspberry Pi, this is running embedded Linux on a single board computer. So embedded Linux is becoming very common in IoT devices just because of its ease to get up and running and write software for. And our router is running embedded Linux, so that we have an idea about the hardware that's involved with it. It will make a little bit more sense, hopefully, when we're looking at the data sheets. So I'm just going to wrap up this lesson here, and in the next one, we will hop over to the browser and try and find the data sheets for these core components of an embedded Linux system that we identified. I'll see you over in the next lesson. Welcome everyone. So in the last video, we chatted about embedded systems and we actually left off talking about embedded Linux and that the router we are using as a target, the TP-Link router that I have a picture of here, is actually running embedded Linux itself. When we were doing our OSINT with the FCC pictures in the FCC application, we were able to identify two of the chips, their manufacturers and the part numbers. And one of them was this one in the middle right here, which is actually the processor. It was that MediaTek chip. And then this bigger one right here, this Zentel chip, this is the RAM. The third one that we weren't able to identify from the pictures is this chip right here, which is the ROM. Now what I've done is I've taken a very high resolution picture with my camera phone. And then if we blow it up, which you can see on the right here, actually able to see in pretty good detail to make out the manufacturer in the part number, which is this CFEON or CFEON. And then the part number is this QH32B104HIP. So if you just look at this with your bare eye, it's actually really hard to tell that there's even some writing on here. And in the past, you would have used either a microscope or a magnifying glass or something to try and read this. But now the cameras are so powerful and high quality on our phones that I usually just use those. They're an excellent tool for Recon and for figuring out what is going on these boards with the traces as well, which is something we'll look at. So not to be underestimated, the power of taking a good high resolution picture and then just zooming that in on the board. I do it all the time. With that being said, now that we've identified the manufacturer and part number for these three core components, we should be able to hop over to the browser and use Google to find the data sheets for them, which is going to give us a lot more information about their functionality. So let's hop over there now. Okay, so what I've done is I've just transcribed over the manufacturer and then the part number from those pictures so that I can easily copy them into Google and that I'll also be able to put them into my notes. One thing to call out here is you'll notice, the manufacturer, that's easy to identify, but then those chips, most of them, they had more details or numbers outside of what I've copied. Now, general rule of thumb is that the first, string of characters that's immediately after the manufacturer, that's the part number. And then if there's a dash and something after it, then that'll maybe be the part number and some options. And then on the other lines, you'll notice that we did have some other numbers. Generally, those aren't part of the part number. They may differ between different batches of chips, and they might, denote something about like what batch they are, where they're made, different information for QA. So we can usually leave those off when we're searching, and we just go with the manufacturer and then that first string of characters after. So I'm going to start with this one. This is the processor, and I think it makes the most sense to look at first. So what I'm going to do is I'm just going to copy this over, and we'll take a look on Google and see what we can find for it. Okay, so the first one here that we see that I've already visited actually is this MediaTek website. So if possible, I'll always try and go to the manufacturer first because they should have the most up-to-date data sheets to look at. So we'll just hop over to the manufacturer's website. Okay, so on the manufacturer's website, we get some details here. And if we read about this, we'll see that this is actually an SoC system on a chip that includes all the functionality that you would need to build a router around it. And we can see here, it's functions mainly for this N300 style router. So it's interesting to see that there is this CPU or chip that is designed specifically for building a router. And this is actually something that you're very commonly going to see in IoT devices where they follow a specific formula where they have those 3 core components. So we talked about again, you're going to have a processor. Generally, it's going to be a processor that's only commercially available. And what I mean by that is only, bigger companies are going to be able to buy them in these mass quantities. And then that processor is frequently going to be specifically designed for a specific function. So in this case, we're looking at a router. And then they'll build out an external RAM and ROM off of that. So if we just scroll down here to look at the specifications, we'll see a little bit of interesting information about it. So the one thing that sticks out to me here is we have the CPU type, which is MIPS. Now, if you're not familiar with MIPS, this is this MIPS 24KEC. MIPS is the architecture of the CPU. So kind of similar to if you are familiar with either x86 or x64 architectures or even ARM. MIPS is just another architecture like that. It's actually a very old architecture and it's not really frequently used outside of these IoT devices. So you won't really see it much anymore except for these IoT devices. Generally, what you're going to see with IoT devices is they'll either be this MIPS style or more common these days is to see it as ARM. So another thing that I'm going to call out here is we actually see the OSs here, and we can see it runs this ECOS and also this Linux 2.636, which has the SDK support, and then also this Linux 3.10. We scroll down here, we actually see there isn't much more information. This isn't actually a full data sheet. So this is quite common on these, only commercially available components. Generally, you'll have to, get in touch with the manufacturer and ask for a data sheet, but if you do a little bit of digging, you can usually find them on the internet. So we go back to the Google results, actually, we see just the second one here. This is a data sheet. It's through this Seed Studio. If you're not familiar with them, they're similar to Arduino in that they make single board microcontrollers and microprocessors and dev boards and things like that that are good for prototyping or for hobbyists and makers. So they're a good resource if you ever see them for data sheets, and we'll just take a look at the full data sheet. We scroll down a little bit. One of the first things that stood out to me, kind of funny to see this is confidential. Interesting to see that. Of course, we just did a very small amount of digging and found it. And on this data sheet, we get a lot more information. So if we want to take a look at the overview, it's kind of interesting to read about. And you can also see all of the core features of it, including this functional block diagram that gives us a little bit of information about how all of the inputs and outputs work on the system. So if we just scroll down a little bit here, this is something that's common in data sheets in that data sheet will be for a few different part numbers that are very similar, but they'll have different packages. And the package that we're looking at, you'll see the part number is for this one ending in NN. And then our package is this DRQFN 156 pins. So the last part, this is just how many pins are on that actual chip. And then this DRQFN, this denotes the actual package of how the chip is laid out. So this QFN stands for quad flat no leads. So you remember when we were looking at the picture of it, it has 4 sides that have inputs and outputs onto it. And then there actually is no leads or like arms sticking out off this. There's just the pads that are directly on the underside of the chip. So we just scroll down a little bit more. I'm not going to go over the entire data sheet, but you're more than welcome to if you want to. But I'm going to call out some of the key things that I see on this data sheet. Okay, so again, in the main features, we see this MIPS, which we already saw. So the other thing that stands out to me is this SPI flash. So we can see that the flash for the ROM is communicating with this SPI format. So this is serial peripheral interface, and this is another communication protocol that we're going to talk about more in depth. So good to see that, and that's how the ROM is communicating. And then we also see all of these other communication protocols that it can use. So these are all just different common communication protocols that you'll see in IoT devices. And we're going to chat about more of them in detail. But the one here that really stands out, we already chatted about, is UART. And we can see that there are 2 UART communications on this chip. Now, the one important thing to note with all of these other communication protocols is that just because there's pins on the chip and they're supported, that doesn't mean that the underlying software is actually going to be utilizing them. However, if we didn't have a UART header, for example, and we didn't see those pins, well, it's still possible that it is in use and we can actually just go directly to the chip to access it. So good to see that and good to know that. If I just scroll down a little bit more, the other thing that I always want to see on datasheets and take a look at is the pinout. And this here is going to give us the pinout. Again, just a quick reminder, there's going to be 2 pinouts here. The first one is for the actual format of the chip that we're looking at in that NN. And you'll see here for readability, they've actually split this up into 4 different quadrants. And this one, it denotes it as the upper left side. When you're looking at chips, generally the upper left side of the chip is going to be denoted either with a circle or a triangle or some sort of tick, and that will help you to determine the orientation of the chip and help you to figure out where those pins go. So if I'm just going to scroll down one more so we can see the bottom left side or the down left side, there's a few different pins on here that I am interested in. The first one is we have this very first UART connection here. So we've got the transmit and the receive lines for the UART. And then we've also got all of these SPI signals here. So all the way from 24 down to what looks like 28. We have these SPI signals that we're going to be interested in because they are most likely going to interface with our ROM chip. So these pinouts are going to be super helpful if we are reverse engineering the board and we don't have any labels and we're trying to figure out what's going on. So there's a bunch more interesting information on this datasheet if you want to read through it, but for what we need to get started, this will give us enough information. So let's move on to the next one. We'll take a look at the RAM. All right, so the first result is through Mouser Electronics. So they're a very popular seller of electronic components. Mouser Electronics and DigiKey are actually 2 of the main places where I get data sheets because generally any of the components that they sell are going to have a data sheet tied to it. So let's hop over there and take a look at the data sheet. All right, so we get a little bit of information about it. We can see it's a 256 megabyte SD RAM. And if we scroll down here, we can get a little bit of information about its features, and we can also see about the pinout. So for us, we're not going to be as concerned about the RAM in this beginner's course because any attacks that are going to target the RAM, those are kind of more of an advanced technique that we're not going to be focusing on. But it is good to have this information, and sometimes you will target the RAM because that will be the only way to get to certain specific things. If they're encrypted, for example, maybe they will be unencrypted at boot up and only stored in the RAM. So if we can dump the RAM, that is one way to get it. And now we have the data sheet for it. So even though we're not going to use it, still good to find it. And I will be keeping all of these data sheets in my notes. Let's take a look at the ROM now. So just a quick note on what a ROM does if you're not familiar with it. Again, that acronym stands for read-only memory, and you'll sometimes hear it referred to as an EEPROM as well, which just stands for electronically programmable read-only memory. And generally these chips are a type of flash memory where we will store the underlying operating system and then all of the additional software that we have wrote for our systems or embedded systems. And usually what we call this package of software is the firmware. And we're particularly interested in this as hardware hackers because if we can dump this firmware and get to it, this is going to contain all of the file system and those binaries that we can then start to reverse engineer. All right, so we identified the ROM as this CF Eon Q32B-104 HIP. Couldn't see it on the chip, but with the pictures, we were able to find it. So let's again do a quick search through Google for that. All right, and the second result here is the one that I found a good data sheet for, and it's through this alldatasheet.com. So before I click on this, I do just want to give a quick heads up about datasheets and datasheet websites. So sometimes for more obscure parts or ones that are, generally only bought through these, big commercial quantities, where you got to get the, data sheet, you got to ask through the vendor for it, they're going to be a little bit more tricky to find. And sometimes these, data sheet websites, they're very popular. Everyone always wants the data sheets, especially if you're building something, reverse engineering or hacking. And there will always be a website that claims to have a data sheet for everything. If you use like torrents, or in the past you use like peer-to-peer downloading software, you may remember like whatever you put in, there would somehow be like some sort of result for it that was like a virus or something. Well, I want to say this, so just keep an eye out when you're looking at data sheets. Use your smart internet browsing techniques and just be mindful. It's no different than if you're looking for, an obscure exploit or something like that. Just keep that in mind. That being said, this alldatasheet.com, I have used it in the past and it's usually pretty good for data sheets. Okay, so it looks like that CF Eon, that is part of this Eon Silicon Solution Inc. And if we scroll down here, we've got this one here that it's pretty much the whole part number of that right here. And I'm going to take a look at the data sheet for it. So looking at some of these main features, the one that sticks out for me here is that it is SPI compatible. So that is, again, that serial peripheral interface. And this just confirms what we saw on the data sheet for the processor. And then if we scroll down a little bit more, we see, it supports these different types of SPI and the different signals that are going to be used for it. So you can see a little bit of a general description here. And then if we scroll up and we actually just go over to the second page here, we are going to see the pinouts, which of course we always want to know. And this is going to be important for us later. We're definitely going to save this because one of the things we're going to do is we're going to try and dump the contents of this ROM so that we can read it. A few other things to take note of is if we just go through a few other pages here, then you get some details about the different signals and how they function. So the different SPI signals, and we just want to keep that in mind. And then also if we just go a couple more pages over here, actually, so we're going to get the different address ranges and the sectors. And then if we just go over one more page here, we're going to get some information about how the SPI functions and the different SPI modes. We're going to chat about this in much more detail in upcoming lessons. So I just want to keep in mind that, it's good that we find these data sheets and we're definitely going to be using all of this. I'm just going to hop over really quickly to that high resolution picture that we took of the PCB so we can take a look at how we can actually trace out those different traces on the PCB and figure out where they're going. So another really useful thing to do with these high resolution pictures is you can either use something like Paint, like I've done here, or you can actually just physically print them out if you have a good enough printer and then just draw the lines on them with a marker or something. But you can actually zoom in enough that you can, trace out these traces to where they are going and then use that to reverse engineer what's going on the board. And this can be super useful if you aren't able to actually get your multimeter in and beep out the continuity. And it can also just be faster this way. So if you remember, I called out that this top left pin here, the second one down from the top, this was the data out. And again, we just see that little indicator here that indicates the top left. Well, on our processor here, this is the top left. And you may recall from the bottom left quadrant that around the top of that bottom left quadrant, we actually had all of the SPI lines. And this one right here, actually, if you count them all out, is what is called the MISO line. So that is master in, slave out. So the processor is generally the master in SPI communication, and then The peripheral, which is the ROM in this case, is the slave. So the slave out would be the same as the data out, and it goes into the master. And we've now traced out this line, and we could trace out the rest of all of these lines as well. And we could even go as far as, if we didn't know that this header was UART, we could trace all of these lines out as well, and we would be able to figure out that these are going to the UART. And that's one way we can start to determine what's going on with these boards and what the different headers and pins are. So we got a lot of really good information in this lesson, and I'm definitely going to be adding all of those data sheets as downloads to my notes, and then also keeping track of some of that core information that we found, because we are definitely going to be using it and relying on it throughout the rest of the course. With that being said, that wraps up this lesson. I'll see you over in the next one. Welcome everyone. So in the last video, we left off taking a look at the datasheet for what turned out to be the flash ROM. Now, if we weren't already suspecting this or aware of it, this just confirms to us that there is going to be some sort of firmware that's loaded onto that ROM. If you're not familiar with what firmware is, especially in embedded systems, generally this is going to contain the operating system and the root file system. And this root file system is going to contain, the file structure for that operating system. And it's going to have all of the files in it, like the binaries and scripts and configuration files that our device requires to set itself up and also to run. As hardware hackers, one of our main goals is going to be to get our hands on this firmware so we can start reversing it and analyzing it, because this is going to greatly assist us in figuring out how the device functions and also to find any vulnerabilities in the underlying software. Now, there's a couple ways that we can extract the firmware off of the hardware itself, and we're going to take a look at those later on. However, sometimes the best way to get this firmware and the easiest way is to just go out on the internet and look for it. There's a couple different places that you will usually find firmware. One of them is on forums or other unofficial sites where people have been able to recover the firmware and then they've uploaded it for other people to use or analyze. And then the other one, which is usually the best method if you can find it, is just to get the firmware directly from the manufacturer. Lots of manufacturers make the firmware available to the public so that they can perform updates to their device when new versions are released. And for TP-Link, that is generally the case. You can usually find their firmware through the support section of the device. So Google is usually your friend here. A quick Google search and we can usually find it. So for our router, it's at TP-Link 84, this one right here. And I'm just going to add firmware to it here, first one. And then we've got this download link and it's under the support for our router. Okay, so I'm just going to click on the firmware section here. And if we scroll down quickly, just one of the things to note here, we've got the bug fixes and modifications. And if we look at number 10, they've kind of just tucked it down here. At the bottom, we get this enhanced device security. So usually when I see this, what this means is that, this version, one of the main reasons they released this is probably because there was a CVE or other vulnerability disclosed to them in the previous firmware, and then they fixed it. So just a little bit of foreshadowing to what else we're going to be looking at. But in the meantime, I'm just going to hit download here. I've already downloaded this before, and I'm going to save this, and I'm definitely going to add this link to my notes and add that we found this firmware to my notes so we can use it later in our analysis. That wraps up this quick video on Recon and how to locate the firmware. I'll see you over in the next one. Welcome everyone. So in the last few lessons, we took a look at the hardware Recon. We were able to identify a few of the core chips, get some data sheets on them, and then get a bunch of important information that we're going to use further down the road when we're doing our hacking. The next step that we're going to take is we're going to move on to Recon for another attack surface. And the one that we're going to be looking at is that internal network that the router hosts. So you may recall previously I chatted that we're not going to be focusing on this attack surface because there's already a lot of excellent training already through TCM Academy on internal network penetration testing. However, I do think it is important for us to at least do Nmap scan and see what ports and services are running on the router before we start poking away at the hardware. Now, if you're running a setup similar to me where you have Kali Linux as a virtual machine that you're going to be using as your pen testing machine, or you really have any other distro of Linux or virtual machine running, then you're going to probably need to make a change to your VM settings. So by default, especially if you're going to be using a Kali VM for ethical hacking, you're going to have your network adapter set to NAT. So this is great for ethical hacking anywhere where we're going to be actually, running exploits. If we still need internet, but we don't want to be connected to our home network or our host network, then this adds that extra layer of separation from it where we actually won't be on that home network. However, what we're going to do is we're going to connect to the router's network, so the one that it creates, and the easiest way for us to then get access to that through our host computer is to set this to bridged. So I am personally using VMware Workstation Pro, and I'll show you how to set it in that, and then we'll take a look at just the regular VMware Workstation Player, the free one, and also how to set it in VirtualBox. So what you're going to do in the VMware Workstation Pro is if you just go to the computer lists, and this is the Linux that I am using, so I'm just going to double click on it. And then if you go in here, network adapter settings, or you can go up into VM and then settings through here. I'm just going to click on this, and I'm going to set it to bridged, connected directly to the physical network. And I'm going to click OK. Now, if I just go back in there quickly, I do want to show one thing, or you'll see here, like it's saying that it's automatic. So just one thing to keep in mind, and this is only for the VMware Workstation Pro, you may need to go into your settings and go here and go edit and then virtual network preference. And then this virtual network editor will pop up and you'll see under the auto bridging here, you may need to change your automatic settings here. So I'm just going to set it, and this is the one where I have my Ethernet port, and I'm going to be using Ethernet for connecting to the router because then I can still have my Wi-Fi going and I won't get kicked off the internet. So just only select one here and choose whatever you're going to be using. So if you are using your wireless, then make sure only your wireless is going to be connected. So however you're going to connect to your router, pick that from here. Again, this is only for VMware Workstation Pro that you need to set this in here. Just going to go cancel and cancel in here because I'm happy with the settings, and I'll just leave it as that for now. The next one I'll show quickly is we'll just pop up this VMware Workstation Player. Just drag it over here. All right, so when it launches up, we get this list of the VMs. I've got a Kali Linux one right here, and you'll notice I actually can go into edit machine settings here. And same thing, we'll just set it to bridged. Now, the one thing I've never figured out how to do this, or if it's even possible in the free version of VMware. I usually only use the Pro one, but you'll notice you can't, there's no settings, unfortunately, for changing the virtual network preference editor. That's something that is tied to the Pro version. So I believe this is just going to pick one. So if you do have two networks connected, like you're connected to your regular Wi-Fi and then Ethernet into your actual router, it may not pick that up. So you might need to just quickly disconnect from one before you start it. So something to keep in mind. If anyone does know how to set this in the non-Pro version, then let me know. I'd love to know how to do that. So I'm going to hit cancel here, and then we'll take a look at VirtualBox. So I'll just drag that one over quickly. And in VirtualBox, so again, we're going to click on the VM we want. I've got this Kali Linux one that I was playing around with. And then if you go into the settings here, and we go down to network, just go from NAT to bridged. And then the nice thing is in VirtualBox, you can actually just change it right here. So pick whatever one you want. So I would pick, this one is the Ethernet adapter that I have on my laptop. So pick whatever one you want there, and then you just click OK. I'm not going to. I want to leave that as NAT. So just go back over to VMware Workstation. And So the one really quick thing I will call out is it's good to have it on this NAT if you're doing other things. You probably don't want your penetration testing VM to be connected to your home network. So just if you are using the same Kali Linux that you use for other things and connecting to VPNs and all that's great stuff that we do as ethical hackers, remember that you set it to this and then you should set it back to NAT afterwards. What I do is I actually have this VM set up that I only do my hardware hacking on, and that's it. So if I accidentally leave it on that or whatever, it's fine. And then I have another Kali Linux where I do my other ethical hacking stuff. So very quickly, I'm just going to power on the router, and then I'm going to plug into the Ethernet port on it. I'm going to be using Ethernet to get to it. You can also connect to the Wi-Fi network that it does as well if you want. The SSID for it and the password are on that label on the back of the router by default. So I'm just going to go plug it in and connect right now. One quick thing to note is we're not actually going to be working with the external network in this. So we're not actually going to be hooking it up to the WAN. So if you are plugging this into the Ethernet ports, pick one of the 4 orange ones on it and just leave the blue one disconnected. The blue one's the one that would go to the modem and would give us actual internet connection, which we're not going to be using for this testing. So I'm going to go plug that in right now. All right, I've got mine plugged in and I'm just going to power on the virtual machine here. Okay, so now that I'm logged in, I'm just going to do a really quick sanity check and make sure I'm on the right network. I'm going to run IPA here. Perfect. So I see I've got this 192.168.0.100, and I'm on this 192.168.0.0/24 subnet. So that is the default subnet for this TP-Link router. If for whatever reason you weren't able to find that out, you can find it easily through Googling it. So now that we know we're actually on this network, the very first thing we're going to do is we're just really going to quickly set up the router and make sure we can access that. I'm going to assume that pretty much everyone has probably set up a wireless router. So I'm just really going to quickly gloss over that. Generally, what they're going to do is they host a internal web server on port 80, and then that's where you go to set them up. And they are usually the very first IP address in that subnet. So this 192.168.0.1, that's the IP address by default for the router. And if we go to it, we get this website to log in. And I do just want to call this out that this is nice to see on routers now that manufacturers are doing this, where they don't just have a default password. They force you on the very first setup of it to actually create a login password, which is good in case, we did see a bunch of these were connected out to the internet. And so this, would be exposed. So this forces people at least to set some password instead of just rocking with the defaults. So I'm going to make a password here and set this. Just going to go with the really secure 1234 QWER so I can remember it. You can set it to whatever you want. So before I click start here, just a quick call out before this little pop-up goes away that we can also set this up. It says through this TP-Link Tether app, and we can scan the QR code here to get it. So again, we're not going to be looking at the mobile app in this course because there's already a really good course on that. But just a quick call out that, of course, we do have a mobile app that is part of that IoT ecosystem. And if we were doing a full scoped penetration test, then this app may be included in that as well. So interesting to see that. I'm just going to click start here, create this password. And then now we can get to all of the settings for the wireless router, which we're not going to change any of these now. I'm just going to leave it as is. And this gets us to where we can start doing an Nmap scan on this router. So I'm going to wrap up this video here, and I'll see you over the next one where we start to run our Nmap scans. Welcome, everyone. So now that we're on that same network as our router, we can kick off our Nmap scans. So I'm just going to start with the tried and tested method of Nmap scan that TCM uses. It will work for us as well. So again, that's just T4 for the speed that we want. We're going to go just all ports on this TCP scan, and we'll ask for all the information, and then we're going to target that router, which the default IP address of it is at 192.168.0.1, and I'll just let this run. It's going to take a couple of minutes. I'll see you back over when it's done running. Okay, so our first scan results are back for that TCP scan, and if we take a look, we see that we have SSH open, and we've got the version here, so it's running this drop bear, and then we get some versioning as well. So that's great to see. We've already got some banner grabbing and versioning that we can take a look at. We already knew this one was open because we already went to the web server for it, and this is that ADTCP where it's hosting that configuration website. Very common to see in IoT devices and especially routers where it hosts a website that is the UI for changing settings and things like that. And we get some of the information and fingerprinting back about that website. And then if we scroll down here, we see that we also have this 1900 open for UPnP, which is Universal Plug and Play, which makes sense to see on a router to be open. So those other devices on our network, if they are using Universal Plug and Play, they can connect back to the router and ask it to open up the ports that they need in order to function. And nice thing about this is we start to see a little bit of banner grabbing here. So we get this UPnP devices and the SDK versioning number. And then we also see the Linux kernel version that's running here. And it's that 2.6.36 that we saw from the data sheet on the CPU, on the processor. So then we are able to confirm that version of Linux. And if we just scroll down here, we'll also see a little bit of that fingerprinting, that it was able to detect that Linux kernel of 2.636. So when I'm scanning IoT devices in particular, I also always like to look at the UDP ports as well and not just do the TCP ones. Again, with these IoT devices, sometimes it can just be the wild, wild west of what they're using. And I like to take a look at the UDP ones. So the next thing we're going to do is we're just going to run a quick Nmap scan to check for the top 100 ports on UDP, because this does take a while. So I'm just going to quickly run that. If you have never done that before, just keep in mind that you need to do this under sudo. So it is sudo nmap and then it's -s u like this, lowercase s, capital U. And then we're going to go dash top dash ports equals 100. And we'll set the IP address here. And run that. This will take a little while since we're doing the top 100 through UDP. So I'll just pause it here and come back once it's all done. Okay, so that took a couple minutes, but we're now done, and we can see at those top 100 ports, we've got the DHCP one here, which is open but possibly filtered, and it makes sense that that would be there on a router. And then we also got the UDP port for this UPnP as well. So nothing crazy for this router, but I just want to show this because I think it's really good to always run the UDP scans on the IoT devices just to see what's there and if there's anything out of the ordinary that we can look to attack. So if we were looking at this device purely just from an internal network assessment viewpoint, either we're doing an internal network assessment and then this has come up in our scope and we think that maybe this is a good target for us to get more access. I mean, routers are a great target if we can get on them because there's so much data that comes through them to see. Or if, for example, this, was just a hack the box or something like that, and these are all the ports that are open, well, then we're stuck with going through these ports. We would do so, in a methodological format where we check each of them. We'll, go through the versioning of them, look for common exploits, and then probably end up at the web server itself. So this port 80 web server, and then we're going to do all of the, web app pen testing things that we would do, enumerating the website, directory busting, running Nikto and fuzzing and all of those things. So on an IoT assessment, it's okay to do all of those. And if we're trying to be really thorough, then it's probably good. We've got some versioning here. So, we can go look and see if there's any exploits for this, for example, or the UPnP. We've got some versioning as well that we could go and look if there's any exploits for it. However, the focus of this course is we're going to actually, still be looking at possibly targeting some of these services, but we're going to do so, from the inside with the aid of the hardware. So as far as the, network recon and assessment go, I'm actually just going to end it here, and we're not going to go, any further into the web server or running any further scans on that web server until we actually have our hardware shell, and then we can also see what details we can get from that as well. Again, I would suggest take all of this, add it to your notes, take a screenshot, or just copy and paste it into your notes as you would with any other testing or assessment. I'll wrap up this video here and I'll see you over in the next one. Welcome everyone. So before we move away from the recon phase, there's just one last thing that I want to quickly show that I find really helpful when looking at these IoT devices. Either if you have one picked out that you're going to be targeting, or you are performing a penetration test on it, or honestly, even more importantly, if you are looking for a target that you want to do some security research on, I like to go and look at the vulnerabilities that have already been disclosed and patched for that IoT device, and then see if there's any, common themes or things that keep coming up. And that gives us an idea if, it's going to be even really possible or realistic for us to find something, or what we can specifically look for. So I just like to use Google for this. Again, Google is your friend, and we will just look up this TP link. Again, so it's this router. And then I'm going to look up CVE. And we'll get a bunch of results for it. So the very first one is actually one that I like for IoT devices because it makes it really easy to group those exploits for a specific hardware product, which is what we want in IoT. But you can use your favorite CVE repository. The MITRE one's great, or I'm going to scroll down. The CVE details, of course, here's the MITRE one. These are all good as well. I'm just going to take a look at this one here. So what I'll do is I'll just take a quick browse through and I'll kind of look at the high impact ones, and I'll see in the details what was discovered and if we start to see any common themes. So looking at this one here, for example, the vulnerability allows attackers to execute arbitrary code on these affected installations. And then it's saying we can bypass the authentication. And this flaw exists within this ATED_TP service, and the issue results from lack of proper validation of a user-supplied string before using it to execute a system call. So already we're seeing this lack of proper validation of user strings. If we scroll down a little bit more here, I want to take a look. We got some command injection here. Taking a look at some other ones. Got a buffer overflow on this HTTPD daemon. Again, we see the firmware version. We can use an arbitrary GET request on the page for the system tools of the Wi-Fi network. So this is, again, that web server. We can make a GET request to it and then have that be passed down into this HTTP daemon where there's a buffer overflow. So again, we're seeing if there's buffer overflow, probably not proper input validation. Scroll down in here, we see a stack overflow again, in this function right here. And if we keep scrolling down, here is another one, buffer overflow in that HTTP daemon, again, coming up once more with the same GET request to a configuration page that's being hosted on the web server. And if we keep looking here, here's another one, execute arbitrary code through that TCP or TCP port 80, does not properly validate the length of user supplied data. And again, that's led to remote code execution. So if we keep scrolling through these, we're going to keep seeing that theme where we don't have proper input validation to things that we can supply to that web server. And then it's passing in those user inputs through that web server then to underlying services or functions that the router is running. And those are generally wrote in C or C++, and we're able to either get some sort of buffer overflow or we're going to get command injection. And we can see that theme being just going over and over and over again. So when I see this gives me a heads up of, major thing that we should definitely be looking for and helping planning out our attack. Really quickly, I just want to show you two other resources here. So what I'll usually do if I find these CVEs that are interesting is then I'll go and see if there's a blog post or anything about it. One of the really cool things that I love about the cybersecurity community is how open people are with sharing information and passing on how they discovered things and their techniques. And you can usually find blogs from the security researchers who found this that outline exactly how they found these vulnerabilities. So I've got two pulled up here. This one right here, we're going to look at in more depth, but I just want to quickly call it out as part of the Recon. All the credit to this Tran Min here who found this and he's wrote up about it. So we just scroll down, we can start to see a whole bunch of descriptions, and you can start seeing he talks about the vulnerability analysis, block diagrams, even code. So really, really good details about how we found this. And then I also found this one here. Again, all this credit to this Gianluca Paciella, who found this. And if we scroll down, we can see his assessment. And again, we're seeing code, and he gives us details about, how this function works and how he's able to reverse engineer this. So a lot of really great details about this. We're definitely going to look at these more in depth, but just wanted to call this out as part of the recon steps because this is something that I usually look at when I'm doing recon, and I would encourage you to do so as well. So that wraps up this recon portion. In the next video, we're just going to do a quick overview of the notes that I have so far, and then we'll move on to hacking. So I'll see you over in the next video. Welcome everyone. In this video, we're going to be doing a review of the testing notes that I've taken so far during the recon phase of this course. I've stressed a couple times about the importance of taking notes and that I will be adding our findings to my notes. So I wanted to give a chance for everyone to see those notes. And this will also serve as a good review of all the things that we've taken a look at and discovered so far in our recon phase. If you want to see a copy of these notes, they are available in the course GitHub, so you can also get to them through that, and they're in this testing notes folder called testingnotes.md. As I've mentioned before, I always like to include a few test details in my notes about the equipment that we're testing. So you can see here, I've started out with noting the manufacturer, the part number, and then also the serial number. If you're doing this in a professional environment, then keeping track of the specific serial number is going to be important because there might be multiples of the device around at hand, and you want to keep track of exactly which one you're performing your testing on. I also like to keep a note of the test equipment that was used. For this course, I think it's sufficient just to list out what equipment was being used, but in a professional environment, you may also need to keep some details about the actual serial number of that equipment because it's possible that there's calibration data or other testing data that's tied to that equipment to certify that it's okay to use for the testing. So we use that multimeter, and I've just listed the manufacturer and part number. Same with the logic analyzer, and I've also taken a note of the software that we used. In the initial recon, we started with our visual inspection. We took a look at the router and also the internal PCB. On the outside of the router, the one piece of information that stuck out was the FCC ID, so I copied that ID down, and I've also added a quick picture of it to my notes. After that, we opened up the router case, and we did so by removing those two Phillips screwdrivers and then snapping open the pressure fit container with the spudger tool. I snapped a quick picture of the internals of the router for future reference. I also noted that we saw 3 chips of interest on the PCB for further inspection, and I've denoted those as A, B, and C on this picture. After that, we moved on to the onboard testing. We noted the presence of a test connection that appears to be a UART connection. We based this off the fact that it had 4 pins and they were labeled with VCC, ground, RX, and TX, and this is shown in detail D here. We then verified the operating voltage of the PCB at 9 volts, and we did this by testing the voltage drop across the input jack with the multimeter. We then identified a ground connection on P1, which is detail E here, and we did so by using our multimeter to test the continuity between P1 and the ground on the jack. We then moved on to testing the suspected UART connection with the multimeter. We did so we could verify that the pins matched the silkscreen and they behaved in a way that we would expect UART to. First, we measured the VCC voltage, and we found that to be 3.3 volts, which confirmed the operating voltage of the UART at 3.3 volts, which is really important for us to know for our future testing and the equipment that we're going to use to do so. We then verified the ground connection by checking the continuity between the ground pin on the UART, and the continuity test confirmed that that ground is actually in fact a ground. We tested the RX or receive pin by measuring the voltage drop between RX and ground was 0 volts. Just to check that this also wasn't grounded, we did a continuity test between that pin and the ground, and there was no continuity, which confirmed that it was actually at 0 volts. We then measured the voltage on the transmit pin, and during standard operation, we saw it was approximately 3.3 volts, which was to be expected. After confirming that pin out and based on the observations of the pins, we suspected that this actually was a UART connection. We then checked for an output on that transmission pin during boot up by power cycling the router and then measuring the voltage drop over the TX pin during that boot up. I noted a fluctuation on that pin from approximately 1 volt to approximately 3 volts, which suggested a busy and active transmission during boot up. We then soldered our through-hole inline header pins to the suspected UART connection, which is shown up in this picture here. So you may have soldered them yourself, or you may have gone with that twist tie method. Either one is fine. I just kept a note of that. We then attached our logic analyzer to the transmit and ground pins of the UART connection, and we captured that transmission during boot up. Here I've taken a screenshot of a single frame. When we manually inspected the framing of that signal, this confirmed a UART transmission, and we noted the start bit, 8 data bits, 1 stop bit, and no parity bits. We also measured the baud rate as 125,000. So you remember we measured it here, or we could calculate it as 1 over this timing. We then looked up the common baud rates and determined that based on those standard serial baud rates, we suspect that the baud rate for this router is actually 115,200. Based on these findings, we then applied a UART decoder to the channel, and we used the below settings. So again, that's this baud rate, 115,200, data bits 8, parity none, stop bits 1. Just a heads up, you may commonly see this referred to as 8 none 1 for how this is set up. It's just very common to, give the UART connection details or serial connection details as baud rate, data bits, parity, and then stop bits, but they won't actually say what those are. You would just see it written as 115,200, 8, none, 1. Of course, we then decoded that UART signal, and we confirmed those UART parameters were correct because we actually got text back in ASCII characters, and this showed the presence of a bootloader and boot up logs, and we're going to investigate those further. Great finding for us to see these. After that, we moved into our OSINT and online Recon. We used that previously located FCC ID to find the FCC equipment authorization filing for the router. So I just linked it here. I think it's always good, and I've done this myself, to download all of the PDFs and everything just in case somehow they go offline or something like that. It's good to keep a record of the PDFs, which is something that I have done as well. Of course, we noted in that filing that the ID has changed from this previous TE7 and then the part number. I just got a screenshot of that document. So we then looked in the previous filing, and we found those internal photos of the router. Unfortunately, the schematics, functional description, and block diagram were redacted as confidential. We got these nice pictures of the internals of the router, including these two that showed a very close-up picture of some of the chips in question, and we were able to pull the manufacturer and part number off of those. Unfortunately, the markers on chip C were not readable in the FCC picture, so we returned back to our test router and we took some high-resolution pictures, and we were able to blow up those pictures to ID the chip, and we ID'd it as this Cepheon QH32B104HIP. We then went ahead and looked for the data sheets for each of the chips. So I've got some notes about the first one, the MediaTek. We noted that it was a system on chip, which is commonly referred to as an SoC, and this contained the CPU or the processor. Some of the important details included that this is a purpose-built SoC for N300 routers, and the CPU is this MIPS 24KEC. We also know the support of these two Linux kernels, and also that it interfaces with the flash memory via SPI. Of course, there was lots more important details in the datasheet, so I've included a link here. I also downloaded this myself. We then checked this Zentel chip and noted that it is the RAM, and we were able to locate the datasheet for it here. Finally, we were able to ID this Cepheon chip, and the full part number for that is listed here. We noted that it is a flash ROM communicating via SPI, and we got the whole datasheet here, which importantly contains that SPI information and the pinout. Next, we did a search for the firmware that we suspected would be loaded onto this ROM, and we were able to find it on the official support page for the router, which I've linked here, and I also saved a download of that. The next thing we moved on to was the initial network recon. We connected our test computer to the network, and we found the router IP address as this 192.168.0.1. We then performed Nmap scans for both TCP and UDP. Got a screenshot of the TCP scan here. We found there was the 3 ports open, the port 22, which is SSH running the drop bear and the version. That port 80 was HTTP, and we noted that it is hosting the router's configuration web portal. And then we also found port 1900, which has the UPnP and a little bit of versioning for it. One notable detail that we found was that this confirmed our suspicion that the router is running this Linux kernel 2.6.36. We also did a UDP scan, and we revealed two ports on it, this port 67, which is the DHCPS, and the UDP port of this UPnP. We then wrapped up by doing some scouting on previously disclosed CVEs, and you may recall in those previously disclosed CVEs, we noted that there was a common theme of a lack of proper user input validation on forms and inputs in the web portal that led to either buffer overflow or command injection of an underlying function or service being called. I then put a link to this list on OpenCVE of all those CVEs and the two blogs that we found about the interesting CVEs. That wraps up all the notes that I've taken. If you took different things or more details, then good on you. I would say the more details, the better for these notes. We're definitely going to be relying on these notes and coming back to them frequently throughout the rest of the course. That wraps up this video and also the Recon portion of the course. I'll see you over in the next one. Hey there, hope you're enjoying the course. We'll get back to it really quickly, but before we do, I wanted to call out again to just make sure you are subscribed both to my YouTube channel, which I'll link down below, and also to the TCM Security YouTube channel, this one that you're watching the video on. So I would really appreciate it if you just take a second and check, make sure you're subscribed, and if not, hit that subscribe button for us. Thank you. Welcome everyone. So in the last section of the course, we performed our recon, and because of our thorough investigation and testing, we identified this UART connection here where we were able to verify the voltage of it. We checked to make sure all of the pins are as they are labeled, and we were also able to identify during boot up that there was a transmission of the boot up logs and potentially other logs coming off of the TX pin on the UART. We also confirmed the baud rate of the UART and all of the framing parameters, so we already know those. We also were able to determine that this router is running a version of Linux, and because of this, it's likely that this UART connection is also listening on its receive pin for commands, and we may be able to get some sort of remote shell connection through the UART. I mentioned that looking at those boot up logs through the logic analyzer is not the best way for us to interact with that and do this. And in this lesson, we're going to take a look at how we can connect this USB to serial adapter that we have to the UART connection, and then connect it to our laptop and actually be able to get a terminal session and a remote shell into our router. So hooking this up is pretty straightforward, especially since we already have confirmed out these pins. Just one quick reminder for the hookup that the ground, of course, is going to go to the ground, so those two match up. We do not need to use the VCC on either the USB to serial adapter or the router because they're both going to get power from their own power supplies. Of course, the router through the jack and the USB through this USB portion. Then, of course, we're going to need to cross the transmit and receive wires. So the transmit from this USB serial adapter is, of course, going to go to the receiving pin on the router. And the receiving pin of the USB to serial adapter is going to go to the transmit pin, which is this top one here on the router. It comes with this female to female jumper cable to assist in this connection. So that's one of the reasons why we have soldered on or connected with the zip tie this header pin to make it easier to facilitate that connection. So I'm going to connect mine right now. Just keep in mind your colors may be different, so you might end up having to use different colors. The color ultimately does not matter that you use, just so long as you remember to correctly set the pinouts. Okay, so on my board, I have chose to use brown for the ground. I'm using red for the RX pin on the router and orange for the TX pin on the router. So I'm just going to connect those now to the USB to serial adapter here. I'm going to start with the ground, which is the brown one. And then I suggest you don't leave the middle one, which is the receive one, to the last. So I'm going to do that next because it is hard to connect those afterwards if you are trying to connect it in the middle. So the receive on this, of course, is going to be the transmit from the router, which is this orange cable here. Perfect. And now I'm just going to connect the red one, which is the receiving pin on the router, to the transmit pin here on the adapter. Okay, so that is how to connect those before you plug this into your laptop, which is what I'm going to do next. I do strongly suggest that you double check these pinouts, make sure they're okay, because we, of course, are going to be plugging this into our laptop. We don't want to cause any damage to that. And we've already tested this on our board and we know it's 3.3 volts, but if you're doing this for any other devices, I strongly suggest you check the voltage, because the last thing you want to do is hook this up to a higher voltage and then have it damage the internals of your computer. So I'm going to swap over to my computer, plug this in, and we'll leave the router unplugged for the time being. So just keep that in mind. I'll see you over at the computer. Okay, so I'm just over on my laptop here and I've got my USB to serial adapter plugged into the laptop. I'm just going to do a quick ls USB here to list out my USB devices on the Kali VM. And notice here that I do not have that USB to serial adapter in any of these. So what that means is I need to connect it to my VM. If you're using a VM, you're going to have to do something similar. I am on VMware Workstation Pro again. So the steps for that is to go up here, VM, removable devices, and it is this Silicon CP2102 USB to UART bridge controller. And I'm going to go connect here, which disconnects it from the host, which is what we want. And click OK. If you are using VMware Workstation Player, the free one, it's the same step, and then it's very similar in VirtualBox as well. So if you're not familiar with how Linux handles devices that get plugged in, everything in Linux is either a file or a folder, if you just like boil it down to its most basic essence. So it's no different for devices that get plugged in, and they go in the /dev folder. In order for us to interact with this device through the terminal, we're going to have to figure out the name of that device file. So to do that, we can run this command is ls-l, and it's going to be, we're looking in the dev folder, and we're looking for the serial devices. And then we can go by-id here. If we run this, perfect. So we get this list here, and we can verify on the left, it is this USB Silicon Labs CP2102 USB to UART bridge controller that we suspected. And then more importantly here, we see that it is this TTY USB1, which is the device name, and that's going to be in that /dev folder. So we're going to use a tool called Screen to connect to that. So I'll just open up the man page quickly here for Screen. And just really quickly read it. You can see it is a screen manager with terminal emulation. We can get a full screen window manager that multiplexes a physical terminal between several processes, typically interactive shells. So this is perfect for exactly what we need it, and we can use it to manage that terminal interactive shell between the serial adapter and our laptop. So I'm just going to hit Q here to get out of here. So depending on the permissions of the user you're using and how you have your root folder permission set up, you may need to use sudo to get Screen to properly access that device. So I'm going to use sudo because I'm not logged in as root here, and I don't give this user permissions to that root folder. And then I'm just going to run the Screen command. Then the next thing we need to do is tell it what device we want to use. So it is that TT1 USB 1, make sure to not forget the capitals in Linux. And the only other parameter we need to pass is the baud rate. The reason we don't actually need any of those other framing parameters is that we are just using the default ones on the router, and that is the 8 data bits, no parity bit, and 1 stop bit. So by default, Screen will also use those, which is nice. So we just need to put the speed in here. But what I want to do is to just really quickly show you what happens if we have the wrong speed and what that looks like. So I'm just going to put in 9600 here, another very common baud rate, and then I'm going to hit enter. All right, we see nothing here, and that is because I have the router powered off. So what I'm going to do right now is I'm just going to power on the router. So I'm going to plug it in. All right, and it's plugged in, and perfect. We start to see all this garbled messaging here that can't be translated. And the reason that I wanted to show you this is if you're starting to connect, through serial to a bunch of devices, you're eventually going to start seeing something like this. And what this means is that you have some of your serial parameters wrong. So either it's not using that standard of the 8 data bits, the no parity, and the 1 stop bit. So something's wrong in your framing. Or what's most likely is you have your baud rates wrong, and then it's not able to translate that to those ASCII characters. So what I'm going to do here is I'm going to quit out of this. Now, you'll notice in screen, it's kind of taken over our terminal. So in order to get out of this, you can hold Control and A in screen, and then you can input other characters that will do other things. So one of them is D, which is to detach. So if I hold Control and A and then hit D, it's going to detach from us there. So luckily for us, we actually know the proper baud rate of this. So I'm going to put that in here. Again, we'll just run the screen canon again. So sudo screen, and then it is that /dev/tty USB1 for me. And we know the speed is 115.200. And I'm just going to unplug my router here quickly so that we can see the whole boot log when it comes in. So we'll just launch that up. Perfect. And now I'm going to plug the router back in, and we should be able to see in proper ASCII the boot log booting up here. Okay, perfect. So I'm starting to see all of this messaging coming through. Some really good details in here that we're going to look at in further, but for the time being, I'm just going to let this all scroll through here. Okay, so here we see some messages that are just coming through, and if you get past this where it's setting the drop bear SSH key and some details about that, you're going to start to see just some of the same logs coming over. And what that shows us is that we're past that boot log, we've handed over to the Linux kernel, and now we're just getting these regular log messages that we'll see out. But we should still be able to get a shell here. So if you hit enter, and you're going to come up with a shell. So what I'm going to do is I'm just going to quickly try who am I? And you'll see here I get that who am I not found. So a couple things there that happened that I just want to quickly show. You'll see like when I was messaging, we got another log that came through. So like kind of like up here, it kind of just kicked me out of the shell for a second. But since we're in this terminal emulator, I could just hit the I and then enter. And we do then see that we have this who am I is not found. So first thing a lot of people probably do when they get a shell, myself included, is check this who am I. Well, in these embedded systems with Linux running, size is a really big factor. So they won't include any of the binaries that we are used to using if they're not absolutely needed, and we don't have who am I. So if we just want to quickly run something though, and we hit enter, we can go ls and list it out. So we can see here that we are in the root file system there. Now, it may be tempting to go through and enumerate this whole device and do your standard Linux enumeration. But since we're on a hardware system here, our goals are going to be a little bit different, and we should also probably take a look at the bootloader. So what I'm going to do is I'm going to pause this video here since it's getting long, and then in the next one we will take a look at how we can read through that bootloader and any important information that is in there before we actually move on to enumerating through the shell connection. So if you're going to keep following along, just leave everything hooked up as it is. I'm just going to pause the video here, and I will join you over in the next one. Welcome everyone. So I just got a little interrupted there in the recording, but I'm here on the next day, and in this video we are going to pick up where we left off with our shell connection through the UART to our router. And in this video, we're going to take a look at some of those outputs and logging during the boot up, and we're also going to learn about how the bootloader works. So the first thing we're going to want to do is actually scroll up and take a look at what was going on during that boot up. And you'll notice if you're using screen and you left off where we did last time, that there's no way to actually scroll up. And if I hit up arrow or page up, it doesn't actually do anything. So in order to access the buffer and be able to go back and look at those previous logs, we have to again hit the Control A, and then while holding Control A, it is the left square bracket or left squiggly bracket. And if you hit all three of those, it will go into copy mode, and then I can scroll up. So what I'm going to do here is I'm just going to page up to the very top of where we started recording. Perfect. And yours should start with the same set of what I believe are memory addresses, and then it gives us du setting cal done. So the very first thing that we see here actually is this U-boot version, U-boot 1.1.3, and then it gives a date of when this is released. And then we get a little bit of information about what's going on with this bootloader. So U-boot stands for Universal Bootloader. It is a very common bootloader, open source bootloader that's used in embedded systems. And before we go any further, actually, with reading these boot logs, I think it makes a little bit of sense if we just chat at a high level about what happens during the boot up of an embedded Linux system. So I'm just going to hop over to the whiteboard quickly, and we will take a look at that. So at a high level, I'm just going to list out that boot sequence. Now, generally the very first thing that's going to be happened is that the CPU is going to run what some people call the ROM code, or it's also referred to as the primary program loader. So I'm just going to call it the primary program loader in our example today. And over here, I'm just going to draw out a little bit of the architecture of our system. So we'll start, since we're talking about right now, with the CPU. Now, you may remember in the CPU, I mentioned that generally, if it's not a microcontroller, it's just a processor, then it's not really going to have any built-in RAM and ROM. Well, that's not entirely true. There's going to be a very small amount of RAM and read-only memory inside the CPU. It's not really going to be meaningful for us to, run much code or anything like that. But what it can do is it can actually hold this primary program loader. In this primary program loader, this is generally already loaded on the CPU, and it's written by the CPU manufacturer. So it's not something we necessarily need to worry about. When the CPU initializes, it's going to have the instructions to just jump to the code that's in that primary program loader, and it's going to execute that. And what the primary program loader is going to do is it's going to actually then look for what's called the secondary program loader. So I will just add that to our list here. And the secondary program loader is generally then going to live on, we talked about this other component of the ROM. And that ROM is generally going to be partitioned up into a few different partitions. So usually it's going to be more than 3, but we'll just put 3 here. And in our case, and for most embedded Linux systems, that secondary program loader is going to be U-boot, which is what we saw in our boot up screen. So I'll just put a U here for U-boot. So what that primary program loader is going to do is it's just going to go, and then it's going to launch U-boot, which is going to then copy itself over to the RAM. So we've got our third component here of the RAM. And now U-boot, I've put it as this drop down here and not just called it the secondary program loader because it can run either in 1 stage or 2 stages. So if we have just a first stage, then all its responsibility is going to be is just to initialize itself, and then it's going to bring over, again, the second stage of U-boot. And then that second stage of U-boot is then going to perform that boot up process of loading up the Linux kernel and doing whatever needs to be done to help that Linux kernel get started and then hand over control to that Linux kernel. So we've got our Linux kernel here, so I'll just put K here. And that U-boot is going to, load up that Linux kernel, put everything into the memory that needs to be there for it to set itself up, and then it will hand over control to that Linux kernel. And then generally what that Linux kernel is going to do is it's going to unpack the root file system. So I'll call that as RFS, and we'll put that as our other little chunk here on our ROM. And it's going to run some sort of initialization script. So we'll just call this init. So now that we've got an idea of how this boot sequence works at a really high level, let's hop back over to the terminal so we can make sense of what some of those output logs mean and what we're seeing taking place there. Back over at the terminal now, hopefully with that quick overview of the embedded system boot process, some of these log messages are going to make more sense to us. So we left off looking at this U-boot 1.1.3. Again, U-boot, this stands for, the full name of it is DOS Universal Bootloader. It's that open source bootloader, and it's very commonly used as the SPL or secondary program loader in embedded systems. So when I was very first looking at this message, I was thinking that we possibly had a two-stage bootloader here, and really it doesn't matter if it's one or two stage, it's not going to affect us, but just a reminder that, of course, we are doing reverse engineering and there isn't any official documentation on this. So sometimes we just have to make our best guesses at what we're seeing. But what I think we're actually seeing here is this RA-Link versioning that we see below here, RA-Link U-boot version 4.3.0.0. Well, RA-Link, they're a manufacturer of CPUs and chips. They actually got bought by MediaTek, and then MediaTek just, absorbed them, and they absorbed their software and hardware. Again, just a reminder, the MediaTek is the SoC that has the CPU that we are working with on our router. So I believe what they've done here is, they're just using this U-boot version 1.13, the open source one. They forked that, copied it over, modified it to meet their needs, and then they've added this versioning message in so they can keep track of it, their internal versioning of it. If we look down past that message, we get a little bit of information about the board here, and we see, of course, again, that is that SPI flash. And if we scroll down a little bit further here, we see that, it's choosing option 3 here to system boot via the flash, and then we get the address, and this is a hex address of hex 10,000. So off of that flash ROM, we're going to boot off of that address. Now, later on in this lesson, we're going to look here. You see here, like, we just have no line. And what it's actually doing is waiting for a quick interrupt there. But since it doesn't see that interrupt, it just boots to the default, which is this 3. So we will look at how we can interrupt that and potentially choose a different option here. Again, we get that message that we're booting the image from that address. We're uncompressing the kernel at that point. And then we just actually transfer control over to Linux, and we give Linux its memory. And we get this message starting kernel. So at that point, we're actually just starting the Linux kernel, and we've handed over control to the Linux. And then the rest of the logs that we see moving forward are actually going to be from that Linux kernel. So if we scroll down a little bit here, there's a few things that we should take note of. Of course, if we didn't already know, we see the Linux version there, and we can also see the date. And we also see how it was built with this build root. So this is a common open source tool for building Linux kernels. So we should keep that in mind. It is with this build root. If we didn't know already, the CPU architecture, they see there, it is that MIPS, and we see even more about that MIPS detailing. Scrolling down a little bit here, I just want to show the very first thing that I see here that sticks out to me is we have this root FS type is squash FS. So we have our root file system. It is squash FS, which is a common read-only file system that's used in embedded Linux. So good to keep note. That's the first thing here. I'm going to enter into my notes. Scrolling down a little bit here, If I scroll just a little bit further to get down, see again about that squash FS, is if I just scroll here, the next section that I'm seeing that sticks out to me that I'm definitely going to keep in my notes and take a screenshot of is all of this information here. And we see here it is creating these 5 partitions, and we see the actual partitions of them. So of course, the first one is that boot, so where that U-boot is stored. And then of course we see this kernel here, and unsurprisingly, it is at that hex location that we saw before. So from this 10,000 in hex all the way up to this 100,000 X. Then we see here the location of the root file system. So definitely something nice to see because we're going to want to get this later so we can investigate it. And then we see 2 other partitions here, one for config, which of course we would probably want to get our hands on, and then this radio one. I'm going to keep scrolling down because there is some other really good information to see here. The next one that I see is this starting PID 29, and we get this /etc/init.d/RCS, which this to me looks like an initialization script that's going to be setting up other things on the kernel. So definitely something to keep note at. We're going to want to get our hands on this and take a look at what's going on in there. And then also good to keep track of what's running at startup, because if we ever wanted to modify this ROM and then either have a backdoor or something like that happen, well, this is something we can modify then to call, for example, our backdoor. Another thing that sticks out to me here is I see this /reduced_data model.xml. So when I see XML files, to me, this looks like also some sort of configuration file. So that might be something that we want to get our hands on and take a look at. We're then going to see a lot of information here about the router setting itself up. So we'll see things like DNS and DHCP and setting up all of the ifconfig. And we're just going to skip over those. Again, if you want to take a look in more detail, I encourage you to, but we're going to skip over most of those messages. And I'll just show kind of the next thing that I see that's really important here. Again, we're just seeing about setting up all of the wireless and the routing and the IP tables and everything like that. See some config files here that may be of interest. And actually, the one that I'm looking for that I saw that I was interested in me is if I scroll all the way down to where we left off here. Yeah, so we get into where we left off with the drop bear. So of course, this may be of interest to us here. We see this prepared drop bear. And of course, we know that the drop bear is the SSH that's running on here. But what sticks out to me is we are writing out this RSA key and we're writing it out to this location. And that's signifying to me that, var/temp, or most likely just this /var folder, is writable. So if we want to have somewhere where we're going to copy over tools and write them onto this while it's running, well, this is a location that it's actually writable, so we can do that. So we got a lot of really good details out of this boot log that I'm definitely going to add to our notes, and it's going to help us when we are further enumerating this system and also when we are reverse engineering the firmware. So what I'm going to do here is I'm going to hit escape to actually drop out of this copy mode. And we are back at, just so you can see, we've gotten all these messages that are coming in just in standard operation. So the last thing that I want to show here is that sometimes you can actually interrupt the bootloader, and you can get into a little bit of a shell that allows you to have some options to either, load a different flash or maybe even dump the flash, which can be useful to us as hackers. And in order to do that, we're going to have to hit a set command, kind of similar to how you would interrupt your BIOS. And that command generally varies depending on the manufacturer. So on TP-Link devices, the command is just TPL. So just as basic as the characters TPL. But you have to be really quick to do it. And we're gonna have to do it right when it's, loading up that U-boot. There's like a millisecond almost delay where you can hit it in and then it just moves on to the next one. And if you're gonna be unplugging your router and then replugging it in, it's almost impossible to get your hands back to the keyboard in time. So what we can do is there's actually a reboot command that we can run. So if I just drop back into the shell, and what's gonna happen here is it's gonna happen really fast. So I just wanna let you know ahead of time. So I'm going to type reboot, hit enter, and it's going to reboot. And then I'm going to immediately start mashing TPL over and over again. And hopefully I'll get it on the first time. Sometimes it takes a couple tries, but that should drop us then into the bootloader menu. So I don't know if you can hear it, but I'm already smashing there, and I was able to get it the first time. So unfortunately, when they have gone and modified this version of U-boot, they have really stripped down this command line interface. And I don't know if that's for security reasons or just to reduce size, but see, even if you go help, for example, well, unknown command help, try help. So there's not much that we can do in here, but if we do pull up really quickly, and I'll just show you. We look up U-boot, command line interface. So I'm just gonna take a look at their GitHub here and scroll down to the README. So I'm just gonna do a quick Control F for commands. So there we go, we get a list of commands here. And what you can do sometimes from the regular U-boot is we can actually display and read the memory and write from the memory. So if we weren't able to get the firmware through other methods, but we did have this UART shell, well, if we weren't in this lockdown version of U-boot, then sometimes we can actually dump the memory from here, read the memory, and also write to it. The only command that we're going to have access to, and I've tried most of them, is this tftp boot. And what this allows us to do, and the reason that it's here, is for recovery. If we were to, brick our device and we can still get into the bootloader, then we can set up a trivial file transfer protocol and we can put an image there for it to boot from, and it will boot from that over TFTP. So if we go back to our terminal here, we can run this tftp boot. You'll see it's going to boot and it's going to actually try and run. So it didn't actually find it, and what's just doing, so it's just booting up the regular method. So we're now back at that same spot we left off before, and I think this is a good spot to end this video. We'll pick up in the next one where we will use our Linux shell here to further enumerate this device. I'll see you over the next video. Welcome everyone. In this video, we're going to begin enumerating our router using that UART shell that we located a couple lessons back. Later on in this video, we will need our VM connected to the same network as the router. So I'm just going to run a double check right now and make sure I'm still on that same network. Perfect. And I'm seeing I've got an IP address on that network that the router hosts. If you do not have this, then go back and change your VM properties from that to the bridge mode and make sure you are bridging to the network adapter on your computer that you're connecting to the router. Lastly, I'm just going to run a very quick check here and make sure that that device file name hasn't changed. So remember the command for that is ls-l/dev serial/by-id. All right, and mine is still that TTY USB 1. I have restarted my VM since last time I did this, so always good to just check because this can change. So I think now we are ready to get that terminal session going. So I'm going to go use screen again, and we'll connect again to that same device here, and the baud rate is that 115200. I already have my router started up there, so we didn't see any of those startup logs, but I do have my shell connection. So you'll probably remember from the first time we got this shell, I tried to run that who am I command, which we can try and run again. And of course we see here, we get this who am I not found. And this is to be expected on embedded Linux systems and something that we're going to frequently have to deal with. And that's not specifically that we won't have who am I, but it's actually that we're not going to have a lot of the tools and binaries that we're used to having in normal Linux systems. And the reason for this is that space and memory are really at a premium on these embedded systems. They try and reduce them as much as possible to save on costs and for many other reasons. So one of the things that I like to do first when I get a shell on these systems is actually just to go and take a look at what we do have access to. So similar to standard Linux, the first place we should take a look is in the bin folder. So I'm just going to go over there right now. And if we just list this out here, I'm going to go into copy mode here so we're not just keeping scrolling. All right, so I see a bunch of different commands here, and we see we're really limited. There's not that many. Some that stick out to me here is we do have PS, and we also have netstat, so those are good to see to use for enumeration. And then the last one here that I see that sticks out to me that you may not be used to if you aren't using embedded Linux is this busybox. So if we just get out of this copy mode here and we just run busybox so we can see its help message. Very first thing we see here is we've got this BusyBox is a multi-call binary that combines many common Unix utilities into a single executable. And we have this list here of those functions that we can use. So BusyBox is used in embedded Linux because what it does by making this multi-call binary is it really reduces the size of these functions. And because of that, you'll see this very, very commonly. You'll almost always see BusyBox on embedded Linux. So if you look down here, we actually see a bunch more different functions that we can call. And one of the ones that sticks out to me is we do have access to this trivial file transfer protocol. So we can use this both to bring files or things that we find on the router that are interesting over to our Linux VM so we can analyze them further with all the tools that we have. Or we can also bring tools over from our Linux VM to the router using this. And that's really good to see. The other thing that I'm seeing here, just from my familiarization of using BusyBox, is that the standard BusyBox actually has a lot more functions than this. And one thing that's missing, for example, here is we don't have netcat. So what we can also do, and we're going to be doing, is we're going to bring over that full BusyBox onto this router so we can make use of all of those functions, and it's going to make our enumeration much easier. In order to make use of this TFTP, of course, we're going to need to host a TFTP server ourselves. Now, luckily, Kali already has one built in that we can make use of. So I'm just going to open up a new terminal window here. So Kali's got built into it ATFTPD. It's a mouthful to say, so I'm probably going to mess it up at least once or twice. And just do a quick double check if you have it against that ATFTPD here. And if you're not seeing that you have it for whatever reason, you can get it through the apt repository. So sudo apt install. So I've already got it and it doesn't need to be upgraded. But if you need to get it, you can get it through that method. The next thing we should do is just take a very quick look at the config file for this. So it is in this /etc default. So we don't need to change anything in here, but the one thing I just wanted to call attention to is we've got this /srv/tftp folder. And this is where we are going to be copying to or copying from files. So this is where we're going to need to either stage our files to copy them over, or where we're going to have our files from the client be copied to. So just something to keep in mind. I'm going to escape out of here. Okay, so in order for us to actually have this server be running, though, we're going to need to start it. So to do that, I'm going to go sudo, and it's atftpd, and it's --daemon. And it should be started now. So what we're going to do is I'm going to hop back over to our UART shell here on the router. Okay, so the first thing we're going to do is we're just going to bring a file from the router over to our Kali Linux VM. And in order to do that, we should find something interesting that we may want to analyze later. So what I'm going to do is I'm in copy mode here. So I'm just going to get out of copy mode. And I think we should take a look at that SBIN folder that we haven't looked at yet. I'm just going to head over there and we'll list out the files. So one that sticks out to me immediately is this init binary that we may want to take a deeper look at and try and reverse engineer. So let's bring that over to our VM. Before we just get started banging out commands with TFTP though, one thing that I like to do in these UART shells is instead of trying to write them in the terminal, and you'll notice we get interrupted sometimes and then it splits the lines and it makes it a little messy, is I'll just write out the command in a text editor and then I will copy and paste it over. So in my text editor here, I've just got the help messaging from that TFTP to aid us in creating our command. And we see it's pretty basic. We just got these 4 options: -L for local file, -R to specify a remote file, and then either -G for get file or -P for put file. And we've got an example here of how to do a get. So we're actually going to be doing a put. So what I'm going to do is we'll just run TFTP. And it's already mapped on the router, so we don't need to use BusyBox. You could put BusyBox in front of it and it would run fine, but they have mapped it so that we don't need to put BusyBox every time. And then we're going to be doing a local file, -L, and then we're going to do this SBIN /init. And then we're doing a put of that. And we need to put the IP address then of our Kali Linux VM. So it's .0.100 is the one that I had. So this should be good to go. I'm going to copy and paste this over into the terminal. Get on my copy mode here. And we are in that S-bin. So I'm just going to go up to the root here. And then if we run this here, I'm going to paste it with Control-Shift-V. Now, if we run this, so we're getting this TFTP server error access violation number 2. So generally when you'll see this, and I just want to show how to fix this in case this ever comes up with anyone, is the first thing you should do is just double check the folder permissions in your server. So if we go back over to the terminal here, our other terminal, and if I just do an ls-l, so see in this TFTP, you should have it so that it is 777's permissions for the folder. So make sure you have read, write for everyone here. And then the owner of it should be nobody. What you can do is we can go chmod and then 777. We go -r as well on that TFTP. I'm gonna need to be sudo to do this. You probably will as well. Okay, and then if we do this again, actually, and I'm gonna go and change the ownership as well. And we're gonna change it to nobody. So mine's already set, but we should also set that to nobody, because that's how the TFTP user generally runs on the client. So I set mine as well, and then just double check here, ls-l, it's still the same. So make sure yours are set. Now for us, this isn't going to fix that issue, but I just wanted to show it in case anyone doesn't have their setup like this. And then if we go back over into our notepad, actually, what I also recommend doing is usually just try and copy like from the folder that you're in, and don't use the full path. A lot easier, and I have a lot more success with TFTP running it like this. So we'll just copy this back over again here. Go back over to here. And if I just check where I am again, oops. Okay, so if we go into that S-bin. All right, now if we copy and paste this in. Perfect, it worked. So if we go back over to our other terminal there, and if we just do a cd into that TFTP, check out what we got that init, and we can run the file command on it to make sure properly copied over and we are getting what we expected. All right, and let me just bring this up a little bit here. Okay, so we see here, of course, it is that executable 32-bit least significant bit executable. Keep that in mind. That's good information for us that we didn't already have. So what that means is that this is little endian MIPS, and we'll talk about that a little bit more, what that means. And then of course we're seeing that it's that MIPS 32-bit, and this is exactly what we wanted to see for this. So this video is getting a little long. I'm going to pause it here. Keep this open if you're going to go to the next video, because what we're going to do in the next one is we'll take a look at how to bring files or tools from our VM over to the router. So that wraps up this video. I'll see you over the next one.
Welcome everyone. In this video, we are going to take a look at how we can use TFTP to bring tools from our VM over to the router that we can use. And we're going to start by bringing over the full version of BusyBox so we can get access to even more binaries and functions. In order to do that, we're going to have to download the full version of BusyBox to our VM. So that's just why I'm here at the VM settings with my VM powered off, because we're going to have to switch it back to NAT so that we can get access to the internet. And then we'll have to shut it down and switch it back to bridge mode. So I'm just going to do that right now. Okay, so we'll start with a quick Google search here to see if we can locate the BusyBox download binary. So I'm just going to search for BusyBox download. Perfect, and it is through this busybox.net. And if we scroll down here, we can just get the binaries. Of course, you could always download the source and compile it yourself, but they already have the binaries here. And I remembered that the version that we were working off was this 1.19. So we could try and get a more up-to-date one, but I think just for ease of use and making sure that's going to work, we'll just grab that same version, but this will be the full one with all of those functions.
Okay, so we're granted here with this list of different binaries, and we're going to need to choose the one that is the correct architecture for our CPU, and that is this BusyBox MIPS EL, or sometimes referred to as MIPSEL. And this EL, that stands for Little Indian. And you'll remember that when we took a look at that binary that we copied over in the last lesson, that it said it was that least significant bit executable first. Well, that stands for Little Endian. So usually you don't necessarily have to worry about the endianness anymore because it's actually just set for different architectures. However, MIPS is unique in that it can actually be configured to be either little endian or big endian. So we need to know the endianness, and ours is this one right here. So the easiest way to download these is actually, I'm just going to go right here and I'm going to go copy link. And then I'm going to switch over to the terminal here, and I'm going to switch over to that TFTP folder that we had set up before. And I'm just going to run a wget command so that we can download that. I'm going to hit Control-Shift-V to paste in that address. And this may take a second to download. Perfect. So then if we just run an ls-l in here, we've got that BusyBox MIPSEL and the init file that we copied over. Okay, so now that we have it here, what I'm going to do is I'm just going to shut off my VM, switch over to bridge mode, and then power it back on. So if you have to do the same thing, go ahead and do that now, and I'll meet you back over here with your VM set to bridge mode. Okay, I've restarted my VM here, and I've set it back to that bridge mode. So just a quick sanity check. Good to double check and make sure, seeing that I'm on that correct network that I want to be. So I'm just going to connect back to that terminal session using screen. Perfect, and we've got a shell here. So the other thing I'm going to do now is I'm just going to open up another window here, and we will launch up our TFTP server. So the command for that is this sudo atftpd --daemon. Perfect, and it's started up here. So if we go back to that other window, then we can now copy over from our VM to the router. The first thing we'll have to do though now is we'll have to figure out a place where we can stash our tools and bring them over. So we did actually identify, if we just take a look at the root file system here, that we had this /var, and we thought maybe this is writable, or maybe just /var/temp is writable, because we saw that there was scripts that were writing to that on startup. And this is the case, so we will be able to move it there, but I just wanted to show what will happen if we try and copy it to other locations and how we could figure this out if we didn't see that script. So let's just go over, for example, to the binary folder. So we'll go to the bin folder here. If we just list this out, we do see that we do have this chmod here. So the first thing I want to show is, let's just pick, for example, BusyBox. Like, let's say we didn't have the correct permissions on this. We wanted to change something about it. So what I'm going to do is I'm just going to try and chmod 777 BusyBox. And you see we can't even do that because this is a read-only file system. And same if we, for example, wanted to make dir and go test, we're going to get that same issue, that this is a read-only file system. Because we did see that most of this file system is that squash fs, which is a read-only file system. So what we can do is if we go back out here to our root, and if we run the mount command, and I'm just going to pause this so it doesn't keep scrolling. So what sticks out to me here is we're seeing that most of this is this type squash fs, which is read-only. However, we do have, and if you're not familiar with the file systems, there is this one RAM FS down here, and it's read-write. And generally when you see this on embedded Linux systems, this is going to be where we have files that are writable. This RAM FS file type is a writable file type. I know these other ones say they are read-writable, but they're not actually going to be. If you try and go to either proc or sys, you're going to get errors. But in this RAM FS, so in all of this /var folder, we will be writable. So what I'm going to do is I'm going to get out of this copy mode here, and we'll go to that /var folder. And it looks like there's already a temp here, so I think we'll just use the temp one. We don't necessarily have to, but I'm just going to go there. And let's list out what's in here. So we do already have some files in here, and this is just personally my own convention of what I like to do on these IoT devices, just to make sure when we're doing our enumeration, any reverse engineering or anything like that, we don't get confused about things that we're bringing over. I'll create a folder. I'll call it tools or something like that, but I always put an underscore in front of it just so that I know when I'm coming back that that's something that I created. So what I'm going to do is I'm just going to make that directory called underscore tools. And we'll cd into there. So just like last time, I'll just write that command out in the notepad to make it a little bit easier for us. So again, it's going to be tftp, and we're actually going to want a remote file, and it was that busy box-mipcell is what it was called. And then we're going to do a -g for get, and of course we need to put our IP address 192.168.0, and mine was .100. Make sure to put whatever you have here. And this looks good, so I'm going to copy this here, copy it over here, get our shell back, paste it with Control-Shift-V. And this might take just a minute or two to copy. Perfect. So then if we go ls, we should see that we have that busy box mipcell. And the last thing that we're going to need to do is just remember to change our permissions so that we can run it. So what I'm going to do is I'm just going to go mod 777 on that busy box mipcell. And we do have, I should have mentioned this before, but we do have tab complete in this, which is kind of nice. So now if we do ls-l, ls-l here, we can see that we are able to execute this. So now if we run this busy box, look at all, I'm just going to pause this so it's not going to keep scrolling on us, but look at all these extra functions that we have. So now we're getting closer to what we would have on a regular Linux distribution. And this is going to make our enumeration of this machine or this device much easier. So just some core ones that I want to call out. For example, here is, we have find, we even have, I believe there's grep on here. If I just look for the G's here, yeah, we got grep. So lots of really useful tools that's going to make our lives a lot easier if we want to do enumeration on here. And one that sticks out to me is here we've got netcat, so we can use this. And what I'm going to show right now before we pause this video is if you're not a fan of using this hardware shell and you'd rather do it over a different network shell, well, we can just use this netcat here to get ourselves a reverse shell. So that's what I'm going to do right now. Let's switch over to our other terminal here. And I'm just going to set up a quick listener. So netcat nvlp, do it on 444, standard port. And then if we go back to our other terminal here, and I'm going to do the same thing. I think it makes sense just to write this one out since it's a little bit longer. So we're going to need to call netcat through this busy box. So any of the new functions here, they're not going to be mapped. So we're going to have to actually call them like this through this busy box. And we are going to want to call netcat. And we're going to put the IP address 192.168.0.100. That was port 444. We're going to go -e and we're going to go /bin sh. Copy this over here. It's frozen, so generally a good sign. If we just switch back over here, perfect. So let's just see. Perfect. So we are in our netcat shell here. We can look at the present working directory, and we can actually even run that who am I now if we want to, because we have it through here. And we are this admin, which is the root on this router. Perfect. So the purpose of this video was just to demonstrate how we can use that TFTP to bring over tools and how that's going to make it a lot easier for us in our enumeration. And we're not as restricted in kind of the live off the land that we were stuck in before. It's really, really common to see TFTP on IoT devices, especially ones running embedded Linux, because that functionality is baked into generally a lot of how they will do firmware updates or other updates, is to use that TFTP protocol. You even saw how even our bootloader had that functionality baked into it. So it's really not that uncommon to find this on your various IoT devices, and we can make use of it as we did here to either bring stuff off or bring over tools to use. That wraps up this lesson. I'll see you over in the next one where we use some of our newfound functionality now to further enumerate this device. Welcome everyone. In this video, we're going to be using our shell to hunt down for interesting files and passwords. I'm going to be using the UART shell through screen in this video, but you could also use the netcat one that we previously established in the last lesson if you prefer. You may recall that I did previously mention, you could go and try and do a full Linux style enumeration on this router, similar to what you would do post initial exploitation in a regular network pen test where you have access to a Linux computer. And there's nothing that's not valid about doing that. However, there are some differences on IoT devices that may make us want to consider how we approach that and what we use our shell connection for. So to talk about that, I've actually just re-pulled up with this mount command the different file systems that we have on this router. So if you want to run this again, you can run mount and it will show these as well. And you may recall that most of our file system is this type squashfs, which is a read-only file system. And this entire file system, it actually exists as part of the firmware for the router. So we can actually get to this through that firmware we downloaded, and then we can analyze this entirely on our local machine. And since we know it's read-only, well, there shouldn't be any differences on the live machine from what we have in our firmware. And it's going to be a lot easier to do any analysis on our VM or our local machine because, of course, we've got all the tools that we would ever want. And if we need more, we can just very easily install them. And then also with IoT devices, they're very limited in their processing power and RAM. So it can take a long time, or we can even freeze them or crash them if we're trying to run, for example, long greps or finds or things like that. Now we do have these other 3 different file systems here that we saw, and the one that we talked about and found where we could write to is this RAM-fs. Well, if you're not familiar with Linux file systems, this RAM-fs is exactly as it sounds. It lives entirely in the RAM. And what that means is that this is a temporary file system. So anything that gets written here while the router is running, well, it's all going to get lost when we reboot. So unfortunately, that actually includes all of our tools and anything that we bring over and write to this folder. All the contents and setup and everything in this folder, it's all created dynamically when the Linux kernel starts up during that initialization. All those initialization functions and scripts, they set up everything in the RAM-fs on this /var folder, and they do that by reading from various config files. So what this means for us is that enumerating and taking a look through this /var folder on the live machine can make our lives a lot easier because then we don't have to try and reverse engineer from this squashfs read-only file system that we have locally and figure out what those scripts do and how they specifically set up this /var folder. We can just take a look at a live one that we have on our router. And that's what we're going to be doing in this lesson. Just quickly, in case you were curious about what these proc and sys file types and folders are, so you have type sysfs and type proc. Well, these are virtual file systems that are used by the operating system. Proc is for process and sys is for system. And they're not standard file systems like you would think of with files and folders. These are virtual file systems that are used specifically by the system. So that's why we can't actually write or do anything with them. And we're not going to be specifically concerned about them in this lesson. What we're going to take a look at is enumerating this /var folder. So what I'm going to do is just head over to that var folder now, and we can start taking a look. So cd/var. And what I'm going to do is just open up the notepad again, and we'll start crafting our first command. And that's going to be to use grep. So I'm going to actually run that busybox through the full path because I don't want to just be in that tools directory to run this. So that's var /temp. We put in _tools /busybox -mipsel. And then we're going to run grep, and we're going to look for, we're going to do it recursively to search through everything. And we'll start by looking just for the word pass. I'll put a dot here. So any file, so what this is saying is we'll search recursively through every folder and we'll look at every file. And if it has the word pass, then we'll take a look for a hit and see that line. You could use pass or password or anything of those, pass WD, any of those abbreviations. I'm just going to use pass because the nice thing with IoT devices is there's not as many files and things like that as you would on a standard computer. So we don't have to be as pinpoint in our search, and this will just help us bring back anything related to passwords. Hopefully we can get. So I'm going to get out of copy mode here, and we'll paste this in here and let it run through. So go back into copy mode so it doesn't scroll on us. And if I just scroll up to the top here, so this is kind of why it's nice that we have this underscore tools. So anywhere we see this, I'm just going to skip over it because we know we've added it. Of course, we're getting some hits through that BusyBox binary that we brought in. And of course, we don't care about any of that because we brought it over. But if we scroll down here to the bottom, we're seeing it looks like 3 config files with this .conf file type, and they have the word password in it. So maybe worth taking a look at these. And then also of definite interest to me is it looks like we have the drop bear password. So this is the SSH password. And this to me looks like some sort of hash. So what I'm going to do is I'm definitely going to save this. I'm going to want to add, all of this to our notes, especially even about these config files and the commands we run. But more specifically, what I'm going to do with this is I'm actually just going to copy this. And if we go over to the terminal I have here, what I'm going to do is I'm going to make a directory for our router here. So I'm going to call it tp_link wr841n. And we'll cd into there. And I'm actually going to make a directory for hashes. Okay, and what I'm going to do is I'm actually just going to create a little document here. We'll call it dropbear.hash. And I'm going to paste it in here. All right. Save this. And then we should have that. Yep, perfect. So we've got this one hash. We'll come back to this later. And let's go back again here and open up the notepad. So another good thing to look for here is I'm just going to run one for admin. We know the user is that admin. We found that through whoami. And then also a lot of times like the default admin user on routers or different IoT devices is going to be admin or administrator or something like that. So another really good one to search for. So let's just rerun this again. Paste it in with Control-Shift-V. And we got a couple hits here. Okay, so first thing I'm seeing here, and this is actually interesting to see, is we've got this passwd file with this. To me looks like what would be the contents of the shadow file, and it looks like, I guess, it's using the old style where it's in the passwd, and for whatever reason it's been copied, or I'm not entirely sure why, but it is in the var folder. But this is a great finding for us because it looks to me like this is going to be the password for the admin account. And if you're not familiar with how the shadow files work, so this $1, this means this is going to be Unix MD5 hash. And if we copy, so all of this right here, all the way to this slash is going to be the hash. So let's take this over again to those hash folders. And we're going to go and we'll call this admin.hash. Paste it in here. Save it. We should have those 2 hashes. Okay, perfect. So let's hop back over. We'll come back to those in a second. So you could, add root here. That would be a good thing to look for. Another one that I like to look for on IoT devices in particular is to see if there's any hard-coded API keys. So I'll put something like, API or key. Let's start with API though here and take a look and see if we get anything back. Okay, so it looks like on this, there's nothing, but this is always a really good thing to check to see if you have any hard-coded API keys or anything like that, or API endpoints. Another interesting thing to look for is if there's any URL endpoints or anything like that. So we can also take a look and see, for example, I don't know, maybe .com. Look for anything with .com in it. Okay, so we'll just ignore again any of this BusyBox tool stuff here. Okay. Looks like we've got these some XML files here, so good to know that it looks like we're using .conf and .xml for those config files. And we've got, this one's not too much interest, but sometimes you can find interesting URLs or subdomains in here. Scrolling down, again, just seeing some more XML files for config. So nothing huge of interest here, but they can find, very interesting URLs and subdomains and API endpoints and things like that by searching for this as well. And, you can do .org, .net, all those different ones and see what you can get back. Okay, so the next one we'll do is instead of using grep, we'll use find, and we'll see if we can take a look for some files. We saw that they're using that .conf and .xml for all of the files. So I'm just going to copy this part here so we don't have to retype it out here. Copy this, paste it, and then we're going to use find instead of grep because we have access to that through this BusyBox. And we're going to look for -name, and we'll look for any files, and this is just going to help us find anything with that file extension. So we'll do .xml, and we should be able to then look for anything in that var folder with this XML. So let's copy this. All right. Okay, looks like we got some hits in here. So we're seeing a bunch of different XML files. So good, I'm going to copy all of this into my notes for us to further enumerate and take a look through these XML files. Another one we can do that's good to take a look at is we can also look for, we saw that we had those .conf files as well. Perfect. So we have all of those .conf files. Again, another thing to take a look for. We should add all these to our notes. So interesting way just to find any like human readable files where there might be interesting information. Of course, we could also do a search for .txt and see if there's anything in there as well. So that wraps up this video. I will see you over in the next one where we take a look and see if we can crack either of those hashes. Welcome everyone. In this video, we are going to take a look at some of those interesting files we found in the last lesson using grep and find, and then we'll take a shot at cracking the two hashes that we also located. So of course, if we find something interesting with grep, it only shows us one line in that file, and it's worth taking a look at the rest of the file. So let's start by looking at that passwd file that we saw. And it was just sitting there in the /var, so we can cat that out. So if you're familiar with modern Linux, then the passwd file usually doesn't have the hashes in it for the passwords, but this one looks like it does, and for whatever reason, it's being moved or copied or remade into the var folder, which is interesting to see. But of note to us, of course, we saw this admin hash, which we copied over, and we can see the other users in here as well. So we have the dropbear user for the SSH, and then we have this nobody that we already know is for the TFTP. So unfortunately, no other hashes or anything, just that one that we did find, and we're going to try and crack later on in this lesson. So we also saw there was that dropbear password, and it was inside a folder in temp here. If we just list it out, there was a dropbear folder in there. If we list out the contents of that, we see, of course, we've got this dropbear password file. So let's take a look at that and see if there's anything more in there. Looks like we just got the one password and hash, so nothing further to find there. And then the other two files that we see in here, we've got an RSA host key and this DSS host key that are used for the SSH. If you're not familiar with these keys for SSH, these aren't the ones for actually accessing. These are the ones that are the host keys for identifying this router. So they're not going to be of any use for us for further access. But of course, this dropbear password is something that we're going to try and crack later in this lesson. So I'm not going to show live taking a look at any of those other configuration files, both the .xml and .conf ones. I have taken a look through those, and they don't really contain anything of interest, and that's most likely because we've still got a pretty much factory default set router. We haven't set anything on it. The config files are for things like the UPnP setup and whatnot, which we haven't touched, so they are mostly blank. If you want to exercise in using this shell and reading those out, though, of course, we do have cat on here, so you can take a look at those, and I would encourage you to look through them on your own. At this point, I'm going to switch over to the other terminal here, and we will take a look at cracking those two hashes. Okay, just to double check on the hashes we have. So the first one that I'm going to take a shot at is this admin hash. So if we just take a look at this, just really quickly looking at this hash, so I can identify that it is the MD5 Unix style hash, because for these shadow file or passwd file hashes, this $sign and then the 1, this denotes what type of hash it is. And $1, that's just the Unix MD5 hash. This hash is very crackable with Hashcat, and I think anyone that took the PEH course should be more than capable of doing that. So I'm not really going to go over the full details of it. And in fact, I'm going to encourage you to pause the video right now and just give it a shot on your own. So go ahead and pause it right here. And when we come back, I will show how to crack it. Okay, so hopefully you were able to crack it. If not, I'm just going to quickly show how we can do that. So first thing I'm going to do is just check in the help and see what module we need to use for the MD5 Unix. So I'm just going to run hashcat, and I'm going to go --help, and we'll pipe it into grep, looking for MD5. And right here, we've got this MD5 Unix. This is the one. Even we see this got this $1 for the formatting, which we have in ours here. So that's going to be exactly what we need. So we'll just run with that one. And then we're going to do -a 0-m is the 500 we just found. And it was the admin.hash. And I'm going to use I'm just going to use rocku for this one. So that is in user/share word lists /rocku.txt, and I'm just going to let this run through. And look at that, cracked it immediately, which even on my VM usually takes a little bit of time to set up, but we got it immediately, and that's because the admin password is 1234. So not a very strong password. I wonder why they even have one, but yeah, 1234 for that admin password. All right, so let's take a look at the drop bear one now, and I'm just going to pop open the hash here. So that was this one. And looking at this one, again, this looks like just a straight up MD5 hash to me. So let's take a look at how we can crack that one. I will mention, so if you want to go and crack this one on your own, go ahead, but if you may not be able to crack it, and I'll just show you why here. So go ahead and try it if you want on your own, but don't expect for sure that you will be able to crack it. So let's go back and run that hashcat command. We're just going to switch here to this drop bear. And I should remember this one from doing it so many times, but the straight up MD5 one is just actually 0 in hashcat. And we'll let this one run through here as well. And mine cracked almost immediately, because you'll see here the password is 1234 QWER. And if you don't remember, this is what I set actually as the admin password to the web portal for the router. And that's what I was saying, you might not be able to crack it, because this is going to be dependent on whatever you set that password to. So whether you set it the same as me or you put your own one in. So it's kind of interesting to see that it looks like that's why this drop bear password is being created dynamically there, because it's being picked up from the config file and whatever we set for that admin password. So if we were conducting a pen test or a security audit or anything like that, then these would definitely be interesting findings for us, and we're definitely going to put them in our notes. So the last thing I want to show quickly here, because I'm just sure a lot of people will be wondering why we're not using that SSH password we found to log in with the SSH. And there's a couple of reasons for that. The first one is, just to be honest, is that I was not able to ever get it working. And I'll show you the issue that I ran into. So we can SSH. So if we just go SSH, we'll just go drop bear at, and the IP address 192.168.0.1. And if I just bring this up so everyone can read it. Okay, so the first thing we see here in this error is just this unable to negotiate with, and then this is the IP of our router. We get this no matching key exchange method found, and we see the key exchange methods they are offering. And I want to show this because this is something you're going to see with IoT devices frequently, that they're running, we have a very old Linux kernel, and we're running lots of outdated software. And of course, we don't have the most up-to-date key exchange methods and cryptography and all that stuff. So these are outdated. They're either deprecated or broken key exchange methods that aren't recommended for use anymore. So if we want to use these, we're going to have to force our SSH to do that. And I'll just bring over the command here because it's a little long to do that, just so everyone can see and how we can actually get that working. So I'll just paste it in here and we'll hit enter and then bring it up so you can see. Okay, so it's going to ask us for a password now, which is at least good enough. And we know for me it was 1234 QWER. We get these errors, so I'll just bring it up again so everyone can see. So this is the command here, and we're just adding these algorithms. So we're adding both the key exchange, and then if you just fix those, then it's also going to complain also about the host key algorithms that they're using. So we need to add those as well. So I've just added both of those in here. And then you see we get this PTY allocation request failed on channel 0. So to fix that, and the way that I've seen that fixed is we can add this -t into the command. And again, I'll put the password in. So just so everyone can see, I move it up. And then we get the shell request failed on channel 0. And then this is as far as I got. I did spend quite a bit of time trying to figure this out, but I was never able to. So if anyone wants to take this as a challenge and figure out how to get this SSH working, I think that would be super cool. If you do some digging, you'll find that the reason this SSH is open is because it's used for that TP-Link Tether app, and that's how it actually communicates. So I'm not entirely sure if they're using some special format or how that's working through SSH, but I wasn't able to log in with it and get a shell. And I also wasn't able to just, how you can send commands with SSH, then you get an exec request failed. So that's definitely something, if you want to spend more time on it, that you could and try and figure out what's going on there. Maybe even download the app and try and intercept the traffic between it. The reason I didn't go any further into it is because as far as hardware hacking and trying to find any vulnerabilities or anything like that, it's really not going to be, that useful to us because we do already have this hardware shell. And then of course we can use Netcat to get a shell. That's going to wrap it up for this video. I'll see you over in the next one where we continue using this shell to take a look at some of the processes and network connections that are running on our router. Welcome everyone. In this video, we're going to continue on with our enumeration, and we're going to be using two very common Linux enumeration commands that you're probably familiar with, and that is ps and netstat. And we'll take a look at how we can use the BusyBox that we ported over to run those commands. So you may actually recall when we were taking a look at the binaries that we initially had access to, if we just head over into that bin folder and list it out here, we actually already have ps and netstat here. However, if we just start with ps, for example, and we just try and run a help, so -h, we get invalid option. So maybe if we try --help, well, we see we don't actually get anything printed out. Now, we already know that on this router, it's running a pared down version of BusyBox that doesn't contain everything. And it looks like it's possible that they've even pared down these various binaries that are included as part of BusyBox because it looks like they've removed the help command or the help menu, at least from this. And because of that, I'm not entirely sure what else they have removed. So I'm going to use the full BusyBox version that we brought over, and I would suggest if you have that option, then it's always better to use that one because then you know it has all of the commands and everything that's available to us. So let's just head over there right now. So mine is in this var temp _tools. Let me just tab complete it here and just double check it's still there. Perfect. So what we can do now is we can run this BusyBox one that we brought over. And again, we're going to do ps, and let's just see if we can get the help working in there. Okay, so not many options here. We can just list to show the threads, which isn't going to be very much use to us. And then we also can select which columns we want to display. But if I just pause this for a second here, unfortunately, it's not giving us much details about, which columns that we'd like to display. Maybe we'd like to run something similar to like ps-augs that you usually run on Linux. So what I did find that you can do to, check what columns here is actually if we just list an invalid column, I actually found this by seeing if I could just run all. Let me just bring this up on the screen here. So we do get these options of these supported arguments. So in case we want to see any of these, if you try and list them all, you can only list about 5 of them. So pick what 5 you want if you do want to list them all. But I found just running with the defaults shows enough to get a good idea of what's actually going on. So I'm going to rerun this again here. And instead of any options, let's just run it as default. And I'll go into copy mode so we stop scrolling. So the very first thing that sticks out to me here is we see that the user that's running everything on here is this admin, which we already know is root. So we have root actually running all the processes that we can see listed here. And this is not surprising, just how we've seen kind of the rest of their internal security hygiene, but definitely not following that principle of least privilege here. So if you're doing an audit or a penetration test, then definitely something of note to list out as a finding. The other thing that I'll take a look at when I'm looking through the processes is anything that just looks like non-standard Linux that might be interesting to further investigate. And when I scroll through here, the one thing that I do see is this COS binary or cause. I'm not entirely sure at this point what this is, but this is of interest of me because it doesn't look like a standard Linux, or at least anything that I'm used to seeing. If we scroll through the rest of it and take a look down, some other things that are of interest to me is we can see, for example, how the drop bear is being run, so how that's being executed. And then we see a bunch of the other internal binaries and commands that are running for the networking. Of course, we see this HTTPD one that we already saw when we were taking a look at past vulnerabilities. So good to see that that's running and also of something of further interest. Okay, let's take a look for netstat here. So we'll go /autocomplete for busybox-mipsel, and we'll go netstat-h. Okay, so it looks like in here we have a few different options than the standard Linux one, where I would usually run something like netstat-ano. We are still going to want to run that A so we can see all sockets. And then the other 2 ones that are interesting to me is we have this -E for other more information. And then we definitely want to run this -P so we can show PID program name and get an idea of what's going on with those sockets. So let's run that. We're going to go here and we'll run -AEP. So taking a look through the sockets that are open here, nothing too much of surprise. We're seeing most of those commands and binaries that are being used for the router, and then things that we already knew were running. So of course the drop bear, we see that HTTPD, of course, some things for the UPnP. Nothing of surprise there. We do see again this COS or COS binary being called, and it's a raw socket on port 255, which is usually reserved for these raw sockets. So maybe something of interest further to see, why this is opened up and what is listening. Other than that, nothing too surprising here. We already knew that most of this stuff was running. So we didn't find too much new interesting information from these 2 commands, but I did just want to quickly show how you can run those through BusyBox, and that it is a good idea if you do get this shell to take a look at both the processes that are running and then whatever sockets are open. That wraps up this quick video. I'll see you over in the next one. Welcome everyone. In this video, we're going to take a look at some of the console log messages that have been streaming into our UART connection. And we'll also see how we can trigger additional log messages from performing some actions on the router, and how these are going to aid us in future reverse engineering. So we haven't chatted too much yet about all of the different messages that have been streaming into our UART connection. And up until now, they have mostly been a nuisance for us as they just interrupt our terminal session when we are trying to type. That being said, they do contain a lot of very useful information. So if I just pause this one here so we can take a look at some of them that are up on the screen, the one that we've been seeing stream in very frequently is this one from the util exec system. And all it's doing is just telling us the unset time zone command and how that's being run. So this one specifically does not contain a lot of interesting information, but from the format of it, we can see how the other log messages are being written. The first thing that I want to call out here, and we can see through a few of the different log messages, is when the message is being called with this square bracket, space, and then a function name, and then square bracket. Well, these are actually functions that are being called by the underlying binaries that are running the functionality of this router. Generally, in embedded Linux systems, you're going to have some sort of shared object library that's going to contain most, if not all, of the functions that are going to be called by the binaries. And generally, in these shared object libraries, even though they are compiled, you will still have the actual names of the functions be available if we reverse engineer them. So what that means is that we can actually take a look at the logging messages and the specific messages that are being printed out, and we can then relate these back to functions that we can reverse engineer. Of course, when we're just seeing them stream in like this, they don't give us a huge amount of information because we could probably already find these messages. However, one thing that we can do is open up the web portal, and then we can test some of the functionality in the web portal and see if we're able to find out through the logging what underlying functions are being called. Of course, this is of particular interest to us for finding those command injections or buffer overflows, because we can then relate what we're doing in the web portal easily to the underlying functions that are actually being called by the router. And then we can try and go and take a look at these functions when we are reverse engineering. So the first thing that I'll try here is we'll just try a quick login. So if we go, for me, it's 1, 2, 3, 4 QWER, and I'm just going to hit login here. And interestingly enough, the first thing that we see is we get a message, AES_get key failed. This AES get key isn't okay. No AES key in IV now. So definitely something of interest about why this is failing and what's happening there in the failure, if it's, defaulting to not using encryption or some sort of preset key. So definitely something of interest there. The other thing that I'm interested in now is we have all of these different commands that we can run through the web portal, and they all offer potential injection points for possibly buffer overflow or command injection. So the first thing I'm going to test is just this quick setup here. And I'm going to choose access point because we don't actually have a WAN port plugged in. So it'll allow us to set it up as an access point still, though. We'll need the WAN port plugged in to do it as a wireless router. So I'll just hit next here. And I've already set this up once, so I'm just going to go with that same settings here. So IoT hacking is what I'm using for the network name. You can set whatever you want here if you want to put it something differently. And then I'm going to use this really bad password of 12345 QWERT. I'll hit next here, and then we can just run with these defaults here. I'll hit next, and then again, it just plays back those settings for us here, and then I'm just going to click here to apply those settings. And when I click apply or finish here, it's going to start streaming through a bunch of log messages as it applies all of these settings that we did. So I'm just going to hit the button here, and we'll see all of those messages start coming through. And if I just pause this now here so we can take a look at some of the interesting things that are coming in. And as I scroll up here, let's scroll down. So we can see a bunch of interesting log messages coming through here. First one from this function, RSL_send app_w LAN config. And we get the message about this tell TMPD server that the WLAN guest config has been changed. And then we see a bunch of information from this util_exec system about how we are actually setting all of these details. So this is the first one that I see that's really sticks out of interest to me because this is something that we actually input. And we're seeing how that SSID of IoT hacking is being set. And we're using this OAL_WLAN_RA_set WLAN basic config to call this command iwpriv RA0 set SSID. If we scroll down again a little further, you actually see in this one how the pre-shared key is being set. Again, it's this OAL_WLAN_RA_set secret, and the command that it's running is this iwpriv. So these are of specific interest to us because now we know when we perform these inputs on the web portal that we can actually see the underlying commands that are being called. So this OAL underscore WLAN, RA set secret, and through the util exec system. This is going to be of interest to us when we do reverse engineering. So one other area of interest that I saw scrolling through the web portal is we have this system tools section, which offers a lot of interesting diagnostic tools and things that we can update that are potential injection points. So under the system tools, I saw this diagnostic here where it allows us to run a ping. So if we just really quickly run, a ping using it as we should be, I'm just going to try and run a ping here for what my VM is actually at. So that's a 192.168.0.100. And I'm just going to put this out of the pause mode so we can see the logs start streaming through. When I hit start here, it should start running a ping. Perfect. And we can see those pings actually come through. So I'll just pause it again here. So scrolling up here, the one thing of interest that sticks out to me is we're seeing how this ping is being run. And again, we're seeing it from this util exec system function, and we have this OAL underscore start ping command is, and then we're seeing it's, this IP ping, which this is actually one of the binaries that we saw through BusyBox. And then of course, we're seeing this IP address that we put in here. In case this wasn't already obvious or sticking out, when we're seeing this util exec system being called, this is actually making system calls. So this is running essentially shell commands to the system. And in this example, it's this actually showing us what it's running here, which is this IP ping command. And this can generally be dangerous to be doing because this is potentially an injection, especially when we're running this command with a user supplied input. So if we aren't doing proper validation of all of these different options here, then this is actually an area where we could do injection. So what we can go back and try manually here, of course, and I'm not going to go over like the full injections or anything, but we could try and just put, a semicolon here. And then if we, for example, I don't know, we have echo, so we could just try echo hello and run this. Well, it looks like they're actually doing some validation here. So good on them. But, the whole point of this is just to demonstrate about how we can now see if we want to, check and see how this validation is being done and if we can break it. Well, instead of just banging our heads on the keyboard, opening a burp and trying a bunch of different injection points, well, now we can actually go back and try and reverse engineer these functions, and we can try and locate them in the firmware using the labels that we already have for them. And this is going to make our lives a lot easier for us. So I'm going to wrap up this video here. There's of course a lot more different interesting areas to explore in the web portal, and I would encourage you to go ahead and do so and just see what log messages you get from the different actions in the browser. I'm not going to show all of them on this video, so I will wrap up this video here and see you over in the next one. Welcome everyone. In this video, I'm going to be demonstrating how we can use Python to connect to serial ports. And in doing so, we can actually have our Python script connect to that UART serial shell on our router. And then we can have the script automate some tasks. There's really endless possibilities to what we can do with this. And in this video, I'm just going to be demonstrating two scripts to give you an idea of what we can do. I'm going to be making the assumption that most people watching this video will at least have a base understanding of Python. And as such, we're not going to be writing out the full scripts. I'm just going to give an idea of what they do, and then we will run them. If you want to copy or download these scripts, I have hosted them in the course GitHub. So in the project folder here, I've actually just created a folder for the scripts. So let's head over there right now. And if we list them out, we've got two scripts that I'm going to be demonstrating. One that interrupts the boot process, and then another one here that just runs the PS command and then logs the output so that we can see what processes are running over time. Before we get started, both of these scripts are going to require the PySerial package. So this is a Python library that allows us to interact with these serial ports. It's already installed by default on Kali, but if you don't have it for whatever reason, you can get it through pip3. So we're going to go pip3 install, and then it's called PySerial. And you'll see I already have it, but just in case you didn't have it, that's where you can get it. Let's start by taking a look at the script that runs PS and then logs that out. I'm going to be using Vim. You're welcome to use whatever code editor or text editor you are most comfortable with. So we'll take a look at this ps_log.py. So I've created this script really just as an example of how to make the connection and then read and write through that serial connection with Python. Of course, you could use this script, for example, if you thought that there was processes that were changing from some cron jobs or other scripts that are running at different times or being triggered, and you wanted to be able to capture those. So what we're doing with the script is at first just initializing some of the settings that we need. So I've added this port here. This is how we're actually going to connect. It's the same as we would do with screen. So this may change for you depending on where that device is. For me, it's TTY USB 0 right now. Next thing we're going to do is we're going to open a serial connection on the selected port. And you'll see here we are actually setting those parameters for our serial connection. We've got the baud rate, the byte size, which is the data bits. We have set a timeout here of 1 second to close that connection if we time out. And then we have this stop bits equals serial.stopbits_1 to set us as just one stop bit. I needed this empty string here just to hold the contents of what we read. And then we're just using a while true loop here because we just want to continuously run the script over and over again to send that PS command. We got the sleep here for 10 seconds. Then we are just writing out to the serial port, and we're doing so in bytes. We need to communicate in bytes. We're just setting PS. And then here, I'll move this up. We're going to read out into that string everything, and you'll see here we're using this read until function, and we're going to read until we see PS. The reason we're doing that is because generally if you run a PS command, then the last thing that's going to be in your list of processes is that PS command that you just ran. So we're going to be using this read until, really useful function because you'll generally have an idea of what you're looking for when you send out a write. And then you can use this to, stop your reading once you get the details that you are suspecting to get. And that's what I'm reading until this PS. Then we're going to print out that serial string. And again, we need to decode it from those bytes into ASCII. And then finally, we're just going to open up a log file here and we'll write those into the log file. And then we just wait for 10 seconds until we run it again. So let's take a look at how we can run this script and what it looks like. I'm going to need to run it as sudo just because of the permissions on the dev folder. So I'm going to go sudo python 3, and then it is ps_log.py. So I'll just run that right now. And sometimes it does take a little while for it to initialize and open up that serial connection. So it might just hang for a second here, but it will start pumping out the results quickly. All right, so we'll see it. It's just going to continuously run here. So I'm actually just going to hit Control-C to stop it. And then now if we check the contents of our folder here, we can see we've got this ps_log.txt. So I'll just cut that out so we can see how that works. Perfect. And we just see here, I only grabbed one. We did get some of the other messaging, but we can see here we ran that PS command. And then we got back the results of that PS command. And here's where it ended again at PS. And then we were just waiting, and we would run this again continuously. And you can let it run for a while and see if you start seeing any interesting things coming through or changing. Again, the idea of this script was just to give an idea of how this works. Okay, the other script that I wanted to take a look at is this boot_interrupt.py. So let's take a look at that right now with Vim. So this is another example script that just demonstrates how we can interrupt the bootloader programmatically with the Python scripting. And what it does is it just reboots the router, and then it sends that TPL command about 10,000 times over and over again really quickly just to make sure we catch that interrupt and then enter the bootloader terminal menu. The reason for showing this script is because this is actually a really good use of what we can use the Python scripting for. Because you may recall from the U-boot bootloader that when we were looking at the standard U-boot, which is pretty common on a lot of IoT devices, We have a lot of options in that terminal, and one of them is that we can actually read out the memory contents from the ROM. And what we can have our script do is actually keep calling that memory dump or display memory command, and then we can have it write that out to a log file. Now, you could do this just with the terminal and try and output it, but the problem is it's going to take a very long time to do this over a serial connection. And sometimes you have to only specify blocks of the memory, so maybe 1024 bytes at a time, or else it's going to overload the processor and also that serial connection. So one way to frequently overcome that is with some sort of script where we will just manually grab the blocks and then append them to a file and kind of create our own binary file that represents the firmware. Let's just take a quick look here at what we're doing. So the setup for this is the exact same. I'm not going to show it here. The one thing that I did do is I just cleared the output buffers from any previously cached reads and writes. This is a good thing. I didn't do it in the other script, but this is something good to do, because what can happen with these scripts is you can have output being in the buffer, and especially here where we're writing this TPL out 10,000 times, we might get some stuck in our serial buffer. So first thing we do here is we just write out that reboot command to actually reboot the router, and then we just wait for 0.5 seconds to give it a little bit of time to actually execute that reboot command. And then what we do is we just start sending this TPL about 10,000 times. And this is just kind of trial and error for me to get the timing and the amount of these to send. And I'm just printing it out so that we can actually see what's going on and how many times we're sending that TPL. And then after we send that in this while loop, I'm just reading each line to see once we get to that prompt for the U-boot terminal. And then at this point, this is where we could then add in the additional code if we wanted to send the MD command and then read back the contents of that MD command and print it out into a file. Of course, that's locked down on our bootloader, but on other bootloaders, this is definitely a valid process to get the firmware, which is why I wanted to demonstrate it. So I'm just going to get out of here and we will look at how this script runs. So again, I need to run it with sudo. So it's going to be Python 3, and then it was this boot interrupter.py, and I'm going to run it right now. Perfect. And we can see that it just, sent that reboot command, and then it spams this TPL. And we overflowed it a little bit here. So I'm just going to kill this here so we can scroll up. And you see that I overflowed it a little bit here, but we then get into the bootloader. So at this point, this is where we could then send that MD command and read out from the firmware almost bit by bit over the serial connection and write it to a file. And then we could essentially download the firmware over this serial connection. And this is definitely a valid way to do this programmatically. It was kind of a last resort option where you should try and exhaust other options, but sometimes this is the only way to get the firmware. So it's good to see how you can do this through a script. So this really just scratches the surface of what these scripts are possible of doing and what you can have them automate. Off the top of my head, a couple other things that I can think of is you could write a script, for example, that automates the TFTP connection, making the directory and downloading those tools if you didn't, for example, want to keep manually transferring over that BusyBox MIPCell binary. You could automate that all with a Python script. And if you want to, I feel like that would be a really good exercise to go out and try on your own to create a Python script that connects to the serial connection of the router. It makes all of the directories that you need in that /var/temp folder and then automates copying over the BusyBox binary. Another thing we could use for this is potentially trying to brute force a login. So on our shell connection through UART, there was no login, but sometimes you actually will have a login, and maybe we want to try, for example, the top 100 default passwords for IoT devices or something like that. And we could write a brute force type script to attempt all of those logins instead of having to manually try them. That wraps up this video here. I'll see you over in the next one. Welcome everyone. So throughout this section of the course, we've seen how useful and beneficial it can be to get this UART connection and also the shell through the UART connection to our IoT devices. and it's going to greatly aid us in reverse engineering and doing further recon on the device. So in our case, for our router, they made it very easy for us to get this UART connection. Of course, they even went as far as labeling out all of the pins for us. They were nice through-hole connections that we were easily able to connect to. In all of the connections from the pads, they actually went directly to where they were supposed to on the microprocessor. And then we didn't even have a login or anything. We could just connect directly as root. Unfortunately, this is not going to be the case for all IoT devices. So what I wanted to talk about in this video is what happens when we encounter, tricky UART connections or things that designers and manufacturers may do to hinder our ability or users' ability to connect to or use these UART connections. So on the left here, I've got a picture from a Belkin router that I had. And what I do actually, and it's something to get in the hang of if you want to get more into hardware and IoT hacking, is when people are discarding these electronic devices, I'll actually grab them up, and usually they work perfectly fine. They're just outdated or something. And they are a great way to learn for free how to do hardware hacking without having to worry about, destroying or bricking anything that you actually care about. Anyway, so on this Belkin router, I identified these test points here that I suspected were either a UART or a JTAG connection, which is just another type of communication protocol. Now, it's hard to see in this picture, but these are not through-hole connections. These are actually surface mount test points. And that means that we can't actually connect our header pins like we did on our router. We actually have to do something different. There's a couple options for this, but this is what I ended up doing in this scenario. And, for us household hackers where we don't have a lot of expensive gear. So what I ended up doing in this scenario is just soldering wires directly to those surface mount pads. So even without, high-end soldering equipment, you can still make a solder connection generally to those pads. And it's not going to be the most durable connection, but for our testing purposes, that will work okay. And what I did in this scenario is I just then used alligator clips to connect off these wires to a breadboard. And then I just plugged my header pins into that breadboard and was able to get a connection. And you could also even just solder your header pins probably directly to these pads as well, or you could solder them to the wires. You really have a lot of options when you're, doing this breakout soldering. So that is one option. So another option is something like this PC byte device here that I'm showing here. So it's kind of a play on words with PCB and then ITE. And this device works similar to the third hand that I was using, where it holds the PCB in place. And then you see we have these test probes that come off these fairly stiff but still flexible arms. And they're stiff enough that you can actually place these probes up to the test pads. And there's usually a little spring connection in here as well. And what that allows us to do is push down and get a connection through this probe. And then you'll see coming off the probe, we have here and here just those general standard sized header pins that we can then connect whatever measurement device, or for example, our UART to USB adapter or a protocol analyzer right to those pins. You also see in this picture here that they're actually just doing those probes directly onto the leads of the processor. So that is another option with these devices. I'm not going to go over and show all of the different adapters or probes, but just keep in mind also that you can buy a lot of different adapters and probes that can even attach onto your digital multimeter. Just a couple examples that may come in useful is we can get clips that clip onto tiny surface mount devices and allow us to take a measurement. Or we can even get very small hooks that hook onto the leads of surface mount chips like this one here. So just something to keep in mind if you're finding these tricky connections and you're not able to do it with the equipment you have. There is lots of options as far as adapters and things like that go. So outside of those tricky connections that just stem from very small surface mount components or surface mount pads, you may also run into scenarios where the manufacturers of the devices want to hinder the ability to connect to those UART connections. And what they'll do is they will make modifications to the actual board for the production boards that get shipped out that essentially disable the UART connection through the test pads or the test pins. So looking at this picture here, this is actually from another TP-Link router. And you can see this appears to be a UART connection. And on this pin here, can see this trace, which most likely just comes from directly off of a pin on the microprocessor. It would then go to this pad here where we could then, insert our header pin and connect to the UART session. Well, we see here we're missing 2 resistors, and one of the resistors, this R24, this is actually an inline resistor that's just making an open circuit here. So we won't actually get any measurement on this pad other than just 0 volts, and we won't actually be able to read anything off of it. So to demonstrate what's going on in this scenario here, and then also something that is not too uncommon to see with these UART headers, I've got a type of pseudo schematic here to represent what's going on. On the left here, we've got what would be our microprocessor. And of course, it would have many more pins than this in the actual one, but all we're really caring about in this is those UART pins. We've got the RX, TX, ground, and VCC. And then on the right here, we've got the actual test pads that would go out to our UART connection, just like they did on our TP-Link router. So we'll start with the TX pin, and if you remember what came off of the TX pin on our router, there was lots of useful information, especially during boot up. And what we're seeing here is that they put an open circuit, and there would be pads here for a resistor or just some sort of straight through connection. And this is actually then blocking our ability to read off of this pin. If we read this, we'll get nothing. So generally to fix this, we can actually just bridge this either with a very low impedance resistor or just with a straight wire and see if it works. One way that we can test is if we can actually just find the pad here on the other side of where the resistor would go, then we can actually take a measurement with our multimeter. And if we're seeing the measurement come off at 3.3 volts or closer, then that's a good indication that we can just bridge this straight across with a wire. Another thing that you may see is the usage of either a pull down or pull up resistor. So what a pull down resistor does is it stops this pin from being what's called a floating pin. Now you may remember when we were talking about our digital communications that we have this threshold for determining whether an input to our pins is either a digital high or digital low, depending on the voltage that's applied. And usually that threshold is above a specific number and then below a specific number. And if it's anywhere in between, well, we're going to kind of get this randomness of whether it determines it to be a high or low voltage. Now you may expect if we just have nothing connected to this pin, well, it will be at 0 volts. Unfortunately, that's not the case. What that's called is a floating pin, and in a floating pin, we'll generally have that voltage fluctuates somewhere in that mid region where then we're just going to get a randomness of the inputs. One of the ways to get away from this is to use what we call either a pull down or pull up resistor. And what we will generally do is we'll connect a very, very high resistance resistor to either the ground, or if we have a pull up, we'll connect it to the VCC voltage. And then that will essentially pull this pin when there's nothing connected to it to either ground or high. And then it's easier for the designers of the software to determine that it's not actually just that floating randomness coming to this pin, it's actually communication. The reason that we use a really high impedance resistance value here is then that doesn't actually affect real transmissions because they're going to be mostly unaffected by this very high impedance value, and they'll be able to have most of their transmission voltage go straight to the receiving pin. So what designers of the board can do though is when they go to production, they'll switch this out from a high impedance resistor to a very low impedance resistor, or just sometimes connect it directly to ground. And what that's going to do is it's going to sync our ability to be able to transmit on this line, because essentially everything's just going to go down to ground, and it's going to be very high for us to pull the voltage up high enough on this RX line to be able to trigger that transmission. So if that's the case, then we're going to need to go and either just remove this resistor entirely, or we'll have to swap it out with a higher ohm resistor. Just the presence of seeing this pull down or pull up resistor, that doesn't mean that the transmission line's not going to work. And in some cases, it can actually be required because it needs that stability of being pulled, for example, down to ground in order to work. And that's what we're actually seeing over here with this missing resistor. This is most likely a pull down resistor. It looks like it's going to, this whole area is a ground pad, and it looks like the pull down resistor is not here. So to fix this connection, we actually may need to add a high impedance resistor in here, and then a low impedance resistor here. So this is where all of the theory and our testing skills with the multimeter will pay off from Electrical Engineering for Hackers 101 in helping us to sort out these different connections and being able to trace out or beep out where the pins are going and identify if we're missing resistors or we have extra resistors that are going to block our connections. So the last thing I want to talk about is what happens if we get our UART connection working. I think we may be able to get a shell, we hit enter, and then we are prompted with this login. Are we stuck at this point? Well, as hackers, of course, we're not. There's a lot more we can go ahead and do further to be able to try and get logged in. So the very first thing I would suggest you do is Google is, of course, your friend. And a lot of times someone else will have figured out this password or it will have been leaked. And you can just easily find the default password for this online and then log in with that. The other thing that we can do, and this is kind of skipping ahead a little bit to what we're going to cover in the next lesson, but you will remember that we were able to find the passwd file and we were able to crack the password for that. Well, if you're able to dump the firmware and then extract the file system, you're most likely going to be able to find some sort of hash of the password that you may be able to crack, and then you can log in with that. The other thing that I do want to quickly talk about as well is that sometimes through the bootloader and the bootloader menu that we uncovered, you will be able to set environment variables. And sometimes these environment variables will switch the device to log into some sort of factory mode or factory setting. And in this factory setting, there will be no login. Well, how would you figure out about this? Again, this is where this reverse engineering is going to come in handy when we reverse engineer either the bootloader or those initialization scripts. And we'll take a look at reverse engineering in the next lesson. So there's lots of different things that you may encounter either with the physical connections or the logins that make it a little bit more difficult for us, but not to be discouraged. Of course, with a little bit of searching and hacking, you can usually get in. With this video, I just wanted to give you some areas where you can get started if you do run into these issues. That wraps up this video. I'll see you over in the next one. Welcome everyone. In this video, we're going to take a look at troubleshooting UART connections. So this is stuff that's just good to know. However, different from our previous video where we were talking about tricky UART connections, these are all going to apply specifically to the UART connection that we are establishing to the target router in this course. This video is optional in that if you were able to get everything working with your UART connection and you did not have any issues, then you don't necessarily need to watch this video. If you did run into issues with your UART connection, then I do ask that you try everything in this video first before reaching out over Discord or trying to contact me to get some assistance. So the very first thing we're going to start on is checking our pinout. Now you'll want to check this if you are not getting any connection whatsoever, either transmission or receiving. So if you're having issues either with one of those two or both, then you should go and check your pinout and your connections. So what I would suggest to do, and I know this sounds obvious, but I have made this mistake and wasted many hours before without checking this, is go back and double check and make sure all of your wires are going to the proper spot. So we have this handy pinout. I won't go over it again, but just double check and make sure all of your wires are going to the correct spot. After you have verified that and checked it, if it did not fix your connection, then I would also suggest you go back, take your multimeter and double check all of your connections are still good. This is especially important and true if you did not solder your header pins here and you are using the twist tie. Over time, that's going to come loose and you're going to get bad or intermittent connections. So what I would suggest is go and take your multimeter and measure at each of these pins and make sure you are getting what you expect to. So on VCC, you should be seeing 3.3 volts. The ground should have continuity over to this ground or the ground on the input jack. The RX pin should be at 0 volts and not have any continuity to ground. And then the transmit pin should be at that 3.3 volts or fluctuating during transmission. I would also suggest going even further and testing those at this point as well. So you can also check the voltages and continuity from these pins as well. And that makes sure that you do not have any issues with your connections through the wires or the wires themselves. If you have tested all that and it is working okay, the other nice thing with the one linked package of this USB to UART adapter is that it comes with two, so you can try and swap it out to the other one. Okay, moving on. The next issue that I sometimes run into and I wanted to show is that if your shell starts to get messed up and you start seeing things like your prompt is moving across the screen, or it's not picking up all the letters, or it's just starting to get really messed up, what can happen is that there is a buffer in the USB to UART adapter and it can start to get kind of messed up. And I sometimes see this when screen doesn't properly detach from it. If you just close a terminal window without detaching, sometimes this happens. The easiest way and the best way that I have found to fix this is just to power cycle the USB to UART adapter. And to do that, you just need to unplug it from the USB power. And then I also suggest power cycling the router. If that doesn't fix it, I would also suggest restarting your VM. So your best bet to fix any of these issues is to power cycle the USB to UART adapter, power cycle the router, and restart the VM. And that usually fixes these issues with the shells being messed up. Okay, we've already gone over this one, but I just want to go over it again because it is something that I see frequently. If you are getting these messed up characters like this means that you have something wrong in your UART parameters, most likely your baud rate. So go back and double check and make sure you're using all of the correct parameters. So the TP-Link router that we're using is that 115,200 baud rate. Okay, the next thing I want to show is if you're getting this error where it cannot execute this /dev tty and then your USB, no such file or directory. There's two possible issues here. So one is that you have not connected the device to your VM. Remember, you need to go into the removable devices and then connect that device to the VM from your host computer. The other possible issue is that that file has been renamed. There is another one at, for example, maybe 1 or 0, and it has renamed. So two easy checks is we should run this ls USB and then make sure the UART device is listed here. So it's this one. If it's not, then it's either not plugged in properly or you haven't connected it to the VM. After that, we can run this ls-l/dev/serial/by-id, and that will give us that actual device file, and then make sure you're using this for your screen connection. Okay, the next one that I want to show is if you are just having your screen session be terminating like this, and this is an issue that I run into. This means that it probably does not have the proper permissions to access this folder, the dev folder. So you need to either go and change the permissions for that, or another easy way to get around that is to run it as sudo. So just a really quick video here on how to troubleshoot some of the common UART connections. Hopefully this helped you out if you are having some issues. I'm going to wrap up this video here and I'll see you over the next one. Welcome everyone. In this video, we're going to do a quick review of what I have added to my notes from this section of the course. In doing so, you can compare your notes to mine, and then also it will serve as a quick review of what we've covered so far in this section of the course. The first thing that I did was add the test equipment here. So we have this USB to UART adapter and the manufacturer and part number here. We also used the screen software, so I've added that to our software used. Scrolling past our previous notes from the initial Recon, I'll go down to where I started our notes here. And we started our enumeration via that UART connection. So the very first thing we want to do was review the boot logs. And in order to do that, we of course connected our USB to UART adapter. And we did so with this pinout here. So I think it's good to add things like this to the notes because it's going to help anyone who is following along or needs to validate them to be able to follow our steps. Another thing that I've added for the same reason is I add copies of the commands that were run so that they can easily be rerun by anyone following along. Of course, the first thing that we saw after powering on the router was all of the logs from the bootloader and Linux initialization. So I've copied that in its entirety into the notes, which I think is a good thing to do. However, I'm not going to go over them all again here. What I did do though is I added in some notes about the very important and key details from there. So the first key detail that we saw was from the bootloader, and that was the versioning of it. It appeared to be a repurposed build of the open source version of U-Boot at 1.1.3, and we then saw that there was some internal versioning of the RA-Link U-Boot, and we saw the versioning of that. We then noticed the default selection of the bootloader to system boot via the flash, and we thought that this may be able to be interrupted, so we could choose a different option and access the bootloader menu. Moving on from there, we saw lots of good details from the Linux initialization. Of course, the first thing that we saw was the Linux versioning, and then also the version of build root that was used to compile the Linux kernel. We also got some details about the CPU, so if we didn't already know it was MIPS architecture, then we would now know. We also saw this very important kernel command line, and in this command line, we saw some important details. First, we see, interestingly, this console equals TTY-S1 and the baud rate. So this is actually the console session that we were connecting to over UART, and this is the baud rate. The other important details we saw from here is that we have this root fs type file system of squash fs, and then we also saw the initialization binary is in sbin/init. So important details there. We also got some important details about the boot partition. The first interesting detail that we saw is we actually got the part number of that flash ROM. This is that Cepheon chip that we were looking at. So if we weren't able to identify that through the pictures, this is one other way. We also then got details about the 5 partitions that are created on the ROM and the specific addresses for those partitions. This is going to come in useful later when we are reverse engineering and analyzing this firmware. We then noted the location of what appeared to be another initialization script at this etc/init.d/rcs. We also noted multiple configuration files being used in the initialization and startup, and this one below here at the etc/reduced_datamodel.xml appeared to be one of the main configuration files being used. We also noted some information about dropbear, and one of the initialization logs showed a writing of the dropbear RSA key into the var/temp folder. This indicated to us a writable path that we could use later if we needed to bring some tools over. We were then able to perform an interrupt of the bootloader. Through our online research, we were able to discover that the interrupt command for TP-Link devices is TPL. And there's a very small window to interrupt this bootloader, so in order to do so, it's best to just actually reboot it through the command prompt using this reboot command. And after that, we could then just type TPL repeatedly, and we are actually able to access the CLI or command line interface for that bootloader. When we tried running some of the known commands for the U-boot command line interface, including even help, we noticed that unfortunately the modified version of U-boot that is being run seems to have all of this additional functionality removed. The only functionality that we had left is the TFTP boot. We then moved on to our initial enumeration via the UART shell, and of course pressing enter revealed that there was shell access with no logon as the root user. Our first quick check over the binaries revealed that we had BusyBox available to us. Of course, we learned that BusyBox is this popular binary used on embedded systems to package many Linux and Unix binaries into one smaller version. When we took a look at the currently defined functions, we noticed that this appears to be a reduced version of the full version of BusyBox. However, TFTP was still available, so we could probably bring over the full version of BusyBox. We then went ahead and transferred over that full version, and I just put the steps here. I won't go over them again, but all the commands we run and the steps that we did so that anyone who would like to follow along could do so. After transferring over BusyBox, we actually used the updated BusyBox, which included grep, to start enumerating over that /var folder. Again, we only worked on enumerating the /var folder with our shell connection because we are going to do the other read-only portions of the file system on our actual Linux host computer using the tools that we have when we do our firmware analysis. I've listed the commands that we run in order to grep and look for passwords, and we noted the interesting config files and those passwords that we found, such as the dropbear password, and then also the shadow file or passwd file that we found with the hashes. Of course, we also searched for interesting files with XML and conf. We then went ahead and attempted to crack those password hashes, and of course I have the commands that we run, and of course I showed how we were able to crack these passwords with Hashcat. Since this is educational purpose notes for everyone in the course to follow along, I've actually put, the screenshots and how everything worked. However, if you were doing this for a client, then you may not want to actually put any of the hashes or how they were cracked specifically in your notes. You may want to leave those as confidential. Of course, we also cracked the dropbear one. The next thing we did was check the running processes and network connections. Of course, the first thing we did is run PS and take a look at the processes running. One thing of note is that all of the processes were running as the admin user and there was no principle of least privilege being followed. Of course, we also used a similar process to check the running processes using netstat. Finally, we then took a look at the console log messages that were streaming through and worked to prompt some additional console log messages. When we looked through the unprompted console log messages, we did see one repeating that stood out, and that was this one from util exec system where it was unsetting the time zone. We noted that this repeated call appeared to be indicative of a log from a function in a shared object library. It also appeared that this is an exec system call, which is a C function that allows running of a system command. And of course, these can be dangerous in nature for command injection if the function uses user input. Because of this, we wanted to check and see if we could identify any areas where our inputs to the web portal would actually trigger any of these exec system calls or other interesting functions that we could go in reverse. To do so, we started by just doing the wireless setup, and we set it with these settings. And once we hit next, we then took a look at the console logs, and I put a whole copy of all of those console logs here, and we can see numerous times that the exec system function was used for user supplied inputs. Of course, primary investigation showed that some user validation was being performed on the inputs, and notably, if we scroll up here and look at the pre-shared key, so the wireless password and the SSID, we can see all of this individual escaping of characters, which is good practice because this is going to generally thwart any command injection attempts. Of course, further investigation is going to be performed using the function names to trace back and reverse engineer the firmware. So now that we are able to trigger those console messages and then trace back and see the underlying function calls that are being made, we're going to use this in the future to aid in our reverse engineering. That wraps up what I have added for the notes. If you had them differently or you added extra things, then kudos to you. Really, just any notes you're taking is a great step, and it's really important to be taking these notes. I'm going to wrap up this video here, and I'll see you over in the next section. This brings us to the end of this YouTube version of the course. So first off, great job on making it this far. I really hope you enjoyed it and you learned something. If you want to finish up this course and get the last 3 sections that go into reverse engineering and unpacking the firmware and the end of course challenge, you can get access to those on the TCM Security Academy, which again, I will link down below. And then if you enjoyed this course and you want to see more full-length courses, make sure you're subscribed to the TCM Security YouTube channel. We're closing in on 1 million subscribers, and we would love to get there, so would really appreciate it if you check if you are subscribed. Thanks again for watching, and I hope you enjoyed. I'll see you again next time.